Hi everyone, I'm sure you can see from the length of this video. Here is my all-in-one A2 chemistry video. It's obviously super long and that's because there's a huge amount of content. If you guys have been following me through your GCSEs and IGCSEs, you'll know what to expect. We're looking at exam-specific wording, making sure that you're maximizing your marks. Obviously, chemistry is a very complex subject, so I'm going to be taking you through all those difficult techniques, whether it's to do with the Arrhenius Equation, Born-Haber Cycles, Electrochemical Cells, so you'll find it all here. Do leave me a comment. Obviously, keep track of where you are in the video by putting a little timestamp in the comments below. But yeah, I really hope you like this. It has taken me approximately 2 months, 8 hours a day. I cannot explain how long it's taken me. One extra thing I wanted to mention is throughout you'll see me referring to a document that is my perfect answer revision guide. These are PDFs available at swhlearning.co.uk. If you're not familiar with the other products we have, we run a tuition agency, so for anyone needing that extra support, the one-on-one support, we have amazing tutors that can help you there, including myself, in case you'd specifically like me to help you. We also run online courses, particularly Easter. Now, these revision classes are an incredible way of covering huge amounts of content, looking at exam wording, how to answer those super difficult questions. The command words are super tough to get to grips with. That's why you should attend the online courses with SwH Learning as opposed to other providers who don't have the same focus on exam board specific content. Let's now consider Born-Haber cycles. Now, lattice enthalpies can't be measured experimentally, and so we calculate these values using the Born-Haber cycle. I know Born-Haber cycles can look pretty scary, but they're simply building on everything you guys learned in the first year related to Hesse cycles. I've just dragged in some Hesse cycles here to remind you that in the situation when you can't measure the direct enthalpy change, remember you can follow an alternative route to arrive at your answer, and it doesn't matter what route that is, as showcased here. And you're going to use that theory when it comes to the Born-Haber cycles. Now, unfortunately, the worst thing about this topic is the list of definitions. And I can't believe I'm saying this, but you will need to know these all off by heart. And not only will you need to know them off by heart, but you'll actually have to apply them in order to construct the Born-Haber cycles. So the mean bond enthalpy is the energy required to break a covalent bond in a molecule, averaged over a range of compounds. The enthalpy of formation, you'll be familiar with, is the enthalpy change when 1 mole of a substance is formed from its constituent elements under standard conditions, with the reactants and products being present in their standard states. Remember that standard conditions are 100 kPa and 298 Kelvin. Enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state under standard conditions. The first ionization energy you'll have met near the beginning of the course. This is the enthalpy change when 1 mole of gaseous atoms each lose an electron to form 1 mole of gaseous ions with a single positive charge. Ionization enthalpies are always positive because energy has to be put in order to pull that electron away from the attraction of the positively charged nucleus. The second ionization energy is the enthalpy change when 1 mole of electrons is this time lost from a mole of singly positively charged ions. So here's the crucial difference here between the first and second ionization energy, as well as the product formed. The first electron affinity is the enthalpy change for the formation of 1 mole of negative 1 minus gaseous ions from 1 mole of gaseous atoms, as shown here. These are always negative as there is an attraction between the nucleus and the electron, meaning that energy is released when the electron is gained. The second electron affinity is the enthalpy change for the formation of 1 mole of gaseous 2 minus ions from 1 mole of gaseous 1 minus ions. So we're just taking that previous step one step further. These are always positive as energy must be put in to overcome the repulsion between the electron and the negatively charged ion. The lattice enthalpy of formation is the enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions. These are always negative because when the lattice forms, new bonds are formed, resulting in energy being released, which remember is an exothermic reaction. Lattice enthalpy of dissociation is the enthalpy change when 1 mole of solid ionic compound separates into its gaseous ions. These are always positive because energy is required to break the bonds in the lattice. You can see in the instruction here in my revision guide, You always want to look back, you always want to refer to these definitions when working through various questions. Now we're going to draw out a Born-Haber cycle using these definitions to illustrate how it's assembled. So in this example, we're going to be drawing a Born-Haber cycle, and we're going to use that to determine the lattice enthalpy of formation of copper oxide. So I've drawn two lines here. This is going to be my start. This is going to be my finish line, the end. Remind yourself of the definition of the lattice enthalpy of formation. It's the enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions. So that means the solid ionic compound is here, the gaseous ions must be here. And here's my solid product. So that is my lattice enthalpy of formation. So this is in effect my X, my lattice enthalpy of formation. As I previously said, we can't work out this value experimentally, so we're going to have to use a different route akin to the way you were doing the Hess cycles in order to calculate this value. So the next thing to be aware of is down here, you need a way of producing that solid copper oxide but through a different route, and the way to do that is using the enthalpy of formation. So to remind you, that means 1 mole of substance being formed from its constituent elements under standard conditions with the reactants and products being in their standard states. That's why it's so important you know the definition, because that tells me straight away that my copper must be solid and that my oxygen must be in gaseous form, and we're producing 1 mole, so that will help me balance my equation here. So that's my standard enthalpy of formation. So now I need to create my alternative route that will take my elements in their standard state to the ions in their gaseous state. And for each step you write down, you're only changing one thing each time. Bear that in mind. So the first thing you want to do is to change the state of the copper. We're only touching the copper in this stage, so we're going to atomize it, which according to the definition means that we're forming 1 mole of gaseous atoms from the element in its standard state under standard conditions. And look, here's an example there. So there's my copper forming a gas, and my oxygen remains the same. My arrowhead points upwards because I'm forming the gas. Make sure you label this. It's the standard enthalpy of atomization of copper. We now need to ionize the copper. Remember that copper forms a Cu2 plus ion, which means we need to effectively do a first ionization of that copper and then a second ionization. So that is our next two steps. We form the 1 plus ion initially, keeping the oxygen the same. And here's the electron that we've removed, and we'll label that the first ionization energy. Now we'll do the second ionization. So this time we're forming a Cu2 plus ion. The oxygen remains the same. We now have 2 electrons, and then label it. So just double check, sit back, look, your copper is exactly where it needs to be. So it's now time to turn our attention to the oxygen. The first thing we need to do is atomize it, because at the moment it's O2 and we need to get it as an individual atom. Noticing that everything else remains the same, do label this. It's the enthalpy of atomization of oxygen. And notice, because we had half an oxygen in here, we only create 1 atom. Now we check your definitions. This is when first electron affinity becomes important, because it's the enthalpy change for the formation of 1 mole of negative 1 minus gaseous ions from 1 mole of gaseous atoms. Because it's a negative value, we do need to make sure that line sits lower. I'm changing colour just so it doesn't get too complicated. The copper stays the same, and then the electrons cancel out, so we end up with only 1 E minus. That's your first electron affinity of oxygen. And then our last stage, guys, we're almost there, is we need to do the second electron affinity. Remember, we said it's always positive. And then remember, because we're using that electron, we're adding it to the oxygen to form the O2 minus. That's why it doesn't appear up here. But after all that hard work, we've constructed our Born-Haber cycle. I know it looks super complicated, but just take a step back. What was our first step? It was to atomize and then ionize the metal. Then really the second step was to atomize and then ionize the non-metal. And that's how we constructed the left-hand part of our diagram. I'm now going to add some numbers so you can see how you'd actually carry out the calculation. You would be given these numbers in the question, but I'm just going to add them here. I'm not going to put the units because I don't want it to get too complicated. Remember I said that this is your X value, so we're going from here to here. But in order to do the calculation, we're going to follow this route this way. Just make sure you acknowledge the signs. We're going against the arrowhead. So it's minus 790, plus 141, minus 249, minus 1960, minus 745, minus 339, minus 155, because that's following the direction of the arrowhead, equals minus 4097. I'll introduce the units, kJ per mole. And remember your X was the enthalpy for the lattice formation. So what to take away from this? Learn your definitions. Without the definitions, you can't do anything. Put the solid product at the end. Top right, you're going to list the ions needed to make that product. That will be your standard enthalpy of lattice formation. And then here, you're going to construct your Born-Haber cycle, first by atomizing your metal, then ionizing it, making sure the ion formed is your standard ion. Same for your non-metal, you're going to atomize and then ionize, and then just follow the route, making sure you reverse any signs based on which direction arrowhead is pointed. Now they do alter what it is they're asking for. So in this particular example, we're being asked to construct a Born-Haber cycle for magnesium bromide in order to calculate the first electron affinity for bromine. So we've got lots of data here that you'll be familiar with that we're going to use. We're going to start like we did in the previous question by doing the lattice enthalpy of dissociation. So showing the working out for that. Remember that involves having the solid compound at the bottom. So our first step is the dissociation of magnesium bromide into its ions. So we'll draw the ions up here. Remember we're forming 1 mole, so that will dictate your ions. Be careful with your arrows. Because they're dissociating, we need to point the arrow in this direction. So this is the lattice enthalpy of dissociation. Before we start atomizing and ionizing the magnesium and then the bromine, the first thing we need to do is do our enthalpy of formation of the magnesium bromide. So we list the elements here in their standard states. Now we're ready to get going. We're going to start by atomizing the magnesium, which means turning it from a solid to a gas. Remember the bromine remains the same. We only change one thing in each step, pulling the numbers from the table. Next up, we're going to form the Mg plus ion, so the first ionization energy of magnesium. Because magnesium forms 2 plus ions, we need to do the second ionization energy. Don't forget to add your electron. So we form the Mg2 plus ion. Bromine currently remains the same. So that's your second ionization energy. We're all good now for the magnesium. It's time to turn our attention to bromine. Let's atomize it. Just be a little bit careful here. Remember, we're going from that bromine diatomic molecule to 2 atoms of it, which is why we need to double this number here. And then we're trying to form our bromine ion. Check your definitions. You're going with the non-metal, you're forming the negative ion. This is your first electron affinity, and after all, that's what the question's after, so that in effect is your X. Remember, first electron affinities are always negative according to that definition. So that's going to take us from our gaseous bromine to the negative ion. Because we're forming 2 negative ions, we need to multiply that number by 2, and after all, that's our X value. And that explains why we've lost the 2 electrons as we go from here to here, because each of those bromines has gained an electron to form the negative ion. So now we're ready to do the maths element. So we're after 2x. Let's go around this way, making sure we pay attention to the arrowheads. We're going against this one, so it becomes 2 times minus 112, minus 1451, minus 738, minus 148, minus 524, plus 2440. So that comes to minus 645. Divide it by 2. Add your units, kJ per mole, and that is your first electron affinity calculated for bromine. And there's your final answer. This is absolutely a topic which needs past paper practice. We're going to start with question 1. Define the term electron affinity for chlorine. Just going to copy in the definition from my guide. So it's the enthalpy change for the formation of 1 mole of negative gaseous chlorine ions from 1 mole of gaseous chlorine atoms. Complete this Born-Haber cycle for magnesium chloride by giving the missing species on the dotted lines, include state symbols where appropriate. It's so great when they do this because they give you lots of clues. We can see straight away here that we've got ions, so we just need to add the chlorine ions in gaseous form. This is enthalpy of formation, so we're taking the elements in their standard states. So magnesium is solid, chlorine, you must remember, is a gas. Following this arrow, we're atomizing the magnesium, we're keeping chlorine the same. Next step, we're doing the first ionization of magnesium, keeping chlorine the same. Make sure you show that electron. Because magnesium forms 2+ ions, we need to show that through the addition of those 2 electrons. And then next up, we need to deal with the chlorine by atomizing it. We've got Cl2 gas here, but we need to form 2 chlorine atoms. So that's done. And then just to prove, look, we've got our electron affinity. We're forming chloride ions from those chlorine atoms, changing only one thing in each stage. Now we're being asked to use our Born-Haber cycle from part B and the data in that table to calculate a value for the electron affinity of chlorine. So let's go up here. Let's label a 2x here. Why? Because we're forming 2 chloride ions. So I'm going to write it here so you can see it more clearly. Let's label the numbers. So this is lattice formation here, minus 2,493. This is enthalpy of formation, minus 642. Here we've got atomization of magnesium. Then we've got first ionization of magnesium, plus 736. Second ionization, plus 1450. And then here we are atomizing the chlorine, plus 121. Don't forget to do that number twice because you've got 2 chlorine atoms being formed. So we're going to head in this direction. Make sure you acknowledge the arrowheads. We're going against this arrowhead. So we do 2 times minus 121, minus 1450, minus 736, minus 150, minus 642, plus 2493. So that comes to minus 727. Divide by 2 to find x to get minus 364 kJ per mole. Let's do this example now for silver fluoride. So in our first step, we're doing our enthalpy of formation of silver fluoride. Remember, we're forming 1 mole, so just be a little bit careful here. Yes, we know the standard state of fluorine is a diatomic gas, but because we're forming 1 mole, we need to put a half here. Then as we move up, we atomize the silver, keep the fluorine the same. Then we do the first ionization of silver, acknowledge the electron, and then next up, we're atomizing the fluorine. Use the cycle in part 1 and the data here to calculate a value for the bond enthalpy of the fluorine-fluorine bond. So this is a little bit confusing. It actually refers to the atomization of the fluorine, but if you're not sure, just fill in all your other numbers and see where your X is. I'll show that that works now. So we know that the enthalpy of formation of silver fluoride is minus 203. We know that the enthalpy of lattice dissociation is plus 955. The electron affinity of fluorine now of minus 348, remember, goes here. The first ionization energy for silver goes here. And then the enthalpy of atomization for silver goes here. Where's our X? We can see it goes here. This is our X value. So according to the direction the arrowhead's pointing, tells us that our start is here, our end is here. Do add these labels if it helps you, and that tells you that we're heading in this direction. Just make sure you acknowledge those arrowheads we're going against. So that's minus 732, minus 289, minus 203, plus 955, plus 348. Put it into your calculator. The answer here is 79 kJ per mole, but do check. Just one final sting in the tail. This is half your value due to that half there, so you just need to multiply it by 2 to get your final answer. Right, moving on to enthalpies of solution. Just remind ourselves that the lattice enthalpy of formation is the enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions, and here's an example equation right here. The lattice enthalpies of formation are always negative because when a lattice forms, new bonds are formed, resulting in energy being released, so an exothermic reaction. So now we've recapped that definition, it's now time to understand that lattice enthalpy values are affected by the size of the ionic radius. So the larger the ionic radius, the less exothermic, the closer to zero the lattice enthalpy will be. And the reason for that is because the attraction between the outer electrons and positive nuclei decreases as the radius increases. The second thing, the charge of the ions, the greater the charge, the more exothermic, the more negative the enthalpy of lattice formation. So let's make a few comparisons, bringing into account both the size of the ionic radius and the charge on the ions. We already said that the smaller the ionic radius and the greater the ionic charge, the more exothermic the enthalpy of lattice formation will be. And this is true here if we compare magnesium oxide with barium chloride. Remember that magnesium group 2 will have a 2+ charge, oxygens in group 6, O2-. In terms of their ionic radii, they're going to be small ions, they're highly charged, which means they have a large enthalpy of lattice formation. Barium chloride, however, barium is much lower in group 2 compared with magnesium. It has a much larger ionic radius, meaning that the barium chloride will have a smaller enthalpy of lattice formation compared with magnesium oxide. The lattice enthalpy can also be calculated theoretically using a perfect ionic model, which assumes that ions are point charges, ions are perfect spheres, and only electrostatic attractions occur between the ions. So we're making a statement that only ionic bonding occurs and that there's no covalent character. However, in reality, bonds usually have both ionic and covalent character. And actually, the Born-Haber cycles, because they're based on experimental data, they're actually more accurate because they take into account the fact that both ionic and covalent character exists within the bonds. Whereas the theoretical lattice enthalpy values are based on the perfect ionic models, and that explains why these values are often smaller than those calculated using a Born-Haber cycle. To explain this further, it's because the covalent bonds are stronger than the ionic bonds, and therefore we can make the following conclusion, which is that the closer the theoretical and experimental values, the more ionic the character of the bond. 2 more definitions now, they never end. Enthalpy of hydration, this is the enthalpy change when 1 mole of gaseous ions are converted into aqueous ions, so an aqueous solution. So there we are turning from a gas to aqueous. The enthalpy of solution is the enthalpy change when 1 mole of a solute dissolves completely in sufficient solvent to form a solution in which the molecules or ions are far enough apart not to interact with each other. When an ionic compound dissolves in water, which is a polar solvent, the positive ions of the ionic compound are surrounded by delta negative oxygens. The negative ions are, however, surrounded by delta positive hydrogens. And now we're ready to draw thermochemical cycles in order to determine the enthalpy of hydration or solution of an ion. So in this question, we're using the data in the table to construct a thermochemical cycle for the enthalpy of solution for magnesium hydroxide, and we're calculating that in kJ per mole. Before we get going on this, I just want to remind you that this lattice enthalpy of dissociation, we met it previously in the Born-Haber cycles. Remember, this cannot be determined experimentally. We need to do a number of steps in order to calculate it by going through an alternative route. So just to remind you, look, here's a Born-Haber cycle for magnesium bromide, and it's that enthalpy of lattice dissociation that we see here that we calculate by going through all these other steps involving atomization and ionization. So this remains in essence the same approach, but we're just going to look at enthalpy of solution and enthalpy of hydration. So I've pulled in the 3 key definitions here, the ones we'll constantly refer to. So the first thing we want to do is set ourselves up for the lattice enthalpy of dissociation. Remember, it's when 1 mole of solid ionic compound separates into its gaseous ions. So at the bottom, I'm going to show the solid compound, 1 mole. So let's separate it into its gaseous ions. So remember, Mg is in group 2, so it will form Mg2 plus ions. It's gaseous. Will form 2 hydroxide ions with the OH minus charge. And remember, this is your enthalpy of lattice dissociation. Now we need to include these other definitions. So the enthalpy of hydration, so we are turning these into aqueous ions effectively. So the enthalpy of hydration is when 1 mole of gaseous ions, which we have, are converted into aqueous ions. And remember, we do this one step at a time. So let's take the Mg2 plus, turn it into aqueous ions, keep the hydroxide the same, label this. So enthalpy of hydration of the magnesium ions. Let's get our hydroxide ions into aqueous solution. Label that line. And then our final step is to go from aqueous ions to the solid. Check your definitions again. Enthalpy of solution is the enthalpy change when 1 mole of a solute dissolves completely in sufficient solvent to form a solution in which the molecules or ions are far enough apart to not interact with each other. In other words, you have dissolved the solid, and that's why this particular arrow will go in this direction, showing that that solid has been dissolved. So this is how you'd set up your cycle for enthalpies of solution. Obviously the question varies in terms of where your X value will be. Here we're being asked to find the enthalpy of solution, which means that it's actually this one here that's the X value. Sub in the rest of your numbers using the table. There's your start and end labels. So acknowledge the arrowheads as you go around. So that's in the same direction. So it's 2842 minus 1920. Just be a little bit careful here. Look, we have 2 hydroxide ions. So we do 2 lots of minus 460 because there's 2 hydroxide ions being formed in aqueous solution. Put that into your calculator. So that gives us a final answer for our enthalpy of solution of 2 kJ per mole. Just a few extra things to point out. The enthalpy of hydration value is affected by the ion's radius and charge. This means that as the ion's radius increases, the enthalpy of hydration decreases. It becomes less exothermic. For positive ions, so positive cations, this is because as the ionic radius increases, the force of attraction between the metal ion and the delta negative oxygen of water decreases. For negative ions, negative anions, this is because as the ionic radius increases, the attraction between the non-metal ion and the delta positive hydrogen of water decreases. And then lastly, as the ionic charge increases, the enthalpy of hydration increases, becomes more exothermic. The greater the charge to size ratio of an ion, the stronger the attraction to the delta negative oxygen and delta positive hydrogen of water. So for example, the hydration enthalpy of magnesium ions, Mg2+, is more exothermic than for the sodium ion because the magnesium ion is smaller and more highly charged, meaning that it attracts the delta negative oxygen of water more strongly. So let's look at a past paper question. When magnesium chloride dissolves in water, the enthalpy of solution is minus 155. The enthalpy of hydration is minus 364. Calculate the enthalpy of hydration of magnesium ions. We've been given lattice dissociation enthalpies for these substances. So we'll start with our solid magnesium chloride at the bottom. Now we'll do a lattice dissociation enthalpy for that magnesium chloride. So we know we're going to form magnesium ions and chloride ions. Add my arrow, get it labelled. Now we need to get the magnesium ions and chloride ions into aqueous solutions. So let's start with the magnesium. We only change one thing at a time. Get that labelled. That will be your enthalpy of hydration. And that's actually our X value here. That's what we're being asked to find. Now, I know automatically you probably want to hydrate your chloride ions and turn them into aqueous ions, but just be a little bit careful here. We've been told that the enthalpy of solution is minus 155. That minus is important. Remember, enthalpy of solutions is all about dissolving your solid and forming your aqueous ions. So because it's minus 155, you actually need to draw your aqueous ions lower than the solid magnesium chloride. So that there is minus 155. So you're now finally ready to do your hydration of chloride ions. Just drawing an arrow down here. So that's your enthalpy of hydration of chloride ions, which we know is minus 364. You're almost ready. Add a start here, end here, and then just follow this route in this direction, making sure you acknowledge the arrowheads. So x equals, that arrowhead is going against, so we need to do minus 2493. This is going in the same direction, so it's minus 155. This is going against the arrowhead. Take care, remember you're forming 2 chloride ions, so we need to actually multiply that minus 364 by 2. So your final answer will be minus 1920 kJ per mole. Gibbs free energy and entropy change. Now, the word entropy is incredibly important. It's the measure of the randomness of a system. If your products are more disordered than your reactants, we say that the entropy change is positive. And then if your products are less disordered than your reactants, then we say that the entropy change is negative. What is the unit of entropy? The last thing to be aware of is that entropy values are always positive. The only exception to this is if we have absolute 0 Kelvin, and at this point entropy will equal 0. When it comes to predicting entropy changes, as you can see from these particle diagrams, gases are the most disordered, solids are the least disordered, and as a result, gases have greater entropy compared with solids. Now we can predict entropy change, so delta S, by looking at the states of the reactants and products. So in our first example, we're taking ammonium chloride, which is a solid, producing ammonia, the gas, plus HCl, a gas. So here we can see that 1 mole of a solid on the left-hand side of the equation is converted to 2 moles of gas on the right. As a result, we can see that on the right we have more disorder. So in this case, the entropy change, delta S, is positive. Let's take a second example. We're starting with sulfur dioxide gas, reacting it with oxygen, a gas, to produce 2SO3, so sulfur trioxide, also a gas. Count the number of moles. We've got 3 moles of gas on the left-hand side, 2 on the right. The products are less disordered, so we've got an entropy change which is negative. But all of this was really gearing up to work out how to calculate entropy changes. We need to use this formula. Delta S reaction is the entropy of the products minus the total entropy of the reactants. So a classic question here where we're being asked to calculate the entropy change. Start by stating the formula. So our products, look at the water, it's 70 minus the entropy of our reactants, to get an entropy change of minus 163.3. Do make sure that you check to see if your answer makes sense. Look, we've gone from a gas to a liquid, so we know that the left-hand side of the equation shows more disorder compared with the right, so we'd expect the entropy change to be negative. Here, just to point out that entropy values are always positive. The entropy change will be positive or negative based on the disorder of the reactants and products. Why are we so interested in entropy? It's because it enables us to determine whether a reaction is feasible. That means whether the reaction will happen spontaneously. Other factors which have an important role to play include temperature and enthalpy change. You tend to find that most spontaneous, most feasible reactions are exothermic, have a negative delta H, although some endothermic reactions do occur spontaneously. It just occurs less than exothermic reactions. We can explain this by combining both enthalpy and entropy in a quantity known as Gibbs free energy. Delta G. So our equation for delta G, Gibbs free energy, is enthalpy change minus temperature multiplied by entropy change. Our units here, kJ per mole for Gibbs free energy. Enthalpy is kJ per mole. Temperature's in Kelvin. Entropy change we just covered. Keep an eye on your units here. You'll probably have to do some converting to get those joules there into kilojoules. Just to point out a few things, if delta G is positive, the reaction is not spontaneous. If Gibbs free energy is negative, then the reaction is spontaneous. And then the point at which a reaction just becomes spontaneous is when Gibbs free energy is 0. So in this example, we're using the data in the table to determine whether the following reaction is feasible at 298 Kelvin. So Gibbs free energy equals delta H minus temperature multiplied by entropy change. First step is to find delta S, so entropy change for the reaction. So use the equation. Let's look at the products. 82.8 plus half of 117 minus 130. That gives us an entropy change of 11.3. Just be careful, we want that in kilojoules, so divide by 1,000. That means we can now use the Gibbs free energy equation. Delta H, we're told in the question, is 337 minus the temperature, which was 298 Kelvin, multiplied by that entropy change we just calculated, to give us Gibbs free energy of plus 334. Because it's positive, it means that the reaction is not spontaneous, it's not feasible. Slightly different question now. Here's our equation. We've been told the entropy change and we're using the information to calculate the lowest temperature at which this reaction becomes feasible. Remember, that means that when delta G equals 0, so we'll write that equation again. So we know that the reaction becomes feasible when Gibbs free energy equals 0, so pop that in first of all. Then rearrange your formula to make T the subject of the formula, so add to both sides. And then divide both sides by delta S. Now substituting the values from the question, we know the enthalpy change is 492.7 kJ. Your entropy change, we were told, is 542.6. That needs dividing by 1,000 to get it into kJ. So that's what I've done there. Put it into your calculator and you'll get a temperature of 908 Kelvin as your final answer. So let's combine everything we've just learned in this question. Use the data in the table to determine if the reaction is feasible at 2,500 Kelvin. Find the lowest temperature at which the following reaction becomes feasible. So the first thing you want to do is find delta H. You're going to use your equation that you first came across in Hess's cycle, which is the enthalpy change of the products minus the enthalpy change of the reactants. So use the table. We're looking at this specific row. So we've got 4 lots of aluminium plus 3 lots of carbon dioxide minus 2 times minus 1669 plus 3 times 0 to give us an enthalpy change of plus 2156 kJ per mole. Now we need to find delta S. So what we've been doing this whole time. Let's look along this row now. 4 times 28 plus 3 times 214 minus 2 times 51 plus 3 times 6. Do include those brackets to get plus 634 jk to the minus 1 mole to the minus 1. Remember, we need that in terms of kilojoules, so divide by 1,000 right now to get that in the correct unit. So to find Gibbs free energy, delta H we just found 2156 minus the temperature, which we were told was 2500 Kelvin, multiplied by entropy change of 0.634. That gives us a Gibbs free energy of plus 571 kJ mole to the minus 1. Because that Gibbs free energy is positive, we know that the reaction is not feasible. Let's do this part of the question now. We need to find the temperature at which the reaction becomes feasible. So remember, that's when delta G equals 0. So I'll sub that in here. We rearrange to make T the subject of the formula. Delta H we already found. Delta S was 0.634. So actually the temperature we need to make this reaction feasible is 3,400 Kelvin. The oxides nitrogen monoxide and nitrogen dioxide both contribute to atmospheric pollution. The table gives some data for these oxides and for oxygen. Nitrogen monoxide is formed in internal combustion engines. When nitrogen monoxide comes into contact with air, it reacts with oxygen to form nitrogen dioxide. Calculate the enthalpy change for this reaction. I'm just going to write, it's not super official, but just so you can see what I'm doing. So delta H, let's look along this column. So it's NO2, so that's 34 minus 90 plus half of 0 equals minus 56 kJ per mole. Calculate the entropy change for this reaction. So remember, that's delta S. So different column this time. So we're doing the products. So that was 240 minus NO's value, which was 205 plus a half of 211. That's minus 70. I'm just going to divide it by 1,000 because I'm pretty sure what's coming up next will need me to mess around a little bit with the units. So that becomes kJ, k to the minus 1, moles to the minus 1. Calculate the temperature below which reaction is spontaneous. So delta G we know has to equal 0. Delta G equals delta H minus temperature multiplied by entropy change. So 0 equals delta H minus T entropy change. Rearrange to make T the subject of the formula. Delta H we just found was minus 56. Delta S is minus 0.0705 to get 794 Kelvin. Suggest one reason why nitrogen dioxide is not formed by this reaction in an internal combustion engine. So we've just found out that temperatures below 794 Kelvin mean that this reaction is spontaneous. So why isn't nitrogen dioxide formed? Because the temperatures must exceed 794 Kelvin. One final thing to look at is how we interpret a graph of Gibbs free energy against temperature in Kelvin. So Gibbs free energy is on our y-axis, temperature in Kelvin is on our x-axis. You must bear this in mind, y equals mx plus c. When we look at this graph, remember this is the equation for a straight line. So starting over here with the y-intercept. Now the y-intercept equals the enthalpy change, delta H, and I'm going to explain that now. First of all, you can see here that our temperature by definition is 0. So if we take our Gibbs free energy equation, we substitute in our temperature as being 0, because when you multiply something by 0, the thing disappears. You end up at this situation where Gibbs free energy equals the enthalpy change. And therefore that explains that at this point, the enthalpy change is 150, which is the same as Gibbs free energy. Now we'll take this portion of the graph, the x-intercept. You can see here that T equals 800 Kelvin. And this is the temperature for which the reaction becomes feasible, because remember, a reaction becomes feasible when delta G, Gibbs free energy, equals 0, which is what we find here on the y-axis. So this is where the reaction becomes feasible. Now let's consider the gradient m, which remember is change in y over change in x. The gradient is equal to minus the entropy change. In order to understand why, let's take that equation for a straight line graph. We already labelled the y-axis as being delta G, the x as being the temperature in Kelvin. We know that the y-intercept is the enthalpy change delta H. So if we substitute those into the y equals mx plus c equation, I've just rearranged that equation a little bit to make it slightly more straightforward to see the following. Remember, Gibbs free energy is given by this equation, enthalpy change minus temperature multiplied by entropy change. So if we substitute in our values, if I literally just lift this up and put it here, you can straight away see, therefore, that the gradient m is the same as, just reverse those signs, is the same as minus delta S. So the gradient of the graph equals minus the entropy change. So if I zoom out, we can see that the y-intercept on these graphs is the enthalpy change. The x-intercept is where the reaction becomes feasible. Just to take this step a little bit further, remember, for a reaction to be feasible, delta G must be negative, which means that all these temperatures down here are temperatures at which the reaction is feasible. And then lastly, the gradient is the same as minus the entropy change. The rate equation and orders of reaction. So remember, for a general reaction, you'll find that reactant A reacts with reactant B to form our products. However, if we were to write this as a rate equation, you'd write that rate equals K, the concentration of reactant A. This is your order with respect to A. I will explain this very shortly. Here's your concentration of reactant B raised to the order of reaction with respect to B. So let me label this. So rate is the most simple thing to explain. It's the rate of reaction. Here are your units for the rate of reaction. K is your rate constant, and you'll need to determine those units. This is your concentration of reactant A with your usual concentration units. Here's your concentration of reactant B. Again, your usual concentration units. And then probably what you're less familiar with are these superscripts. The M is the order of the reaction with respect to A. And the N is the order of the reaction with respect to B. So make sure you have all of that copied down. So what do we mean by the order of reaction? Well, it's the effect that varying the concentration of each reactant has on the rate. This is what we call the order of reaction. And at your stage, there'll be 3 orders of reaction you need to be aware of. 0 order, first order, and second order. If we have a 0 order, with respect to A, you'll see a 0 as the superscript. First order, you'll have a 1. Second order, you'll have a 2. So let's take this in slightly more detail. So starting with that 0 order, what this really implies is that the concentration of the reactant, in this case A, has no effect on the rate. And we can explain this using maths because remember, any number raised to the power of 0 automatically equals 1, and this means that these reactants do not appear in the rate equation because the concentration of the reactant has no effect on the rate. Just to show you from a maths point of view, 3 to the 0 equals 1, 5 to the 0 equals 1. So these reactants don't appear in the rate equation. Let's take the first order now. What this implies is that the rate is directly proportional to the concentration of the reactant. So what that means is that if the concentration of A is doubled, the rate doubles. But what about second order? This means that any change in the concentration changes the rate by the square of the change. So this is the most difficult one. So if the concentration of A is doubled, the rate increases by a factor of 4. If the concentration of A is tripled, the rate increases by a factor of 9. The overall order of reaction now. This is the sum of all the individual orders with respect to each reactant. So for example here, the reaction is first order with respect to A, second order with respect to B. If we add up these individual orders, it gives us an overall order of reaction of 3. Just one thing to be aware of is that the order of reaction is determined experimentally. We don't use stoichiometry in order to determine it. I'm now going to show you how to determine the units of the rate constant. This will need to be calculated for each rate equation. So we'll take an example. Just be aware of the overall order of reaction is 3, 2 plus 1 is 3. So the first step is to rearrange the formula to make K the subject of the formula. So K equals rate divided by the concentration of X raised to the power of 2 multiplied by the concentration of Y. Substituting the units I gave you at the start of this video. There's our rate units. Concentration now. So we need to cancel out our common units. Let's just multiply out that bracket and then get it all on top. And then just rearrange that a little bit to make it slightly nicer. So that's how I've determined the units of the rate constant. I wrote the rate equation. I rearranged to make K the subject of the formula. I substituted in my known units. Here's a diagram I've taken from my revision guide available at swhlearning.co.uk. So sometimes they want you to work out the order of reaction from the rate concentration graphs. If you get a straight horizontal line, it means that the order is 0 with respect to A because the rate is unchanged with changing concentrations of reactant A, which is what I taught you earlier in this video. The straight line, remember, represents a directly proportional relationship, one that passes through the origin. That means that the reaction is first ordered with respect to A because rate is directly proportional to the concentration of A. And then lastly, a curved line that goes through the origin means that the reaction has an order greater than 1 with respect to A. Now, the value of the rate constant depends on temperature. So increasing the temperature increases the value of K, and therefore the faster the rate, which makes sense, you've increased the temperature after all. And why is this? Well, a small increase in temperature means many more molecules have an energy greater than or equal to the activation energy, which remember we looked at when we considered the Maxwell-Boltzmann distribution. Propanone and iodine react in acidic conditions according to the following equation. The student studied the kinetics of this reaction using hydrochloric acid and propanone and iodine. From the results, the following rate equation was deduced. Give the overall order for this reaction. So there's a 1 there and a 1 there. We add up those superscripts to get 2, so it's second order. When the initial concentrations of the reactants were shown in the table below, the initial rate of reaction was found to be this. Use these data to calculate a value for the rate constant K for the reaction and give its units. So write out the equation from above. So we know that the initial rate of reaction was 1.24 times 10 to the minus 4, so we sub that in. We're after the rate constant K, then pop in the concentrations of propanone and hydrogen ions. Rearrange to find K, so that's 3.44 times 10 to the minus 5. In terms of the units, just substitute in the other units. Cancel out, so it becomes moles to the minus 1, dm plus 3, s to the minus 1. Deduce how the initial rate of reaction changes when the concentration of iodine is doubled, but the concentrations of propanone and of hydrochloric acid are unchanged. So if you look at the rate equation, iodine doesn't feature here, which means that the order of the reaction with respect to iodine must be 0, so changing the concentration of iodine has no effect on the initial rate of reaction. If the concentrations of propanone and hydrochloric acid are unchanged, because the order with respect to each of these reactants is +1, it means it's directly proportional, so overall the initial rate of reaction is unchanged. The rate of the reaction between substance A and B was studied in a series of experiments carried out at the same temperature. In each experiment, the initial rate was measured using different concentrations of A and B. These results were used to deduce the order of reaction with respect to A and the order of reaction with respect to B. What is meant by the term order of reaction with respect to A? In the simplest terms, this is the power of the concentration term in a rate equation. When the concentrations of A and B were both doubled, the initial rate increased by a factor of 4. Deduce the overall order of the reaction. So this is key. It says that they were doubled and that the initial rate increased by a factor of 4. So that tells us that the order with respect to each is 1. It means it's directly proportional. So the overall order, we do the 2 powers added together, so it's second order. In another experiment, the concentration of A was increased by a factor of 3 and the concentration of B was halved. This caused the initial rate to increase by a factor of 9. It's a bit of puzzling here, but the fact that the concentration of A was increased by a factor of 3 and the overall initial rate increased by a factor of 9 indicates that A is second order, but that B must be 0 order. So what happens here is that 0 order effectively means that the concentration of B has no effect on the overall rate. The fact that A was increased by a factor of 3 and led to the initial rate increasing by a factor of 9 stands to reason that A is second order. Using your answers from part C, 1, write a rate equation for the reaction and suggest suitable units for the rate constant. So its rate equals the rate constant We know that A is second order. Because B is zero order, it doesn't feature. Now let's sort out the units. So rewrite that rate equation, making the rate constant the subject of the formula. Sub in your units. So there's your units. The Arrhenius equation is used to link the fraction of molecules with energy greater than the activation energy with the rate constant. Okay, it looks pretty disgusting. I'm going to take each of these components in turn and explain them to you. So remember K we've met before, that's the rate constant, whose units we'll have to determine separately. EA up here is your activation energy. T is your temperature in Kelvin. R you met at the ideal gas equation, it's your gas constant, which has a value of 8.31. Now this E here is an exponential, which is just a maths term, which means the A here, because it occurs before your exponential, it's your pre-exponential factor. Which has the same units as your rate constant. Don't worry if maths isn't your strong point and you're feeling a bit freaked out by all of this. I'm just going to give you a simple list of steps you can follow, which will help make sure you know what you're doing in the exam. Now, we're trying to plot a graph fundamentally here. In order to do that, we need to get this Arrhenius equation into the format of a straight line, which is y equals mx plus c. Bear that in mind. So the way in which we go about that is by taking natural logs. And the reason you take natural logs is it allows you to remove that exponential. So if I take a natural log here, it will remove my exponential, but I need to make sure I take a natural log of everything in your equation. So this is why I'm allowed to write this, because I've taken a natural log of it. And I must remember to take a natural log of my pre-exponential factor also. So that's what's happened here. I've taken a natural log here, and by taking a natural log here, I've removed my exponential. If you're not comfortable with exponentials and natural logs, don't worry. Just make sure you can find these buttons on your calculator, and do make sure you learn these equations off by heart. Now let's get this into the format of y equals mx plus c. Just put that here. That's your equation of a straight line. So we've got your natural log of k, the rate constant. We're just going to separate our fraction here in order to give us an equivalent of m, the gradient, and x. So just take a step back, look. What I've written here is exactly the same as this. I've just separated out the r and the t in effect, keeping our natural log of that pre-exponential factor. So just to really show you what we've done here, we've taken that Arrhenius equation, and by taking natural logs, we now have it in the format which lines up with our y equals mx plus c. So now we're ready to draw a graph. So our natural log of the rate constant goes on the y-axis. We can see here that our x is 1 over t, so that forms our x-axis. I'm just going to add the units here, which is obviously temperatures in Kelvin. It's 1 over temperature, so that's why it's k to the minus 1. The y-intercept, which remember is given by c, is the natural log of our pre-exponential factor. Okay, for argument's sake, I've just got a line plotted on here. I'm now going to show you what we can work out from said line. So remember, c is our y-intercept. We know it must be the natural log of a, so that's here. The gradient now, m, is this term here. It's our activation energy divided by the gas constant. So it's therefore a pretty straightforward step in order to calculate the activation energy, because we know that R is always 8.31. So when there are actual numbers on these scales, you can work out your gradient, sub in your 8.31 as your R value, and that will enable you to calculate your activation energy. Just make sure you're mindful of units. I will show you an example now. So let's put into practice what we've just learnt. So use the Arrhenius equation in the graph below of natural log of K against 1 over temperature for the reaction shown to calculate the activation energy in kJ per mole for the reaction. So remember, the activation energy we pull out by looking at the gradient. So gradient M is given by change in Y over change in X. So my change in Y is going to be here. My change in X will be along here. Just read carefully down these scales and you can see our change in Y is minus 14.1 minus 2.8 divided by our change in X, which is 0.0018 minus 0.00128 to give us a gradient of minus 21,731. Let's take the Arrhenius equation in the format of y equals mx plus c, which remember is the natural log of the rate constant. So remember I said you needed to learn this equation. There's our y, our m, our x and our c. Remember that we said that the gradient is our activation energy divided by our gas constant R. We've just calculated the gradient. We know that R, the gas constant, equals 8.31, so just cross multiply and then get rid of your minus signs to get an answer which is 180,583 joules per mole. Final step is to get that into kJ by dividing by 1,000. So just to remind you, what did we do? We wrote out our Arrhenius equation in the form of y equals mx plus c. We pulled out the fact that the gradient is equal to minus the activation energy divided by the gas constant. We found the gradient using the graph. We substituted in our values, remembering that the gas constant equals 8.31. And then we finally did a unit conversion to get a final answer of 181. Right, the second part of the question, a reaction has a rate constant of this value at this temperature. Use the equation to calculate a value for the activation energy. That pre-exponential factor A equals this and the gas constant is this. So I've written out this equation. I've just popped RT down there so I can see it more clearly. Let's rearrange to make activation energy the subject of the formula. So we need to multiply everything by RT. I'm going to add the activation energy to both sides. And then just take away that natural log of the rate constant multiplied by R multiplied by the temperature. And then look, let's take RT out as a common factor. Let's substitute in our values. R, remember, the gas constant is 8.31. The temperature we've told is 356 Kelvin. We'll do a natural log of A minus natural log of the rate constant. So our final answer here is 86,094 joules per mole. Let's get that into kJ by dividing by 1,000. To recap, we take the equation in the form that they've given us. Then we rearrange the formula to make the activation energy the subject of the formula. We take out the common factor of RT and then we substitute the values in from the question, remembering to convert to kilojoules at the very end. A slow reaction has a rate constant at 300 Kelvin. Use the Arrhenius equation to calculate a value in kJ per mole for the activation energy of this reaction. So we're looking for EA. We've been told that A equals this and R equals this. So let's write down the equation. We need to make the activation energy the subject of the equation. So multiply everything by RT. Add EA to both sides. Take out a factor of RT. And then substitute in your values. R equals 8.31. The temperature we were told is 300 Kelvin. A is 2.57 times 10 to the 10. The rate constant was 6.51 times 10 to the minus 3. Put that into your calculator. That's in joules per mole. So just divide by 1,000 to get it in the appropriate unit. A second series of experiments was carried out to investigate how the rate of the reaction varies with temperature. The results were used to obtain a value for the activation energy. Identical amounts of reagents were mixed at different temperatures. The time taken for a fixed amount of bromine to be formed was measured at different temperatures. Complete table 3. So here we're being asked to find the natural log of 1 divided by T. So press the natural log button on your calculator and then do 1 divided by 27 to get minus 3.30 to 3 significant figures. And then to fill in this row, all you have to do is 1 divided by temperature, so 1 divided by 302, which is 3.31 times 10 to the minus 3. The Arrhenius equation can be written as, in this experiment, the rate constant K is directly proportional to 1 over T. Therefore, you can write it as this, where C1 and C2 are constants. Use values from table 3 to plot a graph of natural log 1 over T on the y-axis against 1 over T on the grid. Use your graph to calculate a value for the activation energy, and the value of the gas constant is 8.31. So they've already told us what's going on the y-axis. It's the natural log of 1 over T, so that's what we have here. It means that we are looking at this particular column here for our scale. So as you can see, it goes sensibly down from -2 to -4, and then 1 over T we've already been given in this particular question along with the scale. Then we're going to plot a graph. I've done that too. We're plotting on the y-axis minus 3.99 against 3.5 times 10 to the minus 3. So that's that point right here, and so on and so forth. And now the hardest bit is to find the activation energy. First thing, remember that this equation here is in the format y equals mx plus c. So we can see, therefore, that the gradient is minus activation energy over R. So let's write that down here. So let's work out the gradient of this line, which remember is change in y over change in x. So I'm going to create a triangle right here for you to just see what I'm doing. So that's my change in y, that's my change in x. So my change in y is minus 4.0 minus 2.0. Read off your x values carefully using your x scale. So you can see that's 3.50 times 10 to the minus 3 minus 3.20 times 10 to the minus 3 equals minus 2 over 3.0 times 10 to the minus 4, which equals minus 6667 as your gradient. So substitute that in. We know that the gas constant is 8.31. Multiply both sides by 8.31 and then take out the minus sign to get an activation energy, 55,400 joules per mole, and then finally divide by 1,000 to get it in kJ per mole to get 55.4. Let's move on to determining the rate equation. So the way in which we can do this is by carrying out a series of experiments, and we call the experiment type that we carry out the initial rate method, and that's a series of experiments carried out at a constant temperature. Now what you find is that each experiment starts with a different combination of initial concentrations of reactants, and then as we move through the experiments, we change only one concentration of the reactants. And then as that experiment continues, the concentration change of one reactant is monitored so that we can then plot a concentration time graph. It's important that we can determine the initial rate, and the way in which we do that is finding the gradient when t equals 0. So when time is 0, we can draw a tangent, which then enables us to find the initial rate when t equals 0. Why do we use the initial rate? Because the concentrations of all substances in the reaction mixture are known exactly at this time. And then by comparing the initial concentrations and the initial rates for pairs of experiments, this allows us to determine the order with respect to each reactant. So this is just an introduction. I'm going to go through this step by step to clear up any uncertainties you have. Just be aware that it's very common for an exam question to ask why the order of reaction with respect to one of the reactants can be ignored. Why is that? It's because invariably the concentration of that reactant is much larger than the others, so in effect its concentration is almost constant. But as I said, the most straightforward thing here is if we actually look at an example. So in this particular example, we're being asked to determine the initial concentration of reactants. The results of an investigation of the reaction between X and Y are shown in the table below. The rate equation is rate equals rate constant multiplied by the concentration of reactant X and the concentration of reactant Y. We can see that reactant X is first order, reactant Y is second order. So what is the initial concentration of Y in experiment 2? So we're looking for this value here. So the way in which we're going to do that is take experiment 1, after all, we've been given the concentrations, we'll substitute in their values. We know the initial rate, so obviously that gives us enough information to calculate K, and then we can reuse this equation with our known number for K in order to find out the initial concentration of Y. So this is fairly straightforward. So our value for K is this. Remember, you need to work out the units for K every time. So substitute in the units given in the table. So therefore we can see that the unit is mol to the -2, dm to the +6, s to the -1. So rewrite your rate equation in order to find out that unknown concentration of reactant Y in experiment 2. We know the rate from the table is 0.8. K we've just calculated as being 8. X is 0.6. So multiply that out. 8 times 0.6 is 4.8 times Y squared. And then finally square root to find Y. So our final answer is 0.408. The units for concentration are nice and straightforward. Now we're being asked to determine the rate equation from experimental data. So the data in the table below were obtained in a series of experiments on the rate of the reaction between compounds A, B and C at constant temperature. Use the data to deduce the rate equation for the reaction between A, B and C. Give the overall order of the reaction and the units of the rate constant. So obviously in order to find the rate equation, we're going to have to find the order with respect to each reactant. So that would be A, B and C. So the easiest way to do that is to compare two experiments where only that reactant is being changed. So if we compare experiment 1 and 2, we can see that B and C are unchanged, but the concentration of A has halved. So let's just make a note so you can see what I'm doing. I'm comparing experiment 1 and 2. I'm just making a note that the concentration of B and C are constant. The concentration of A has halved. And have a look at the rate. That's also halved. So immediately we can conclude that the reaction is first order with respect to A. So as you can see here, when the reaction is first order with respect to a particular reactant, it means that when you double concentration, the rate is doubled. If you halve it, the rate is halved, as we see here. Okay, moving forwards, comparing experiments 2 and 3, the initial concentration of A has remained the same for C. This time the concentration of B has tripled, but the initial rate has increased by a factor of 9, which means that the reaction is second order with respect to B. Okay, time to sort out reactant C. So here the concentrations of A and B remain the same. Here the concentration of C has doubled. The initial rate has remained unchanged. That therefore tells us that the reaction is zero order with respect to C, Why? Because changing the concentration has had no effect on the rate. So we've done all the hard work. We're ready to assemble our rate equation. So remember, it's rate equals the rate constant K multiplied by the concentration of A, which we know is first order, the concentration of reactant B, which we know is second order, and then because the reaction is zero order with respect to C, it doesn't feature in the rate equation. So we've done the rate equation. The next thing we need to do is find the overall order of the reaction. So we just add up these superscripts. It's 1 plus 2, which means it's 3. So the reaction is third order. And then finally, to deduce the units, let's take our rate equation, rearrange to make K, the rate constant, the subject of the formula. Pop in your units. Cancel down. So we get mole to the minus 2, dm to the plus 6, s to the minus 1 is the unit of our rate constant. So just have a look at what I did in order to find the rate equation. I compared experiments where only one of the reactants' concentrations changed. I looked at what happened to the initial rate based on that change in concentration. That allowed me to work out the order with respect to each reactant. Therefore, I could write my rate equation because its rate equals the rate constant multiplied by the concentration of reactants A and B in this case, raised to their order. To work out the total overall order of the reaction, I just added up the superscripts to find out that it was third order. And then lastly, to find the units of the rate constant, I rearranged the subject of the formula to make K the subject, and then I substituted in the known units. Let's do a more difficult example now. So determining the rate equation from more complicated experimental data. The data in the table below were obtained in a series of experiments on the rate of the reaction between compounds A and B at constant temperature. Use the data to deduce the rate equation for the reaction between A and B. Right, okay. So here between experiments 1 and 2, we can say that the initial concentration of B has remained the same. The initial concentration of A has tripled. So we can see that here, between experiment 1 and experiment 2, the initial rate has increased 9 times. So that tells us straight away that the order of reaction with respect to A is 2. Feel free to write it all out like I did in my previous example if you're not entirely happy. What about if we consider B now? So this is annoying because the concentrations have changed for both. So you have to work it out. Look, here, from 2 to 3, the concentration of A has doubled. So therefore, you would expect the rate to be times 4 because we know that the order of reaction with respect to A is 2. So let's work out what effect that should have had here on 1.89 times 10 to the minus 3. Let's just multiply that by 4 to predict what that rate there should have been, which is 7.56 times 10 to the minus 3. Obviously, that's not the initial rate, so that we know the order of reaction with respect to B can't be 0, because after all, changing the concentration has affected the rate. But let's look more closely what's happened here. We've halved the concentration of B. And then look, the expected rate has also been halved, so we can say that the rate is halved, which automatically tells us that the order of reaction with respect to B is 1. So we've done all the hard work. Let's write our rate equation. Rate equals the rate constant, concentration of A, we know that it's second order, concentration of B, we know that it's first order, so that means that's my rate equation. Okay, and then just to mention one of the required practicals, which is measuring the rate of reaction by a continuous monitoring method. So concentration time graphs can be plotted by taking continuous measurements during the course of a reaction. This is known as continuous monitoring. It can be done by using a colorimeter in order to monitor the color change. We could do it by monitoring the change of mass using a balance. We could collect any gaseous products using a gas syringe, and we could monitor any change in pH. If you're using the colorimetry method, you need to prepare standard solutions of known concentrations of the colored reactant. You want to use distilled water in order to zero the colorimeter. You measure the absorbance readings of the standard solutions, and you plot a calibration curve of absorbance versus concentration. And the reason you do that is it allows you to convert the absorbance readings into concentrations of the reactants. Then you measure known volumes of each of the reactants into separate containers. You start a timer at the point of mixing, and you take a series of colorimeter meetings at regular time intervals. You then use the calibration curve to measure the concentration of the colored reactant at each absorbance reading, and you plot a second graph of concentration of the reactant against time, and therefore using that concentration time graph, you can determine the order of the reaction with respect to the colored chemical. Now, the titration method is the method you'll use if, instead of using colorimetry, capturing gas in a gas syringe, looking at changes in mass, that's the method you'll use to monitor the change in pH. This time you're measuring known concentrations of each of the reactants into separate containers. You start a timer at the point of mixing. You remove samples of the reaction mixture at timed intervals. Stop the reaction in the sample by diluting or cooling it. This is to prevent the reaction continuing in each sample taken. You titrate the sample with alkali to determine the concentration of H+ ions, and then finally you plot a graph of concentration of H+ ions against time. Once you've plotted your concentration time graphs, you'll be able to determine the order of reaction. If you have a zero order reaction, it's going to produce a straight line with a negative gradient. And that's because, remember, with a zero order reaction, the reaction rate does not change with changing concentration of reactant. With a first order reaction, you get a downward curve with a decreasing gradient. Make sure you can recognize these curves. And that's because as the concentration of the reactant decreases, obviously the rate decreases. If you determine the gradient of these graphs, it will tell you the rate of the reaction at that particular point in time. Now, in reality, most reactions take place in more than one step, and the slowest step of this multi-step mechanism is known as the rate determining step, and only species involved in or before the rate determining step will appear in the rate equation. So, using the order of a reaction to find the rate determining step, the rate equation for a reaction was determined to be rate equals the rate constant multiplied by the concentration of NO, which is second order, with respect to NO, and then multiplied by the concentration of H2, which is first order. The following three-step mechanism for the reaction was suggested. P and Q are intermediate species. So, in order to determine the rate determining step, let's have a look at the rate equation, and then we're going to cross off each of the species as you meet them in the mechanism steps. So, that means we're going to cross out NO. The H2 appears in the second step, and now because we've crossed everything out, it tells us that step 2 must be the rate determining step. Okay, let's take another example now. Example 2, the compound this reacts with aqueous sodium hydroxide as shown in the following equation. This reaction was found to be first order with respect to the CH3,3-CBr, zero order with respect to the hydroxide ions. The following two-step process was suggested, deduce the rate determining step. So let's first of all write out the rate equation. So we know its rate equals the rate constant. We know that it's first order with respect to CH3CBr, and then zero order with respect to the hydroxide ions, so we're not going to feature them there. So let's start working through. When do we meet these various species in the steps? So we know straight away that we can cross out this one here. Now nothing else features, so therefore that tells us straight away that it must be step 1 because that's the only place we've crossed out a species. Step 1 is the rate determining step. This question is about rates of reaction. Phosphonate ions react with hydroxide ions to produce hydrogen gas. A student completed an experiment to determine the initial rate of this reaction. The student used a solution containing phosphonate ions and measured the volume of hydrogen gas collected every 20 seconds at a constant temperature. Figure 1 shows a graph of the student's results. Use the graph in Figure 1 to determine the initial rate of reaction for this experiment, state its units, and show you're working on the graph. So we need to start by drawing a tangent. So I've drawn my tangent, so I've shown my working on the graph here. Let's find that gradient. So I think the neatest thing for me to do is my change in y here over my change in x here. So you can see that's 125 divided by 20 to get 6.25. What are our units? So let's just sub in the units from the graph. So that means the answer is 6.25 centimeters cubed per second. Another student reacted different initial concentrations of phosphonate ions with an excess of hydroxide ions. The student measured the time taken to collect 15 centimeters cubed of hydrogen gas. Each experiment was carried out at the same temperature. The table shows the results. State the relationship between the initial concentration of phosphonate and the time. Deduce the order of the reaction with respect to phosphonate. You can see here that as the concentration is doubled from 0.25 to 0.5, the time has quartered. So what does that mean? That obviously means that the order is second order with respect to the phosphonate ions. Complete the diagram in Figure 2 to show how the hydrogen gas could be collected and measured. So we need to have our reaction mixture down here. Now we need a gas syringe to collect that gas. I'm so sorry, my drawing is just horrible. Here's our conical flask. There's our bung. Deduce the overall effect on the rate of reaction when the concentrations of both L and M are halved. So we know that the reaction is first order with respect to L, second order with respect to M. So obviously the fact that the concentrations have been halved means that by halving the concentration of L, yes, that will halve the reaction, but because the reaction is second order with respect to M, when you halve the concentration of M, you effectively quarter it, and then because we're combining both of these, we multiply them. So to write that, the rate is multiplied by 1/8. So the rate of reaction is this. When the concentration of L is this, calculate the concentration of M if the rate constant is this. So slightly more straightforward question. I've pulled down the rate equation. We know the rate constant is 21.3 times the concentration of L times the concentration of M. So that's what we're after. Square root it. And then lastly, define the term overall order of reaction. It's the sum of the powers to which the concentrations are raised in the rate equation. Another A2 topic now, the equilibrium constant Kp for homogeneous systems. So starting with our definition of partial pressure, this is the contribution of a gas to the total pressure of all gases in the mixture. And it's given by the equation, which is how you'll most commonly come across it in your exam. The partial pressure of, for example, gas A is given by the mole fraction of A, to be discussed very shortly, multiplied by the total pressure of the system. So what is the mole fraction? It's the number of moles that a gas contributes to the total number of moles in the mixture. And again, it's more useful to see this as an equation, so we're taking the mole fraction of gas A again. It's the number of moles of gas A in the mixture divided by the total number of moles of gas in the mixture. So how do we deduce the expression in the units of Kp, which remember is our equilibrium constant? Here is your general equation for a reaction containing gases that has reached a dynamic equilibrium, one where there's a reversible reaction taking place. To write the expression for Kp now, we write Kp, so the equilibrium constant is the partial pressure of gas C multiplied by the partial pressure of gas D divided by the partial pressure of gas A multiplied by the partial pressure of gas B. So that is your very important expression for Kp. Be careful not to use square brackets here. Remember, square brackets represent concentration. So in general, we can see that Kp is the partial pressure of the products divided by the partial pressure of reactants as taken from this general equation. So let's substitute in some actual substances so you can see this more clearly. So in this first example, we're taking sulfur dioxide, which is reacting with oxygen in a reversible reaction to form sulfur trioxide. So writing our expression for Kp, it's very straightforward. We're going to take the partial pressure of our products. So that's the sulfur trioxide. Don't forget to raise it to the power based on this stoichiometry. So there's that 2 there, which we acknowledge there. Divided by the partial pressure of our reactants, raised to its power, multiplied by the partial pressure of the second reactant, which is oxygen. So that's now done. In terms of working out the units of Kp, you want to substitute in the unit for pressure, which is usually kPa. It may also occasionally be atmospheres, so ATM. So if I sub in kPa here, these cancel out. So it becomes kPa to the -1. We're moving on now to calculating mole fractions. Whilst carrying out the Haber process, an equilibrium mixture at 400 degrees Celsius contains 18 moles of nitrogen gas, 54 moles of hydrogen gas, 48 moles of ammonia. Give the mole fractions of each of these gases. So I've stolen my equation for calculating the mole fraction from above. So we're going to start with the mole fraction of nitrogen. So we know it's the number of moles, so it's 18, divided by the total number of moles. Let's add them up. It's 18 plus 54 plus 48, which equals 120 moles. So we just do 18 divided by 120. The mole fraction of hydrogen is just 54 over 120. And then the mole fraction of ammonia is 48 over 120. And actually it's fine to leave them as fractions without simplifying because they're then usually used to find partial pressure measures. It's also fine to use decimals. Now we're going to calculate the value of Kp, the equilibrium constant. So 1 mole of carbon dioxide, 3 moles of hydrogen was sealed in a container. After the mixture had reached equilibrium at a pressure of 500 kPa, the yield of methanol was 0.86 moles. Calculate a value in the units of Kp to an appropriate number of significant figures. What we need to do is combine what we learned at AS level with what we learned at A2, because really our first step is to find the equilibrium amount of everything. So find equilibrium amounts, and I taught you that you need to use a Rice table to do that. It's really straightforward. There's rice. Now, the R in rice stands for the reaction, so that means copying down the equation they've given you. Okay, now pop into the table the information also provided in the question. So I stands for the initial number of moles. So we can see that we started with 1 mole of carbon dioxide, 3 moles of hydrogen. It says it here. Then we know that at equilibrium, the yield of methanol was 0.86 moles. So I'm going to pop that here. Because at the start of the reaction, obviously, we have no product. We're going to put 0 here. So therefore, we can work out the change in moles. That's what the C here stands for. So we can see straight away that it's plus 0.86. So let's use the stoichiometry to work out the other changes in moles. So again, 0.86. Over here for carbon dioxide, obviously we'll have less of our reactants at equilibrium. So I'm going to say minus 0.86. So 1 minus 0.86 is 0.14. Just be a little bit careful here. We've got a 3 here. That indicates we need to multiply this number by 3 to get minus 2.58. So simply take away 2.58 from the 3 to get 0.42. So that's how we find our equilibrium moles. So I'm hoping you can see that we can now find out our mole fractions. So starting with the mole fraction of carbon dioxide, and actually you use this in order to represent that you're finding the mole fraction. Don't worry, you just find your equilibrium number of moles for carbon dioxide and then divide it by the total number of moles. So that's 0.14 plus 0.42 plus 0.86 times 2, which comes to 2.28. So there's our mole fraction of carbon dioxide. What about our mole fraction of hydrogen? It's 0.42 over 2.28. The mole fraction of methanol, 0.86 over 2.28. And then what about our mole fraction of water? 0.86 over 2.28. Take a step back. So we found the mole fractions. Let's find the partial pressure. So starting with our partial pressure of carbon dioxide, I've just copied down the equation from before just so you can see how I'm doing it. So the partial pressure of carbon dioxide is the mole fraction of carbon dioxide multiplied by the total pressure. So we work that out. It's 0.14 is the mole fraction divided by 2.28 multiplied by the total pressure, which we found to be 500 kPa. So that's 30.7 kPa is the partial pressure of carbon dioxide. What about of hydrogen? So we take the mole fraction of hydrogen times by the total pressure of the system. Now the partial pressure of methanol. So it's mole fraction multiplied by that total pressure. And then lastly, the partial pressure of water. So its mole fraction will be the same as methanol. So we've worked out all the individual partial pressures. Now clearly you can see if you're going along the right lines, because if you add up these individual partial pressures, it should come up to your total pressure, which it does, 500 kPa. Now we're going to deduce an expression for Kp and find the units. So Kp we know is the partial pressure of the product, so that's methanol, multiplied by the partial pressure of the water, our second product, divided by the partial pressure of carbon dioxide, multiplied by the partial pressure of hydrogen. Check your balanced equation. We need to acknowledge the stoichiometry, so we need a 3 as a superscript for the hydrogen. So that's now done. That's our expression for Kp. Sub in our values that we just calculated. So that's 188.6 multiplied by 188.6 divided by 30.7 times by 92.1 cubed. So therefore Kp equals 1.48 times 10 to the minus 3. Let's work out units. So I'm just subbing in kPa. And then we need to work out an appropriate number of sig fig. Now, 2 significant figures is the lowest number of significant figures used in the question, which means that 1.5 must be our final answer. Right, to recap then, we used the Rice table to find the equilibrium number of moles for each of the reactants and products. This enabled us to calculate the mole fraction, which remember we did by finding the equilibrium moles and dividing it by the total number of moles for each of the reactants and products. Then we found the partial pressure by doing the mole fractions multiplied by the total pressure, making sure that we check that our individual partial pressures add up to the total pressure. Then we deduced an expression for Kp and then substituted in the values we found for partial pressure to find the value of Kp before subbing in the units to find the unit of Kp. Just a couple of things on how changing the conditions may affect the value of Kp. Now, the greater the value of Kp, the further to the right the position of equilibrium lies. And then if Kp equals 1, the equilibrium position is directly in the middle of the reactants and products. If it's much greater than 1, as I've just said, the equilibrium position is over to the right in favour of the products. If it's much less than 1, the equilibrium position is over to the left in favour of the reactants. Increasing or decreasing the temperature is the only change in condition that changes the value of Kp. So changing pressure has no effect on the value of Kp. Now, if the forward reaction is exothermic, increasing the temperature moves the equilibrium position to the left, so Kp decreases. If you decrease the temperature, it moves the equilibrium position to the right, so Kp increases. If the forwards reaction is endothermic, increasing the temperature moves the equilibrium position to the right, so Kp increases. Decreasing the temperature moves the equilibrium position to the left, so Kp decreases. You must remember with this endothermic, exothermic thing, this is all IGCSE and GCSE knowledge. Remember, exothermic reactions release heat energy, endothermic reactions take in heat energy. So do recap that if you're not sure why the following occurs. In the second stage, carbon monoxide and hydrogen react according to this equation. A 62.8 mole sample of carbon monoxide was added to 146 moles of hydrogen. When equilibrium was reached at a given temperature, the mixture contained 26.2 moles of methanol at a total pressure of this. Write an expression for the equilibrium constant Kp. Calculate a value for Kp at this temperature and give its units. 8 marks. Wow, that's worth a lot of marks. Okay, so we're going to start by finding our equilibrium moles by constructing a Rice table. So R stands for reaction, which means copying down the equation they've given us. So we know that the initial moles of carbon monoxide was 62.8. The initial moles of hydrogen was 146. At equilibrium, we know we have 26.2 moles of methanol. So remember, our initial moles of our products by definition must be 0. So the change in number of moles C is plus 26.2. Therefore, our change in moles of our reactants must be minus 26.2. So that's 36.6 moles of carbon monoxide at equilibrium. What about hydrogen? Double check the stoichiometry. We just need to multiply that number there by 2 to get 52.4. So minus 52.4 from 146 to get 93.6. So that's our equilibrium moles. Remember, we now need to find the mole fraction of each of these substances. So the mole fraction of carbon monoxide is the equilibrium moles divided by the total number of moles. So I'll just quickly add those 3 numbers up. So there's our mole fraction of carbon monoxide, mole fraction of hydrogen, our mole fraction of methanol, Time for our partial pressures. So partial pressure of carbon monoxide is the mole fraction multiplied by the total pressure, which was 9.5. Partial pressure now of hydrogen. Partial pressure of methanol. So the mole fraction times by the total pressure. And remember, those individual partial pressures should add up to 9.5, which was the total pressure of the system. Now let's write an expression for Kp. So our equilibrium constant, so it's our partial pressure of our products, which was methanol, divided by the partial pressure of our reactants. Double check the stoichiometry. It's 1 to 2. So we need that superscript there against the hydrogen representing the 2. Now we can sub in those partial pressures. So it becomes 1.59 divided by 2.22 multiplied by 5.69 squared. Then let's pop in our units, which were MPa. And that's how you get 8 marks. Now some MCQs. The equation for the reaction between sulfur dioxide and oxygen is shown. In an experiment, 2 moles of sulfur dioxide are mixed with 2 moles of oxygen. The total amount of the 3 gases at equilibrium is this. What is the mole fraction of sulfur trioxide in the equilibrium mixture? So it's quite a lot of work really for 1 mark. We're constructing a rice table. So we know the initial moles of sulfur dioxide are 2. We've got the initial moles of oxygen of 2. Now this question is completely disgusting because it only gives us the piece of information that the total amount of the 3 gases at equilibrium is 3.4 moles, whereas usually it tells you what one of the gases is, and then you can work backwards. So because of that, what you therefore have to work out is a bit of algebra, which means that to work out the change in moles here, you need to use the stoichiometry to realise that it's going to be minus 2x because we don't know what that x is. This one's going to be minus x because you've got an invisible 1 here, and this one's going to be plus 2x. So therefore equilibrium moles are going to be 2 minus 2x of the sulfur dioxide, 2 minus x of the oxygen, and 2x for the sulfur trioxide, and we know that together those equal 3.4. So solve for x. So we know that x equals 0.6, which means if we zoom in on the sulfur trioxide, that therefore that change is plus 1.2 to get 1.2 moles of sulfur trioxide. So to find the mole fraction, it's the number of moles of equilibrium divided by the total moles to get 0.353. Please don't stress if you're super struggling with that. It's insane and it's only worth 1 mark, so just don't worry about it. Move on in the exam. Nitrogen reacts with hydrogen in this exothermic reaction. Which change increases the equilibrium yield of ammonia but has no effect on the value of the equilibrium constant? So remember, Kp is affected only by temperature. We know therefore that changing the temperature changes the value of Kp. We want no effect, which is why we're crossing out this one. So now we go back to our IGCSE and GCSE knowledge. Adding a catalyst, remember, just increases the rate of the forward and reverse reactions equally, so it won't affect the yield of ammonia. Let's look at the number of moles of gas. We have 4 moles on the left-hand side, 2 moles on the right. So if we increase the partial pressure of the nitrogen, what that does is it shifts the position of equilibrium to the right, increasing the yield of ammonia, which is why B is the correct answer here. An equilibrium mixture is prepared in a container of fixed volume. The temperature of this mixture is decreased. The mixture is allowed to reach a new equilibrium, which is greater for the new equilibrium compared to the original equilibrium. Now notice this is an exothermic reaction, so if we decrease the temperature, we shift the position of the equilibrium to the right, and what that does is it increases the value of Kp, which is why D is the correct answer here. Which statement about Kp is correct for this reaction in the gas phase? I can see straight away that A is the correct answer because the value of Kp is independent of pressure. Remember, I told you that the value of Kp depends only on temperature, so therefore it is by definition independent of pressure. Which change would alter the value of the equilibrium constant? Again, it will be altering the temperature, so I'm going straight in at D. Electropotentials and electrochemical cells. So what is the purpose of an electrochemical cell? Well, they actually act as batteries, and that's because they convert chemical energy into electrical energy. Now, in terms of how they actually work, in essence, they're comprised of two metals. Crucially, they need to have differing reactivities, and what that does is it sets up a redox reaction, and as we know with redox reactions, reduction and oxidation take place, which by definition means that there's a transfer of electrons. So that's in essence how these electrochemical cells work. So here's a simple diagram of an electrochemical half cell. We have a metal bar being dipped in a solution of its own ions. This means that an equilibrium is set up, and we call this arrangement an electrode or a half cell. So there's our metal bar, in this case it's solid iron. Here's our electrolyte containing positive ions of the same metal, in this case Fe2+ ions. In its simplest form, an electrochemical cell is comprised of two half cells which are connected by a wire and a salt bridge. So here's a diagram taken from my revision guide, which is available to purchase at SwH Learning.co.uk. I'm super proud of these guides. They are crammed full of perfect exam wording and explanations. So in its simplest form, an electrochemical cell comprises of two half cells. There's the wire we mentioned and the salt bridge. In this case, we have two metals, iron and copper. They have differing reactivities. Remember, iron is more reactive than copper, so that's going to set up a redox reaction. They often like to ask you what the purpose of the salt bridge is. The purpose of the salt bridge is that it allows ions in the ionic substance to flow. So in essence, the salt bridge exists to complete the circuit. If you're interested, the salt bridge tends to be made from potassium nitrate. The key thing here about the salt bridge is that the ions used must not react with either electrolyte, and that's something that commonly gets asked. If you have a look up here, you've got a voltmeter that's added to the circuit in order to measure the electromotive force, the EMF, in volts. If you're keen for your cell reaction to go to completion, it's very important that the voltmeter is removed from the circuit. You often notice that the electromotive force is given this symbol, E theta, and it's not possible to measure the EMF of an electrode on its own. It must be measured between two connected electrodes, as we see here. Now, the EMF of all electrodes is measured by connecting them to a standard hydrogen electrode. That standard hydrogen electrode is given an E theta value, so an EMF of 0 volts by definition. Let's take a closer look at the standard hydrogen electrode. They often ask you the components of a standard hydrogen electrode. So the first thing to mention is that it involves hydrogen gas at a pressure of 100 kPa. You have a concentration of 1 mole per dm cubed hydrogen ions, HCl. You've got a temperature of 298 Kelvin, and you have the presence of a platinum electrode. So those are your components of a standard hydrogen electrode. It's also important that the concentrations of the ions in solution of the attached half cell, which we see here, should also have a concentration of 1 mole per dm cubed. As I've already mentioned, by definition, the electrode potential of the standard hydrogen electrode is 0 volts, and that allows the E theta value of all other electrodes to be measured as a comparison. Now we're going to discuss the conventional representation of half cells. So I'll write out an example here of a half cell. There's your platinum electrode. The first thing I want to point out is that a solid vertical line indicates a phase boundary, e.g. between a solid and solution. Your double vertical line here represents a salt bridge. Now your more positive half cell, that means where the reduction reaction is taking place, is always written on the right hand side. I promise I'll explain what that means very shortly. The species with the highest oxidation state in each half cell is written next to the salt bridge. So here's our copper. So we know that reduction is occurring over here. Just compare these oxidation states. Cu2 plus has a 2 plus oxidation state versus 0 here for copper, which explains why it's nestling up against the salt bridge. Now let's have a look at this side, at the standard hydrogen electrode. This hydrogen here has a 0 oxidation state. This is +1, hence why it nestles up against the salt bridge here. And then the EMF produced should be indicated, although it's not necessarily required by mark schemes. I'm just going to write it here, E theta equals plus 0.34 volts. Now the overall E theta value refers to the difference in the E theta values between the two half cells. So by connecting different half cells to a standard hydrogen electrode, it allows us to develop an electrochemical series. So let's have a look at this table and really work out what it's explaining to us. Now one thing to be aware of is, look, if you have the positive ion, obviously that needs to gain electrons in order to become neutral, so that's where reduction is occurring. If you look at these arrows, you can find that the weakest oxidizing agent, so the species least likely to be reduced to gain those electrons, has the most negative E theta value. So in this case, this lithium ion is the least likely to be reduced. It is the weakest oxidizing agent. Down here at Ce4+ with the most positive E theta value, that's going to be your strongest oxidizing agent, so those Ce4+ ions are the most likely to gain electrons. If we consider the right-hand side of the equation, notice that this table shows reduction half equations. Now, the element in its neutral state, these species will obviously therefore lose electrons, they'll be oxidized. So in this case, lithium here is the strongest reducing agent, it's the most likely to be oxidized, to lose electrons. Down here, Ce3+ is the weakest reducing agent, it's the least likely to lose its electrons. So in the exam, you might find it helpful when you get this table of electrode potentials to actually add these arrows with the labels, but do be careful. Sometimes the exams will list the reactions in reverse numerical order or back to front. So make sure that you're looking out for that. But when written conventionally, the oxidizing agents are the species on the left, as we know, as I was just saying. Reducing agents are the species on the right. The reduction reaction will be carried out by the half cell with the most positive E theta value. This occurs at the positive electrode, which is the right-hand side when drawn conventionally. The reaction occurs as it's shown in the electrochemical series. So yeah, your reduction reaction will just be one of these equations pulled out, whereas the oxidation reaction will be carried out by the half cell with the most negative E theta value. This occurs at the negative electrode, so the left-hand side when drawn conventionally, and therefore we need to write our reaction in reverse in order to show the loss of electrons. And then the E theta cell value overall is calculated using E theta cell equals the E theta value of the reduction reaction minus the E theta value of the oxidation reaction. I personally prefer just learning this, that the E theta cell is your most positive E theta value minus your most negative E theta value. So let's jump in with an example. So we're being asked to consider the following cell diagram and half cell reactions. So what we're actually going to do here is we are going to work out which of these equations represents reduction, which one represents oxidation. We're then going to rewrite those equations, making sure we flip the oxidation equation. We'll balance the electrons, and then we'll finally combine the equations to give the overall reaction of the cell before finding the total E theta of the cell. So I've pulled down the rules that I just went through so you can actually see how we're approaching this question. So first of all, we need to identify which reaction is reduction. We're looking at the most positive E theta value, which is this number here. So we're going to label that reduction. This reaction is oxidation. Now the reduction reaction we write left to right. So I'm going to keep that Ni2 plus 2E minus producing Ni solid. Just label that E theta value. It says here that for the oxidation reaction, the reaction needs to be written in reverse. So I just need to take that reaction and flip it. So that's step 1 done. Step 2, I need to balance the electrons. So we'll do a little bit of simultaneous equations here. 2 and 3 both go into 6. So I'm just going to multiply this equation by 3, this one by 2, and rewrite them. Let's combine those equations. We can see therefore that those electrons cancel out. So there's our overall equation, and then our final step is to find the overall E theta of the cell, which remember I'm going to do by doing my most positive E theta value minus my most negative. So the most positive value was minus 0.26. Take away the most negative value. We've got 2 minuses in a row, which means we need to add. So our final answer here is plus 1.40 volts. In order to deduce the negative electrode, the positive electrode, and the direction of electron flow, let's have a look at this conventional representation. Remember that oxidation will always occur at the negative electrode because electrons will be lost. And so that is located here on the left-hand side of the salt bridge. Reduction always occurs at the positive electrode, so that's where electrons will be gained. So it's the nickel half cell over here. The electron movement is that it flows along the wire from the negative electrode, which we already said is the aluminium one, to the positive one, the nickel. In terms of any observations, be prepared to mention colour changes of the solution. What you'd find though is that the aluminium electrode would decrease inside because the solid aluminium is being converted to Al3 plus ions. That occurs because of oxidation occurring, whereas over here the nickel electrode would gain in size because we know that reduction is occurring, so we're forming more Ni solid. So just to remind you what we've done overall, we had a look at the E theta values in order to determine which reaction was reduction, which was oxidation. The oxidation reaction has the most positive E theta value. Remember that the reduction equation is written left to right. The oxidation reaction is reversed. We then balanced the electrons. We added the two equations together. We cancelled out the electrons to give us the overall equation. And then finally, we calculated the E theta value by taking the more positive E theta value and then taking away the more negative E theta value from that to give an overall value of 1.4 volts. Remember, you could be asked to come up with the conventional representation of the cell. You'd be able to work that out through the fact that we've identified which equation is reduction, so we know that occurs on the right-hand side of the salt bridge. The left-hand side represents the oxidation reaction, and then the highest oxidation state species occur next to the salt bridge. Now, some half cells do not include metals, so some half cells do not contain a metal that can act as an electrode. In these cases, we use a platinum electrode because platinum is unreactive and can conduct electricity, so it provides a conducting surface for electron transfer. So here's a good example of the Fe2+, Fe3+ half cell. We've got the presence of a platinum electrode. If we look at the conventional representation of the cell, because there's no phase boundary between the Fe2+ and Fe3+, look, they're both in the same solution, there's no need for a vertical line. We see instead a comma. Over here we've got the chlorine gas and the chloride ion half cell. You do have a phase boundary here because you can see the chlorine gas being introduced, the chloride ions in solution, hence the vertical line here. This represents the salt bridge, and remember that the species with the most positive oxidation number goes next to the salt bridge. This platinum here is the platinum electrode. Now, some electrochemical cells are set up using the same metal as the half cells, but with different concentrations of aqueous ions. So as is the case here, we have the Cu2 plus present in solution, but 0.5 moles per decimeters cubed over here versus 1 mole per decimeter cubed over here. The first thing to be aware of is that the side with the higher concentration, so the right side here, is where reduction occurs. So I'll make a quick note of that here. So the side with the greater concentration of Cu2 plus experiences reduction, so that's why I'm adding 2 electrons here to produce that copper solid. So in terms of observations, you'd expect the solid copper electrode to increase in size, and the solution here will become lighter in colour as the Cu2 plus ions are used up. Therefore, it makes sense that the side with the lower concentration is where oxidation occurs. So let's write that equation for oxidation. So that's the loss of electrons. In terms of observations that take place over here, the solid copper electrode will decrease in size and the solution will become a more intense blue colour for the reason that more Cu2 plus ions have been produced and we've lost some of that copper solid. To set up an electrochemical cell, such as this one here, clean a piece of copper and a piece of zinc using fine sandpaper. This removes any oxide layer present on the metal. Degrease the metal pieces with cotton wool and propanone. The reason for that is that we need to remove the grease because it could prevent the cell from working efficiently. Place the copper in a 100 centimeters cubed beaker containing 50 centimeters cubed of 1 mole decimeter cubed copper sulfate solution. You may need to calculate the mass of an ionic solid containing the metal ions that would be required to make solution. And remember, we use moles equals concentration times volume to find the moles, and then mass equals moles times MR to calculate the mass of the metal compound required. Our next step is to place the zinc in a 100 centimeters cubed beaker containing 50 centimeters cubed of 1 mole per dm cubed zinc sulfate solution. Create a salt bridge using that potassium nitrate we mentioned before, which remember doesn't react with either solution. Connect the copper and zinc pieces using a wire and crocodile clips and include a voltmeter to determine the EMF. So now we're really going to apply what we've learnt. It does take practice, but we'll start here with question 1. We're using the electrochemical series below to select the species which is the most powerful reducing agent. So the first thing you need to be aware of is something which is a reducing agent is by definition oxidized, which means that it loses electrons. We need to look at the species on the right hand side. Let's look closely at the zinc because it needs to lose electrons in order to become Zn2+. So the species on the right hand side will be oxidized and therefore they'll be acting as reducing agents. The next thing to zoom in on is the most powerful one. Now, the species which is most likely to be oxidized is the one with the lowest E theta value. This is something you have to remember. So, as we look at the values, it means that it's therefore zinc. Select a species which in acidic solution will reduce this to this, but will not reduce this to this. So again, look at the table. We're looking first at row 6 because we're taking the VO2+, we're producing VO2+. So that, we've been told, is the reduction reaction, which means that has to read left to right, and it also means that it has to be the more positive of the E theta values when you compare the two equations. So that therefore means that we're looking at lower E theta values, but they've told us that it won't reduce VO2+ to V3+. So now we're looking at this row, so it can't be lower in terms of E theta values because it would allow this reduction. So we're looking for an equation that sits between the two. It's the one involving Fe3+. Because this is the reduction reaction reading left to right, oxidation must be occurring for this reaction, which means that the species that is being oxidized is Fe2+. Select a species which in acidic solution will oxidize VO2+ to VO2+. So let me clear up the table a little bit. So again, we're going from VO2 plus to VO2 plus, so we're looking along this row. Because they're telling us that this is the oxidation reaction, we're going to be writing that equation back to front to show that this is being oxidized. It therefore needs to be the low of the E theta values. So now we need to find an E theta value which is higher, indicating that reduction is taking place. So that gives us only one option, this one with a high E theta value. It's got to be something which is being reduced, which is why it's the Cl2. The cell represented below was set up under standard conditions, deduced the standard electropotential for the following half equation. So they've given us the overall EMF, so now we need to find the E theta values for the oxidation and reduction reactions. Now, as you can see here, this is the reduction reaction. It makes sense, it's on the right hand side of the salt bridge. So that's in effect our X value. Over here we have our oxidation reaction, so look in the table, we're looking along here. There's our E theta value. Now to find the overall E theta or EMF of the cell, we do E theta reduction minus E theta oxidation. We know the overall E theta of the cell at 0.48. The reduction value is what we're after. So what about the oxidation value? It's 0.77. So when you solve for X, you get an E theta reduction value of 1.25 volts. Write an equation for the spontaneous cell reaction. So we know that the E theta value is plus 0.48 volts, meaning that the reaction will be spontaneous. This is the reduction reaction. It's on the right-hand side of the salt bridge. This is the oxidation reaction. Just check the electrons happily. They cancel out. Now, because there's a 2e minus there and only 1e minus there, we need to multiply that one by 2. And then in terms of combining the equations, the reduction one reads left to right, so that remains the same. The oxidation one is reversed. And I'm just going to pop in the state symbols. Past paper practice. Table 4 shows some electrode half equations and their standard electrode potentials to deduce the oxidation state of nitrogen. Okay, so we know that oxygen is always -2. There's an overall negative charge. That means that if over here in total, because of that 3, we've got -6, it means the nitrogen here must be +5. And then here it's -2, so the nitrogen is +2. State the weakest reducing agent in table 4. So by definition, reducing agents are oxidized. We're looking for the most positive E theta value, looking down the right hand side, because after all, these are the substances which will lose electrons. So the answer here is therefore the chloride ion. Write the conventional representation of the cell that has an EMF of plus 0.43 volts. So we're going to have to fiddle around with these numbers here to try and work out what combination will result in plus 0.43 volts. Remember, what you're doing here to find the overall EMF, the E theta of the cell, is to pull out the most positive value and take away the most negative value. So it will take some practice to get used to what you're looking for here. I've written out the EMF equation. I'm just going to show you why it is 0.77. There's your most positive value, 0.34. You can see straight away how we arrive at plus 0.43. So then we need to identify which one's reduction and which one's oxidation. So remember, reduction is the most positive E theta value, oxidation is the lower of the two values. And so then when it comes to our conventional representation, we draw our salt bridge. We draw reduction to the right with the highest oxidation state closest to the salt bridge. If you check the state symbols, we can see that it's an aqueous solution, so that will be in the same phase, which is why we use a comma as opposed to a vertical line. There's our Fe2+, and then for the same reason, that means we have the presence of a platinum electrode. And then sort out the oxidation side, we have Cu2+ closest to the salt bridge. We have a phase boundary because of the solid versus aqueous, so So there's our solid state symbol. Use data from table 4 to identify an acid that will oxidize copper. Explain your choice of acid. Use these data to suggest a possible equation for the reaction and calculate the EMF of the cell that has the same overall reaction. I'm just going to label this. So because the acid is causing the oxidation of copper, the acid is acting as an oxidizing agent, and therefore by definition it's reduced. So we can apply what we've learned to that electrochemical series. So if I have a look at the E theta values, I'm looking for a more positive E theta value. So that sends me up in this direction. Remember that an acid is a proton donor, so although you can't see HNO3 anywhere, it's fine because look, we've got the proton donor combining with the NO3 minus. Then it's important obviously that you pick the right species. Then of course, because this is being reduced, you're allowed to write it left to right. So I'm just going to steal that equation as it is. Then we need the one with copper written the other way around because it's oxidation. Then we need to balance the electrons and then add them together, the two equations. Take your time here. And then finally, to find that overall EMF, let's do the most positive E theta value minus the most negative E theta value. So there's the most positive and there's the most negative. In non-rechargeable cells, reactions go to completion and cell reactions cannot be reversed. The flow of electrons between half cells provides the current required for the battery-powered device to work. There are many different versions of non-rechargeable cells, but they all work on the same principles. You don't need to know the exact chemical used in your exam, but you need to understand the role of all the components. So here we have an example of a non-rechargeable cell, which is a zinc manganese 4 oxide cell. In terms of its setup, you have a carbon rod, which is acting as an unreactive, inert positive electrode that allows electrons to flow. You have a non-reactive porous separator, which acts as a salt bridge, and as we know, salt bridges allow ions to pass through. The walls of this cell are made of zinc, and in this case, they act as the negative electrode, and because it's the negative electrode, they'll be attracting positive ions. The oxidation reaction occurs here, so the zinc solid loses electrons, and because that solid zinc is reacting, the cell will eventually leak if used for a long time. Inside the walls you have a zinc chloride paste which provides the important Zn2+ ions required for the half cell, and then the manganese oxide paste is where the reduction reaction occurs, so you'll see the addition of electrons. And here are two reduction half equations. So now let's write the overall equation. So because this is the more positive E theta value, remember that means that reduction is going to take place. So we keep that equation running left to right. The more negative E theta value is our oxidation reaction, so we know we're going to need to reverse that equation in order to show the loss of electrons. So I'll do that right now. Let's balance these electrons. I need to multiply this equation by 2 before adding them together. So overall, then I'm going to remove those electrons to give my overall equation. And then the overall EMF. So take the more positive EMF, take away the less positive EMF, so in effect we're adding them to get a final EMF of 1.50 volts. Now in a rechargeable cell, the reactions can be reversed by passing an electric current through the circuit. This forces electrons to flow from the positive electrode to the negative electrode. Rechargeable cells are more environmentally friendly than non-rechargeable, obviously because the metals and their compounds are reused. Rechargeable cells can also be responsible, however, for the release of CO2 into the atmosphere, as the electricity used for recharging the cell may come from power stations which have been burning fossil fuels. So there's really no perfect solution here. Let's look at an example of a rechargeable cell the lead acid battery. So the equation when discharging, so in effect when it's acting as a battery, is as follows. You have your oxidation reaction, which remember occurs at the negative electrode, the cathode. You've got your solid lead reacting with aqueous sulfate ions, forming lead sulfate. There's our loss of electrons, as you'd expect with an oxidation reaction. Your reduction reaction now, which occurs at the positive electrode, the anode. Lead oxide reacting with hydrogen ions, which remember have been donated by the acid. There's reduction taking place with the addition of 2 electrons. So what is our overall equation? Well, look, the electrons balance, which means we can just add the 2 equations together. Now, when the current is applied to the battery so that it's recharging, the reactions here will reverse. So I'll write those 2 equations occurring now at the negative and positive electrode together with the new overall equation. Again, the electrons cancel out, so the overall equation is how about a lithium-ion battery now? So the first set of equation when the lithium-ion battery is working as a battery, so when it's discharging, there's the loss of electrons. What about the reduction reaction, which occurs at the positive electrode? The overall reaction, thankfully the electrons are already balanced. Now when a current is applied, so we know that the battery is recharging, as you'd expect the reactions reverse. So at the negative electrode, let's reverse that reaction and make it reduction. At the positive electrode, let's make it oxidation. And then the last example I want to show you is the nickel-cadmium battery. So when discharging, when it's acting as a battery, the oxidation reaction which occurs at the negative electrode is as follows. The reduction reaction occurring at the positive electrode is as follows. You'll need to multiply this equation by 2 in order to be able to cancel out the electrons to give the overall reaction of this. And then as we know, when a current is applied to the battery and it's recharging, the reactions reverse as follows. Again, we've multiplied this equation by 2 in order to cancel out the electrons to provide this as our overall reaction. Hydrogen-oxygen fuel cells. So hydrogen-oxygen fuel cells are used to generate electricity without producing carbon dioxide. So they're thought to be a more green approach to releasing the energy we need to power our homes. The hydrogen-oxygen fuel cell does not need to be electrically recharged, and the reason for that is because the reactants are continuously supplied to the fuel cell. We find that they're more efficient than internal, more traditional combustion engines, and that's because a greater proportion of the energy available from the hydrogen-oxygen reaction is converted into useful energy. The major hazard, though, associated with the use of these fuel cells is the fact that hydrogen is extremely explosive, and we can't say that they're entirely carbon neutral, despite the fact they don't release carbon dioxide. And that's because the hydrogen used in them is often produced from crude oil or via electrolysis. Now here's the setup of an alkaline hydrogen-oxygen fuel cell. You've got your electrodes. They'll be made from platinum, which is an unreactive inert metal. They're porous in order to increase the surface area, and that's important because after all, platinum is extremely valuable and inexpensive. You have a non-reactive semi-permeable membrane, which is your salt bridge, allowing the hydroxide ions to pass through. As aforementioned, it's an alkaline fuel cell, meaning that the electrolyte being used is sodium hydroxide. If you were using an acidic fuel cell, it would have a strong acid, such as phosphoric acid. The current is generated because electrons are produced by the hydrogen electrode and are accepted by the oxygen electrode. So here's our 2 reduction half equations. As I've already mentioned, it's the reactions for the alkaline fuel cells due to the presence of the hydroxide ions. if you're asked about an acidic fuel cell, you'll need to use the half equations which contain H+ ions rather than the hydroxide ions. So looking more closely at the redox reactions taking place, the oxidation reactions where electrons are lost, this will occur at the negative electrode. Your reduction reaction where electrons are gained occur at the positive electrode. And then, as you can see, the electrons balance out, so it's possible to combine both equations to form the overall equation. And as you can see, it's such a clean source of energy because you have hydrogen reacting with oxygen, producing water with no carbon dioxide formed. Then the overall EMF, here's our E theta cell. We're doing E theta reduction minus oxidation, or the more positive E theta value minus the more negative E theta value to give an overall EMF of plus 1.23 volts. Now the value is the same for both the alkaline and acidic hydrogen fuel cells because the overall reaction is the same. Right, lots of past paper practice here is key. So this question is about electrode potentials and electrochemical cells. State the meaning of the term electrochemical series. It's a list of electrode potentials in numerical order. The table below shows some electrode potentials. State two conditions needed for the following half cell to have an E theta value of 0 volts. So we're looking for our standard hydrogen electrode, which, remember, I taught you needs to have a temperature of 298 Kelvin or a concentration of hydrogen ions of 1 mole per dm cubed or pressure of 100 kPa. Identify the weakest reducing agent in the table. So reducing agents by definition are oxidized. So we're looking on the right hand side at the species which will lose electrons. The weakest one needs to have the highest E theta value because remember the highest value refers to the species most likely to be reduced. So it's actually going to be this ion here. Use half equations from the table above to deduce an equation for the reduction of this to form this in aqueous solution by ion. So the first thing to be aware of is that we're carrying out a reduction reaction. So we need to look along this row in the table and the equation needs to read from left to right because that is reduction, the addition of electrons. And then we know that this is being carried out by ion. So by definition, the ion equation must be oxidized, which means it needs a lower E theta value. So the oxidation equation will be reading left to right, which means that it's the ion doing the reducing of this ion. Now, what's so insanely disgusting about this question is, yes, we know that oxidation will occur here to produce this ion, but the problem is that further oxidation will occur to this ion now because the E theta value here is lower than this reduction reaction here, which means that another reaction will take place to oxidize this complex ion to this one here. So that means that in order to oxidize both of these equations, you need 3 electrons, so you need to multiply this one by 3 before combining the equations. You're combining this one from left to right. Because this reaction occurs first, but it ends up with this product, you're actually going to combine this side and this side. Guys, please don't stress. This is the most disgusting question I've ever seen, so honestly, just move straight past it and it will not affect whether you get an A star or not or whatever grade you're after. Don't worry about it. I'm really running out of space here because then that one cancels out and this one becomes 3. So really you'd want to rewrite that again. Use data from the table above to explain why this complex ion will undergo a redox reaction with this. Give an equation for this reaction. Just get rid of this to make it a bit tidier. So we're looking at this ion. We know that because that has the most positive E theta value, by definition that one's reduction. In terms of oxidation, when we look at these two, we know that it's undergoing reaction with this particular ion. So that ion needs to appear on the right with a lower E theta value. Yes, it has a lower E theta value, so that's okay. So that's where your oxidation will occur. So in terms of our explanation, we write that the E theta value of this reaction is greater than that of the Fe2 plus reaction. And then in terms of the equation, luckily the electrons cancel out, So you're going to write this one left to right and reverse that one. Question 2. This question is about the development of lithium cells. The value of E theta for lithium suggests that a lithium cell could have a large EMF. The table below shows some electrode potential data. Use data in the table above to explain why an aqueous electrolyte is not used for a lithium cell. So we need to look at the E theta values here, and we can see that the E theta value for the lithium is more negative than that for water, hence the mention of the aqueous electrolyte. And therefore what that means is the water will oxidize the lithium to Li+, basically meaning that lithium would react with the electrolyte. Obviously, we really don't want that lithium reacting with water. In the 1970s, lithium iodine cells became a common power source for heart pacemakers. Lithium iodide is the final product of the cell reaction. Use the data in the table above to calculate the cell EMF of a standard lithium iodine cell. We're looking at these two values. So to find the E theta value of the cell, we do our reduction reaction, the one with the more positive E theta value, minus the oxidation reaction to get 3.58 volts as our final answer. An EMF value for commercial lithium iodine cell is 2.8 volts. Suggests why this value is different from the value calculated in part B. It's most likely due to the presence of non-standard conditions. In some lithium cells, lithium perchlorate is used as the electrolyte to reduce the oxidation state of chlorine. So oxygen is -2, lithium is +1. Overall, we know that oxygen is producing -8, so that means that chlorine must be +7 in order to make it neutral. In other lithium cells, lithium cobalt oxide electrodes and lithium electrodes are used. Give an equation for the reaction that occurs at the positive lithium cobalt oxide electrode. This is what I was just going through. You do need to learn these off by heart. Give an equation that occurs at the negative lithium electrode. Remember, the way round we're writing these equations is based on the battery in operation, so discharging. So that's why this lithium equation is the oxidation reaction. The diagram represents the cell used to measure the standard electrode potential for the Fe3+, Fe2+ electrode. Name the piece of apparatus labelled A. That's the salt bridge. What's the purpose of A? To allow ions to flow or to complete the circuit. Name the substance used as electrode B. Remember, that's your platinum electrode. It's inert. Complete table 1 to identify C, D and E from the diagram. Include the essential conditions for each. So C was your HCl. Remember, we want 1 mole per dm cubed. D is your hydrogen gas, which, because it's a gas, we need to state the pressure of it. It's 100 kPa. And then E is your solution containing the Fe2+ and Fe3+ ions. And we need a concentration of 1 mole per dm cubed. The standard electrode potential is plus 0.77 volts. Give the Ionic equation for the overall reaction in the cell in the diagram above. State the change that needs to be made to the apparatus to allow the cell reaction to go to completion. Well, I know what that is. We need to remove the voltmeter. So in terms of that Ionic equation, we know that the hydrogen gas is being oxidized. We know that the Fe3+ ions are being reduced. Then to cancel out the electrons, we need to multiply that equation by 2 and then add together the equations. The E theta values for 2 electrodes are shown. What is the EMF of the cell? So there's our salt bridge. This, remember, is reduction. This one's oxidation. Let's label them. So to find the E theta value, we do reduction minus oxidation. A student set up the cell shown in the diagram. The student recorded an initial voltage of this. Explain how the salt bridge provides an electrical connection between the two solutions because it has free ions. The standard electrode potential for the Cu2 plus Cu electrode is this. Calculate the electrode potential of the left-hand electrode in the diagram. So in order to do that, we take the E theta value of the standard electrode potential and take away the initial voltage. Both electrodes contain a strip of copper metal in the solution of aqueous Cu2 plus ions. State why the left-hand electrode does not have an electrode potential of 0.34 volts. The most likely reason for that is because the concentration is not 1 mole. Give the conventional representation for the cell in the diagram, include all state symbols. So because this is an electrochemical cell using solutions of different concentrations but involving the same element, in this case copper, here's your lower concentration. Remember, that's where I said oxidation occurs. Your high concentration represents the reduction reaction. So we'll draw our salt bridge. We know that reduction's occurring, so we're going from Cu2 plus to Cu. We put the highest oxidation state closest to the salt bridge. Make sure we include state symbols. Because it's going from aqueous solution to solid, we need a vertical line representing that phase boundary. And then the oxidation side, we're going to list that over here. Again, keeping the highest oxidation state closest to that salt bridge. When the voltmeter is replaced by a bulb, the EMF of the cell in the diagram decreases over time to 0 volts. Suggest how the concentration of copper 2 ions in the left-hand electrode changes when the bulb is alight. Give one reason why the EMF of the cell decreases to 0 volts. So if we look at the left-hand side, we know that oxidation is occurring there. Therefore, we're going to form more Cu2 plus ions, so we'd expect the concentration to increase. And then reasons why the EMF decreases to 0 volts, because eventually over time the concentration of Cu2 plus ions becomes equal across both solutions. The table shows some standard electrode potential data. Use data from the table to deduce the species that is the best oxidizing agent. So it is being reduced, which means we need to look down this side, and we need the most positive E theta value, which we can see belongs to chlorine. A cell was made by connecting 2 half cells with a salt bridge. One half cell consisted of silver in a solution of silver nitrate. The other one consisted of tin in a solution of tin 2 nitrate. Calculate the EMF of the cell and write a half equation for the reaction that occurs at the negative electrode. So to find the E theta value, we're going to do the reduction value minus the oxidation one. And then what about the half equation that occurs at the negative electrode? So remember, at the negative electrode, oxidation occurs. So that's why we need the tin equation. Use data from the table above to write an equation for the reaction of silver 1 ions and iron 2 ions. So there's our silver ions. What about the iron one? Well, if that's your silver, because compared with the 2 ions, it's more positive. It means that reduction's occurring, which means we need to look at the oxidation of both of these. So we're going to flip the equation, and it needs to be the one that's reacting with Fe2+. So it's only when you flip this one will it react with Fe2+. So that's oxidation. Handily, the electrons balance, so we can now combine those equations. Fuel cells are an increasingly important energy source for vehicles. Standard electrode potentials are used in understanding some familiar chemical reactions, including those in fuel cells. A salt bridge was used in a cell to measure electropotential. Explain the function of the salt bridge. Allows ions to move. Completes the circuit. Use data from the table to deduce the halide ion that is the weakest reducing agent. So it's oxidized. We need the one which is least likely to be oxidized, so the one with the highest E theta value. Let's look at all these values. Because it's being oxidized, remember we need to look at the right-hand side, and so that's why it's the fluoride ion, which makes sense, it's a halide. Use data from the table to justify why sulfate ions should not be capable of oxidizing bromide ions. The bromide ions are being oxidized, which means they need a more negative E theta value compared with what's going on with the sulfate ions. So we're looking at these numbers here, and sure enough, the bromide equation has a higher E theta value. So that's what I'm saying there. The E theta value of the bromide equation is greater than that of the sulfate equation. Use data from the table to calculate a value for the EMF of the hydrogen-oxygen fuel cell operating under alkaline conditions. So remember from what I just taught you, to find the overall EMF, we take this equation here, which represents reduction. This equation here represents oxidation, and therefore EMF is our reduction minus the oxidation, which gives us a value of 1.23 volts. There are two ways to use hydrogen as fuel for cars. One way is in a fuel cell to power an electric motor. The other is as a fuel in an internal combustion engine. Suggests the major advantage of using the fuel cell. Remember I said that a fuel cell converts more of the available energy from combustion of hydrogen into useful energy in the car. Acids and bases. So starting with our definition of a Bronsted-Lowry acid and base, it is a proton donor, and remember proton is an H+ ion. Good examples include strong acids like hydrochloric acid, sulfuric acid, weak acids like ethanoic acid. They're all Bronsted-Lowry acids. A Bronsted-Lowry base is a proton H+ acceptor. It includes strong bases like sodium hydroxides and weak bases like ammonia. If you have a water-soluble base, then you have what's known as an alkali. Now, in an acid-base equilibria, you have the transfer of protons, such as in this example. Here's your acid, here's your base. Because it's at equilibrium, it's a reversible reaction. So you'll produce another base, and water here is acting as an acid. So I just mentioned the term strong acid, but what does it mean? It's an acid that completely ionizes in solution. So, as I've already mentioned, hydrochloric acid is a good example of a strong acid, and it completely dissociates, it completely ionizes in solution, producing H+ ions and chloride ions. A strong base is a base that completely ionizes in solution. So, a good example is sodium hydroxide, and here we have it completely dissociating into sodium ions and hydroxide ions. If I change the wording slightly, what about a weak acid? The key thing here is that it partially dissociates in solution, such as ethanoic acid. So look, you've got a reversible arrow there. There's your ethanoate ion. Here's your H+ ion. A weak base now. It's a base that partially dissociates in solution, such as ammonia. Again, we have a reversible reaction making an ammonium ion and that hydroxide ion. So the pH scale. It's a measure of how acidic or how alkaline a solution is. And it's actually based on the concentration of H+ ions in solution. So remember, that means concentration of, in this case, H+ ions. The greater the concentration of H+ ions, the more acidic the solution is. And the lower the pH value is. So for example, a pH of between 0 to 2 represents strong acids, so ones which fully ionize. A pH of 12 to 14 represents a strong base. So again, one that fully dissociates, donating the OH- ions. Now, a difference of one pH value represents a 10-fold difference in hydrogen ion concentration. So, for example, a pH of 3 has 10 times the concentration of hydrogen ions compared with pH 4. So to recap, the pH scale is a measure of how acidic or alkaline a solution is. It's based on the concentration of H+ ions present in solution. The greater the concentration of H+ ions, the more acidic, and therefore the lower the pH value. A pH of 0 to 2 represents a strong acid. And then a difference of one pH value represents a 10-fold difference in the concentration of H+ ions. So for example, pH 3 has 10 times the concentration of H+ ions compared with pH 4. So this is taken from my revision guide available at swhlearning.co.uk. You will be familiar with this from when you started studying science in general. Here's your pH scale. These are the colours that universal indicator goes. Here is a neutral pH, which is 7. One thing to be aware of is the pH scale is a logarithmic scale, and that's because it has to accommodate an extremely wide range of H+ ions. It makes sense really if you consider that there's a 10-fold difference in concentration of H+ ions as you move from one pH to another. And using a log scale therefore simplifies awkward numbers into an easy to use range. So now we're asking ourselves how to convert between concentration of H+ ions and pH. So we're going to use two equations. pH equals minus log base 10 concentration of H+ ions. It makes sense therefore to say that the concentration of H+ ions is 10 to the minus pH. An acid has a pH of 3.5. What is the concentration of H+ ions in solution? So we're using this equation. Sub in your pH. So the concentration of H+ ions is 3.16 times 10 to the minus 4 mole per dm cubed. Next question, what is the pH of a solution with a hydrogen ion concentration of this? So we need pH equals minus log base 10 concentration of H+ ions. So our pH equals 1.9. And just so you know, pH is always given to 2 decimal places. Now let's look at calculating the pH of a strong acid. As we know, strong acids completely ionize in water, such as hydrochloric acid. Therefore, you need to learn this. The concentration of a strong monoprotic acid, that means that it releases 1 proton per HCl. And therefore, we can infer that the concentration of that acid is the same as the concentration of H+ ions. At 298 Kelvin, 25 centimeters cubed of a solution of strong monoprotic acid contained 1.65 times 10 to the minus 3 moles of hydrogen ions, calculate a value for the pH of this solution. So in step 1, we need to calculate the concentration of H plus ions. So remember, concentration, if I write the formula triangle over here, is number of moles divided by volume. So we know our number of moles. Just be careful with that volume, you need to divide it by 1,000 to get it into decimeters cubed. So our concentration of H plus ions is 0.066 mole per dm cubed. So now we need to find the pH. So write your equation, which is pH equals minus log to the base 10 concentration of H plus ions so to 2 decimal places, our answer is a pH of 1.18. Now I know this said a monoprotic acid, which is a more simple example. If you had something like sulfuric acid, H2SO4, which is diprotic, that means it releases 2 H plus ions. So if you're asked to calculate the pH of a diprotic acid, the concentration of H plus ions will be twice the concentration of the concentration you've calculated. So that's what I'd write there to summarize. And that's because 2 protons have been donated. Calculate the pH of a solution containing 0.066 mole per dm cubed of H2SO4. So here's an example of a diprotic acid. So pH equals the following. We know we've already got the concentration here, so we don't need to do as much as we did in the previous example, but we do know we need to multiply that number by 2, owing to the fact that 2 H plus ions are released. So our pH this time is 0.88. The ionic product of water, Kw. Water is slightly ionized according to the following equation. So that means it exists in an equilibrium where it forms H plus ions and OH minus ions in aqueous solution. Position of equilibrium, however, lies very much to the left. Now, as water is in equilibrium, an expression for Kc can be given. We've covered Kc previously. That's the equilibrium constant, where you do the concentration of the products divided by the concentration of reactants. And again, something we previously mentioned, that when the concentration of one of the substance is so much greater than that of the others, so in the case of water, the concentration of water is much greater than that of the H plus ions and the OH minus ions, it does mean that the concentration of H2O is effectively constant. So that's what we've written there. The concentration of H2O is much greater than that of the H plus and OH minus ions, meaning the concentration of H2O is effectively constant. And we can therefore incorporate it into the equilibrium constant Kc to create a new constant known as Kw, which is the ionic product of water. And at 298 Kelvin, the ionic product of water, Kw, equals exactly 1.0 times 10 to the minus 14. And this value here is something you'll need to know off by heart. So here I've written that in pure water, each water molecule that dissociates split into one hydrogen ion and one hydroxide ion. So we can therefore say that the concentration of H plus ions is equal to the concentration of OH minus ions. And then based on the value of Kw at 298 Kelvin, if we rewrite the ionic product of water equation, sub in that value, which was 1.0 times 10 to the minus 14, we can therefore write, because these two equal the same, that it equals H plus squared. So if we square root, we'll find the concentration of H plus ions. as being 1.0 times 10 to the minus 7. And then taking a previous equation we've looked at to find the pH of pure water at again 298 Kelvin, we take our pH equation we sub in that concentration of H plus ions we just found, and sure enough, as you might expect, the pH of pure water is 7.00. Remember, we give pHs to 2 decimal places, which makes sense as we know that water is neutral. Now, one thing to be aware of is that the dissociation of water into its ions is an endothermic reaction, so delta H is positive. And what that therefore means is that if you were to increase the temperature, it favours the forwards reaction, so the position of equilibrium shifts to the right, and what that has a knock-on effect is meaning that the value of that ionic product of water, Kw, increases due to the increased concentration of H plus ions and hydroxide ions. So if we look at another example, the value of Kw at a higher temperature of 323 Kelvin is, as you'd expect, higher at 5.48 times 10 to the minus 14. Let's write the ionic product of water equation. Sub in 5.48. We know that it equals H plus squared, square root to find the concentration of H plus ions, and then find the pH. So we can see here that the pH has decreased slightly. The odd thing here, though, is that despite the fact the pH has decreased, pure water we still count as being neutral because the concentration of H plus ions equals the concentration of hydroxide ions. So combining several different steps, so using Kw to calculate the pH of a strong base. Strong bases completely ionize in water according to this equation, therefore the concentration of a strong monoprotic base is the same as the concentration of hydroxide ions. So being asked to calculate the pH of a 0.1 mole per dm cubed sodium hydroxide solution at 298 Kelvin. So the first thing remember is that because sodium hydroxide is a strong base, it means it fully dissociates. So you can therefore say that the concentration of sodium hydroxide equals the concentration of hydroxide ions. So in this case, that tells us that the concentration of hydroxide ions is 0.1. Let's now find the concentration of H plus ions because after all we need that to feed into the pH equation. So the way we do that is by writing Kw equals, we said that we need to learn the value of Kw at 298 Kelvin. Remember I said it's always 1.0 times 10 to the minus 14. The concentration of hydroxide ions we know is 0.1. So solve for the concentration of H plus ions by dividing both sides by 0.1 to get a concentration of 1.0 times 10 to the minus 13. And now to find the pH. So our pH here is 13.00. That makes total sense. We started with sodium hydroxide. Sodium hydroxide is a strong base, so it makes sense, therefore, that it has a high pH. So what did we do to calculate the pH of a strong base? We knew, first of all, that the concentration of hydroxide ions equals the concentration of sodium hydroxide because it's a strong monoprotic base. We wrote down the ionic product of water equation, subbing in our value of Kw at 298 Kelvin. That enabled us to find the concentration of H plus ions, and then we fed that directly into our pH equation. So in our second example, we're being asked to calculate the pH of 0.0120 mole per dm cubed solution of calcium hydroxide at 298 Kelvin. So straight away, look, this is the formula of calcium hydroxide. It's diprotic, which means it releases 2 lots of hydroxide ions. In order to find the concentration of hydroxide ions, therefore, we'll need to do 2 lots of that. Let's write down our ionic product of water equation. Remember, we've learned that number off by heart. Solve for H plus ion concentration. Now let's find our pH. And as you'd expect, it's another strong base. Our pH is 12.38. Water dissociates slightly according to the equation. The ionic product of water Kw is given by the expression. Kw varies with temperature as shown in the table. Explain why the expression for Kw does not include the concentration of water. As I previously mentioned, it's because the concentration of water is so very high that in effect that concentration is constant. Explain why the value of Kw increases as the temperature increases. Right, I told you that it's an endothermic reaction. That means that as the temperature increases, the position of equilibrium moves towards the right, increasing the concentration of H plus ions and OH minus ions, therefore increasing the value of Kw. That means therefore, so the equilibrium position shifts to the right-hand side to oppose the increase in temperature. Calculate the pH of pure water at 50 degrees, give your answer to 2 dP. So we need this Kw value here. Let's write an expression for Kw. Now remember, when we use the ionic product of water, because each water molecule dissociates into one H plus ion and one OH minus ion, we can effectively write this. So we square root to find the concentration of H plus ions. And then we take our equation for calculating pH. Calculate the pH of this concentration of aqueous sodium hydroxide at 50 degrees Celsius. Give your answer to 2 dP. So we know our concentration of NaOH is 0.12. Because it's a strong base, it will completely ionize, meaning that the concentration of OH minus is the same as the concentration of sodium hydroxide. So we can infer the following. Let's write an expression for Kw. Kw remains 5.48 times 10 to the minus 14 at 50 degrees Celsius. Solve for H plus ion concentration. And then final step to find the pH. A nice high pH owing to the fact we have a strong base. We've looked at previously how strong acids and strong bases behave and the ionic product of water, but what about weak acids and weak bases? The first thing to point out is that they only partially dissociate in water. So, for example, if here's our generic formula of a weak acid, as I previously pointed out, there's going to be an equilibrium set up. It's a reversible reaction which releases H plus ions, hence it's an acid, it's an H plus donor, and in this case an A minus ion. So that's the negative ion left over once the H plus has been lost. Therefore, an equilibrium expression can be written for Ka, the acid dissociation constant, the concentration of H plus ions at equilibrium multiplied by the A minus ions, divided by the concentration of reactants, so our weak acid. Now, the larger the value of Ka, the further the equilibrium is to the right. That means that more of the acid is dissociated, so the stronger the acid. And the units for Ka need to be worked out each time in exact same way as we work them out for Kc, the equilibrium constant. Calculating the pH of weak acids is slightly more tricky compared with when we worked out the pH of a strong acid. Now, the first approximation we make when calculating the pH of weak acids is that the weak acid dissociates to produce equal concentrations of H+ ions and A- ions. So it allows us to write this. And then another way of writing that is this. If we multiply our two products, it's the same as saying that we've got the concentration of H+ ions squared. Our second assumption, because the dissociation of the weak acid is very small, as per our definition of a weak acid, it means that the concentration of HA is effectively constant. So there's our first assumption, and here's our second assumption. So here we're being asked to calculate the pH of 0.15 mole per dm cubed solution of a weak acid, ethanoic acid, at 25 degrees Celsius. For ethanoic acid, the acid dissociation constant Ka equals 1.74 times 10 to the minus 5. So your first step is to write an expression for Ka. So we'll put our concentration of products multiplied together. Remember, ethanoic acid looks like this. There's the H+ ion. So the other ion will be CH3COO- divided by the concentration of reactant, so the ethanoic acid itself. And when you write Ka, there's no need to include EQM, the equilibrium. The next thing we're going to do is use the assumptions I just went over and the data provided to sub in the given values. So Ka we know is 1.74 times 10 to the minus 5. According to this assumption here, we can write that it equals H+ squared divided by the concentration of our original weak acid, which was 0.150. Cross multiply these numbers and then square root to find the concentration of H+, which is 1.62 times 10 to the minus 3. And now we can find the pH. pH equals minus log to the base 10 concentration of hydrogen ions. So we get a sensible pH of 2.79. Remember, we give pHs to 2dP, and that makes sense considering we have a weak acid. So what did we do? We wrote an expression for Ka, then we subbed in the value of Ka as well as the concentration of the weak acid, and then based on this assumption up here, it meant that we could rewrite this as H+ squared. We solved to find the concentration of H+, and then we popped it into our pH equation. What about the effect of dilution on pH? 25 centimeters cubed of 0.5 mole per dm cubed propanoic acid is diluted by adding water until the total volume is 100 centimeters cubed. Our Ka for propanoic acid is this. Calculate the pH of this diluted solution of propanoic acid. This is a very involved question. Our first step is to calculate the dilution factor. And the way in which we do that is by dividing the total volume by the initial volume of acid. So our total volume was 100. We started with 25 centimeters cubed, so we have 4 times dilution. We're now going to find the concentration of our acid. We know that we had 0.5, but it's been diluted 4 times, so we need to divide that number by 4 to get a starting concentration of 0.15. And now we just dive back into what we were doing previously. So let's write an expression for Ka. It's propanoic acid this time, so we have H+ ions, C2H5COO- ions. Because remember, the formula propanoic acid is this. It's a carboxylic acid. There's that H+ ion, then everything else produces the rest of the ion divided by the concentration of propanoic acid. Pop in the value of Ka, it's 1.35 times 10 to the minus 5 equals, using that assumption we just made, H plus squared, divided by the concentration we just calculated, cross multiply and then square root to find the concentration of H plus ions. And then lastly, and most straightforwardly, we're going to find the pH. So our pH is 2.89. Ka and pKa. Now, like the concentration of H plus ions, Ka values are difficult to compare as they have a wide range and they have negative indices. As with the pH scale, this can be solved by converting Ka into pKa by taking the negative log. So to find pKa, we do minus log to the base 10 of Ka, which means that Ka equals 10 to the minus pKa, so very similar to our pH equation and its relationship with H plus ions. And the pKa values make it easier to compare relative acid strengths compared with Ka values. Because look, these are quite difficult to comprehend, but by the time we've popped them into this equation, the pKa values are much easier for us to use. Just be aware here that the stronger the acid, the larger the Ka value, so that this number is much greater than that one, but the lower the pKa value, the weaker the acid, the smaller the Ka value, the larger the pKa value. And do make sure you're happy popping these numbers into this equation. This question involves calculations about 2 strong acids, 1 weak acid, all measurements carried out at 25 degrees Celsius. A 25 centimeters cubed sample of 0.085 mole per dm cubed HCl was placed in a beaker. 100 centimeters cubed of distilled water were added. Calculate the pH of the new solution formed. Let's first of all find out the dilution factor by taking the final volume, which was 125, and dividing it by the initial volume. So we have 5 times dilution. Then we divide our concentration by the dilution factor to find the new concentration, 0.017. Now, because we have a strong acid, it allows us to infer that the concentration of hydrogen ions is the same as the concentration of that acid. And then we pop it into the equation of pH to get 1.77 as our final pH. What is the pH of a 0.02 mole per dm cubed solution of diprotic acid, which is completely dissociated? So the fact that it's diprotic means that it donates 2 lots of H plus ions. So if we take the 0.02, which is the concentration of the original acid, we need to multiply that number by 2 to find the concentration of H plus ions. And then we just pop it into pH equals minus log to the base 10 to 2 dP, that's 1.40. So the answer here is B. This question is about alkalis and carboxylic acids. In this question, all data are quoted at 25 degrees C. Carboxylic acids are weak acid. State the meaning of the term weak as applied to carboxylic acid, so only partially ionized. Write an equation for the reaction of propanoic acid with sodium carbonate. So we know that H plus is being donated. So in effect, it looks like this, the 2 ions plus water plus carbon dioxide. Then just make sure it's balanced. Calculate the pH of this concentration of calcium hydroxide. The ionic product of water is this. Give your answer to 2 dP. Right. So again, you're releasing 2 hydroxide ions. So that means the concentration of hydroxide ions is double this number. Pop in your Kw value, your concentration of hydroxide ions, solve to find H plus. The value of the acid dissociation constant Ka for benzene carboxylic acid is this. Write an expression for the acid dissociation constant Ka. Calculate the pH of this concentration solution, give your answer to 2 dP. Let's steal that Ka expression. We know that that equals the equivalent of H plus squared. The concentration of the acid was 0.012. Cross multiply and then square root to find the concentration of H plus ions. There's our final pH. Now we are investigating pH changes, and we're going to be obtaining a pH curve for titration using a pH meter. So here you've got your typical titration setup. In this case we have the acid placed in the conical flask. We've got our alkali and our burette. That's being added slowly to the acid in the conical flask, and we're measuring the pH using a pH meter. As always, we want to stir or swirl the flask continually to ensure that all the alkali which we've added has reacted. Make sure you measure the pH after each addition, and actually in this case we're repeating until the alkali is in excess. We add it in small increments as we get towards the end point in order to avoid missing the end point. When calibrating the pH meter should be calibrated just before it's used to improve the accuracy of the pH measurement. That's because over time the meter does not give accurate readings. The pH probe should be washed with distilled water between each of the calibration measurements, and that's to prevent different solutions from contaminating each other. Now, one thing you'll need to be familiar with is the shapes of the various titration curves. You'll need to learn these shapes. So if you have a strong acid reacting with a strong base, you'll obviously start at a very low pH owing to the presence of the strong acid, and you'll end at a very high pH. If you have a strong acid and a weak base, because you've got your strong acid, you'll start at a low pH, but then you'll end at a pH which is comparatively lower than when you had the strong base of between 8 to 11 on the pH scale. A weak acid and a strong base means that you'll start at a slightly higher pH due to the weak acid, but you'll end at a high pH due to the strong base. A weak acid and a weak base will start at a comparatively high pH for that weak acid and end at a comparatively low pH for the weak base. We're now doing pH calculations involving the mixing of an acid and a base. A 40 centimeter cube sample of 0.48 mole per dm cubed of potassium hydroxide, so a strong base, was partially neutralized by the addition of 24 centimeters cubed of 0.35 mole per dm cubed solution of sulfuric acid. Calculate the pH of the solution formed. Start by writing your neutralization equation. So there's your potassium hydroxide, your sulfuric acid. It's going to produce a salt, potassium sulfate, plus water, get it balanced. So this reaction will continue until one of these reactants is used up. If the acid is in excess, the remaining solution will be acidic. If the base is in excess, the remaining solution will be alkaline. So step 1, we need to find the number of moles of our base. So we do that by doing concentration times volume. The concentration we were told is 0.48. The volume is 40 centimeters cubed. Do divide by 1,000 to get that into centimeters cubed. 0.0192 moles is our answer. Now we need to find the number of moles of sulfuric acid. Very similar process. Our next step is to identify the number of moles of potassium hydroxide remaining in excess in the solution formed. So we take the number of moles we calculated minus, just be a little bit careful here, because that sulfuric acid is diprotic, it dissociates into 2 moles of hydrogen ions. So the moles of H plus will be twice the moles of sulfuric acid. Our step 4 is to calculate the concentration of hydroxide ions in the solution formed. And it's important that this volume here is the total volume in decimeters cubed found within the solution. So we need to add these two numbers together. Make sure they're in decimeters cubed. And I promise we're nearly there. So step 5, we're going to find the pH of the solution formed. The first step to do that is to write Kw expression. Kw, remember, equals 1.00 times 10 to the minus 14 at this temperature. The H plus ion concentration we're calculating, we know the concentration of hydroxide ions. So that gives us a concentration of hydrogen ions of 2.67 times 10 to the minus 13. And then final step. So that was quite a beastly question. So let's recap what we did. We wrote out the balanced symbol equation. We started by calculating the number of moles of potassium hydroxide that reacted, the number of moles of sulfuric acid that reacted. We identified that there was more moles of potassium hydroxide. We worked out how many would be left over by the time this reaction was completed. We then used that to find the concentration of hydroxide ions. We wrote an expression for Kw, substituting in that concentration of hydroxide ions in order to find the concentration of H plus ions, and then we did the final step that you're very used to by now. I'm now going to show you how you can use a titration curve to work out the concentration of an acid. So here we have a pH curve which was obtained when a 0.15 mole per dm cube solution of strong base, sodium hydroxide, was added to 25 centimeters cubed of aqueous solution of a weak monoprotic acid, HA. So just as you'd expect with the titration curves I've shown you before, because it's a weak acid, you won't have the lowest pH here, but you will end up at a very high pH because of the presence of that strong base. Now, this vertical section of the titration curve is known as the equivalence point, and this is the point at which sufficient base has been added to just neutralize the acid, or it could be vice versa. It's important to note that the pH at the equivalence point is not always exactly 7. We can see here that this is the volume of that sodium hydroxide that's been added to just neutralize the acid. If we consider half that volume, we call that half the neutralization point, and it's possible to read off the pH at that half neutralization point. So to find the concentration of the acid, step 1, you need to find the number of moles of sodium hydroxide added at the equivalence point. So we're using this formula triangle here. We know that the concentration was 0.15, the volume was 18.2 centimeters cubed. We need that in decimeters cubed, so just make sure that's divided by 1,000 to get a number of moles of sodium hydroxide added at the equivalence point of 2.73 times 10 to the minus 3. Then at the equivalence point, we can make the assumption that the number of moles of sodium hydroxide is the same as the number of moles of our weak acid. So we can say that the number of moles of our HA is also 2.73 times 10 to the minus 3. So now we have enough information to find the concentration of our acid. So concentration is given by number of moles divided by volume. Our number of moles was 2.73 times 10 to the minus 3. The volume, we were told, was 25 centimeters cubed. So we get a concentration of 0.109. So just to recap, to find the concentration of that acid, we first of all found the number of moles of sodium hydroxide added at the equivalence point. We used this volume down here in that calculation, seeing as this is the equivalence point. We inferred that the number of moles of our acid would be the same. And then we did a simple calculation to find the concentration by doing number of moles divided by volume as given in the question. If we zoom in on that half neutralization point again, so we can see it's the halfway point between 0 and the equivalence point. Here it's 9.1 centimeters cubed. At the half neutralization point, what we can infer is that half of the weak acid here has been converted to the A minus ion. And so therefore, we can write that the concentration of our weak acid is the same as the concentration of the A- ion. If we write an expression for Ka, the acid dissociation constant, let me just quickly write you an equation. It's easy to see therefore that the expression for Ka is the concentration of our product divided by the concentration of the reactant. And so if this is true, it means that this is also A-, so it's possible to cancel those out, meaning that Ka equals the same as the concentration of H+ ions. And if we take our equation for working out the pH, it's therefore possible to write this, seeing as the concentration of H+ ions is the same as Ka, and so it's therefore possible to write that pKa equals the pH. So to continue this question, to calculate the Ka of this acid, the acid dissociation constant, first step is to find the pH of the half neutralization point. So it's 4.2. That means that pKa also equals 4.2. Based on this statement here, and then we previously wrote the equation Ka equals 10 to the minus pKa, so just sub in that 4.2 to get a Ka value of 6.31 times 10 to the minus 5. Let's now determine how to select a suitable indicator. Remember, indicators are effectively dyes which change colour at a variety of pHs. Now, not all indicators are suitable for a particular reaction, and it's important you consider their pH ranges when picking a suitable indicator. So bromo-cresol green has a pH range of 3.8 to 5.4, phenol red 6.8 to 8.4, thymolphthalene 9.3 to 10.5. So here's a reaction here. We can see we started with a weak acid and a strong base. When selecting an indicator, it's important that the indicator's range lies within the vertical part of the titration curve. So based on that information, the thymolphthalene and the phenol red are both suitable indicators. These colours here represent their range. So as you'd expect, that sits between 9.3 and 10.5. This one sits between 6.8 and 8.4. Bromo-cresol green, that has a range of 3.8 to 5.4, as you can see, doesn't sit within the vertical part of the titration curve and as a result would not be suitable. You'll probably be used to this, but a good indicator by definition will show a sharp colour change in order to give a precise endpoint, and that explains why universal indicator is no good here, because it shows a range of colours. It needs to have a colour change in the vertical part of the titration curve, and clearly that colour change needs to be distinct so that the endpoint is obvious. Do note that there's no indicator suitable for weak acid and weak base titration because this vertical part of that titration curve is too short, because the weak acid's pH will start high, the weak base's pH will start quite low, reducing the size of the vertical portion. A beaker contains 25 centimeters cubed of a buffer solution at pH 3. Another beaker contains 25 centimeters cubed of a buffer solution at pH 12. 2 drops of each of the 3 indicators in the table are added to the solution. State the colour of the mixture of indicators in this buffer solution, assuming that the indicators do not react with each other. So we'll start with our beaker that contains pH 3. Let's take each of our indicators in turn. So bromo-cresol green, it's going to be yellow at pH 3. Phenol red will also be yellow, and thymolphthalene will be colourless. What about our solution that's at pH 12? Bromo-cresol green will be blue, phenol red will be red, thymolphthalene will be blue. So what will the overall colours be? Well, you've got yellow, yellow, colourless over here. So our colour will be overall yellow. Over here we've got blue, red, blue, so overall the colour will be purple. Our next topic is buffers, and we're going to be looking at the definition of a buffer, the various types of buffer, and the all-important calculations. So diving straight in with the buffer definition, these are solutions that resist changes in pH when small amounts of acid or base are added. So here we are monitoring the pH changes of a buffer solution when we add a strong base such as sodium hydroxide. Now these flatter horizontal regions of the titration curve represent the buffer regions, and here you can see as you increase the volume of your strong base, there's only a very small change of pH, so it's acting perfectly well as a buffer. Now if you neutralize half a weak acid, you end up with a buffer whose pH is equal to the pKa of the acid, and the reason for that is because it has an equal supply of HA and the A- ions, which remember we call the half neutralization point. So there are two types of buffer. One is an acidic buffer and the second type is a basic buffer. I'm now going to talk you through how acidic and basic buffers work. Remember, always bear in mind that you're trying to resist changes in pH when you add an acid or an alkali. So starting with acidic buffers, they're made from a weak acid, remember this partially dissociates, and a soluble salt of that acid. And if you think about it, it makes sense because the weak acid will react with any base you add, and the soluble salt will react with any acid you add. So here's your general equation. Your weak acid sets up in an equilibrium where it releases H+ ions and A- ions. The acidic buffer will maintain a pH of below 7. So how can we go about making an acidic buffer? Well, as I said, we need a weak acid. In this case, we've added excess ethanoic acid to a strong base, potassium hydroxide, and that allows our ethanoate ions to be produced, and we mix those with a solution of ethanoic acid to create the buffer equilibrium, where you have ethanoic acid dissociating to form H+ ions and the ethanoate ion. So in the case when you add alkali to your solution, how do we resist a massive increase in pH? Well, those alkali ions which have been added react with your weak acid in your buffer. So in this case, it would be the ethanoic acid. Here's your general formula of a weak acid in this case. It's going to produce water in a neutralization reaction and A- ions. And by doing this, the hydroxide ions are removed and the pH remains almost the same. What about when you add acid? How do we prevent a massive decrease in pH? Well, as you'd expect, your acid donates H+ ions, and this reacts with your soluble salt ions, which are present in your buffer. So in the case here, it would be the ethanoate ions. By doing that, it moves the position of equilibrium to the left, increasing the amount of, in this case, ethanoic acid. Your ethanoate ions here would decrease, meaning that the pH remains almost the same. And now let's consider how basic buffers work. Well, in this case, they're made from a weak base, something like ammonia, and a soluble salt of that base. They work by maintaining a pH of above 7. So here we have our weak base, the ammonia solution. We mix it with the soluble salt of that base, so in this case it's ammonium chloride. The ammonia solution partially dissociates, producing an ammonium ion, hydroxide ions. The salt we've added fully dissociates. So what happens when alkali is added? How do we prevent a massive increase in pH? Well, the hydroxide ions present in the alkali react with the ammonium ions present in the buffer. By doing that, it removes some of the hydroxide ions, and according to this reaction, it means that more undissociated ammonia forms, meaning that the pH remains almost the same. What about when we add acid? How do we prevent a massive decrease in pH? So what happens here is the H+ donated from our acid reacts with hydroxide ions. The hydroxide ions up here, the buffer equilibrium moves to the right, more ammonium ions form and the pH remains roughly the same. And obviously remember your equilibrium chemistry, by decreasing hydroxide ions, it will automatically move the position of equilibrium to the right in order to increase their number. How to calculate the pH of an acidic buffer solution. The acid dissociation constant Ka for weak acid has a value of 1.35 times 10 to the minus 5. A buffer solution was prepared by dissolving 0.0236 mol of a salt NaA in 50 centimeters cubed of 0.428 mol per dm cubed solution of weak acid. calculate the pH of this buffer solution. So as we know, we have an acidic buffer solution. So the way in which we're going to do this is we're going to calculate the concentration of the salt formed. We're going to write an expression for Ka, so our acid dissociation constant. We'll use that to calculate the concentration of H plus ions, and then it's the simple expedient of subbing in our concentration of H plus ions into our pH equation that we're very familiar with. In step 1, we're finding the concentration of our salt, NaA. So concentration, remember, is number of moles divided by volume. We know the number of moles is 0.0236. The volume we were told was 50 centimeters cubed. Do divide that by 1,000 to get it into decimeters cubed. Our concentration is 0.472. Next step is to write an expression for Ka. Remember, our equation for the dissociation of our weak acid looks like this, which is why this is our expression for Ka. It's our concentration of products multiplied together divided by our concentration of acid. Ka, they told us, was 1.35 times 10 to the minus 5. One thing to be a little bit careful of is you need to remember the fact that because our salt is going to completely dissociate, it means that we can infer that our concentration of A- ions is the same as our salt concentration. Concentration of acid we were given in the question. So our concentration of H plus ions equals 1.22 times 10 to the minus 5. So finally we can find pH. So our final pH is 4.91. So to recap, we found the concentration of our salt. We then wrote our expression for Ka. Because that salt completely dissociates, it means that our concentration of A- was exactly the same. Now, one thing I do want to point out is you cannot write this formula here, which you will have seen previously. And the reason for that is because the concentration of H plus ions by definition does not equal the concentration of A- ions in a buffer solution. And then by solving to find our concentration of H plus ions, it enabled us to find the pH. Now we're being asked to calculate the pH of a buffer solution with equal acid and salt concentrations. So a buffer consists of 0.1 mole per dm cubed ethanoic acid, 0.1 mole per dm cubed sodium ethanoate. What is the pH of the buffer? And Ka for ethanoic acid is this. Now, by definition, when you have equal acid and salt concentrations, we've reached our half neutralization point. So to remind you, it's this portion of the graph here where you've added half your volume in order to neutralize either your acid or your alkali. And so we can make this statement, which is at that half neutralization point, the concentration of H plus ions equals the concentration of A minus ions, and therefore that pH equals pKa. So now we can calculate pKa of the acid. So pKa is minus log to the base 10 Ka. Building on everything we've learnt previously, we said that because pH equals pKa, we know that the pH is therefore 4.77. Remember, these three dots mean because, these three dots mean therefore. Calculating the mass of salt required to make a buffer solution. A buffer solution is made using benzene carboxylic acid and sodium benzene carboxylate. According to this equation, calculate the mass of sodium benzene carboxylate with an MR of 144 that should be dissolved in 25 centimeters cubed of 0.1 mole per dm cubed solution of benzene carboxylic acid to produce a buffer solution with pH of 4.05. The pKa for benzene carboxylic acid is 4.298 Kelvin. Assume that the volume of solution remains constant. So lots of different terms here that you'll have come across. I know it's all about making sure that you do everything in the right order, but if you're not sure, you can definitely find, if you've got pKa, that will enable you to calculate Ka. You'll be able to write an expression for Ka. Hopefully you'll be able to work out H plus ion concentration. So it's somewhere to get started. Now, in terms of how we're actually going to go about answering this particular question, our first step is to indeed calculate the value of Ka, so the acid dissociation constant for our weak acid, our benzene carboxylic acid. So Ka, remember, is given by 10 to the minus pKa. Step 2, we're going to calculate the concentration of H plus ions using the pH of the buffer solution. So our concentration of H plus ions is 8.91 times 10 to the minus 5. Step 3, we're going to find the concentration of the benzene carboxylate. And in order to do that, we need to write an expression for Ka. So Ka equals concentration of C6H5COO minus multiplied by a concentration of H plus ions divided by the concentration of our acid. So Ka we just found to be 6.31 times 10 to the minus 5. We're after our concentration of benzene carboxylate. We just found our concentration of hydrogen ions. And then finally the concentration of the acid was 0.1. Once you've rearranged, our concentration of benzene carboxylate ions is 0.071. We're so close now because we're being asked to find overall the mass of sodium benzene carboxylate. We have the concentration, which means we can now find the number of moles. Which we do by doing the concentration times volume. The concentration we just found, the volume was 25 centimeters cubed. Get that into decimeters cubed. And then final step, find the mass of C6H5COO minus. We do number of moles times MR. They told us that the MR was 144. So our final answer is a mass of 0.25 grams. To summarize, to find the mass of salt required to make a buffer solution, we used all the information in the question to calculate Ka by doing 10 to the minus pKa provided in the question. We found the concentration of H plus ions, very similar maths, 10 to the minus pH provided in the question. Then we wrote an expression for Ka, substituting all the values either just calculated or given in the question. That enabled us to find the concentration of benzene carboxylate ions. We then used that to find the number of moles, and then finally we found the mass by doing number of moles multiplied by the MR. One thing I should mention is that dilution with a small volume of water does not affect the pH of a buffer solution, and that's because the ratio of the A- ions, so for example the ethanoate ions, to the concentration of the acid, for example the ethanoic acid, remains constant, and then due to this equation here, the concentration of H plus also remains constant. Time for another calculation. So this time we're calculating the change of pH when adding a base to an acidic buffer solution. So remember, an acidic buffer solution will contain a weak acid and a salt of that acid. So in this case, a buffer solution was prepared by adding 0.0142 moles of potassium propanoate to 100 centimeters cubed of 0.5 mole per dm cubed solution of propanoic acid, mixing thoroughly. 2.5 times 10 to the minus 4 moles of potassium hydroxide was then added. Calculate the pH of the buffer solution after adding that potassium hydroxide. And for propanoic acid, the value of Ka is this. So the way in which we're going to go about this question is we're going to write an expression for Ka for the buffer solution. We'll find the initial number of moles of propanoic acid. We can see here that we have volume and concentrations. So that should be very straightforward. We're then going to calculate the amount of propanoic acid remaining after the addition of our strong base, the potassium hydroxide. And this will enable us to find the number of moles of propanoate ions and then various concentrations, so that we can rearrange to find the concentration of H plus ions and finally calculate pH. I know it sounds super complicated, but the order is logical. So we'll start by going through step 1. We'll write an expression for Ka. Let me just write the equation. So here's your propanoic acid. It's a weak acid. It dissociates partially into our all-important H plus ions and our propanoate ions. So we can see straight away that our expression for Ka looks like this. Our next step is to find the number of moles of propanoic acid, so our weak acid initially. So it's concentration times volume. Concentration was 0.5, volume was 100 centimeters cubed. So our initial number of moles of propanoic acid was 0.05 moles. Now we need to find the number of moles of propanoic acid remaining after the addition of our strong base. So I've just underlined the two key number of moles here. So number of moles remaining will be our starting moles minus the number of moles of potassium hydroxide. So we have 0.0498 moles of propanoic acid remaining. Now we need to find the number of moles of propanoate ions in solution. I'm going to change colour of highlighter for you to see this more clearly. So what will the number of moles of propanoate ions in solution be? Well, it will be the number of moles we started off with plus the number of moles of potassium hydroxide. And that's because the hydroxide ions present in that potassium hydroxide react with the propanoic acid to give water and the propanoate ions. We're getting closer now. We're almost ready to sub in numbers for our expression for Ka. The first thing we want to do is find the concentration of propanoate ions and find the concentration of propanoic acid. Our volume up here is 100 centimeters cubed. So there's our concentration of propanoate ions. What about our concentration of propanoic acid? And now we're on our home stretch. We're subbing our values into the expression we wrote for Ka, and therefore we're finding the concentration of H plus ions in the process. So we're going to steal this expression. Ka equaled 1.35 times 10 to the minus 5. Concentration of H plus ions is what we're after, and we just found out the other two values. And step 8, we're going to calculate the pH. So wow, that was certainly a very complicated question. So what were we doing? We were finding the change in pH when we add a base to an acidic buffer solution. So our first step was to write the expression for Ka. We then calculated the number of moles present in solution of the propanoic acid by doing concentration times volume. So we used these two numbers here to find that we started with 0.05 moles of acid. Then we needed to work out how much reacted, so how much was left over. So we took that number that we started with initially and then minused, in effect, the number of moles of potassium hydroxide, because the hydroxide ions, after all, react with the propanoic acid to give water and propanoate ions. So that was the number of moles of acid remaining. Then in order to find the number of moles of propanoate ions present in solution, we took the initial number they told us and added the 2.5 times 10 to the minus 4, because remember, when a base is added to an acidic buffer, the amount of weak acid decreases. And that's because when we add our base, what happens is the amount of this decreases, but the amount of the salt increases. So that's why we added that number there. Then we found the concentration of propanoate ions, the concentration of propanoic acid. That gave us enough numbers to substitute into the expression for Ka. We solved to find the concentration of H plus ions and then finally found the pH. So in the previous example, we calculated the change in pH when adding a base to an acidic buffer. This time we're adding an acid to an acidic buffer. In a buffer solution, the concentration of ethanoic acid is this. The concentration of sodium ethanoate is this. Ka has a value of this. Calculate the pH of this buffer solution. So slightly more straightforward. What you want to do first of all is find the concentration of H plus ions in the original buffer solution. So write our expression for Ka. You should be nice and familiar with this by now. So Ka we were told was 1.74 times 10 to the minus 5. We're after the concentration of H plus ions. Solve for H plus ion concentration. And then to find the pH of the original buffer solution, it now gets more complicated if we consider part 2. 10 centimeters cubed of 1 mole per dm cubed HCl is added to 1000 centimeters cubed of this buffer solution. Find the pH of the new solution. So we will need to find the number of moles of hydrochloric acid added to the buffer. That will enable us to find the amount of ethanoate ions remaining after the addition of HCl. We'll also be able to calculate the amount of ethanoic acid now in solution, and then based on our expression for Ka, we'll be able to find the concentration of H plus ions. So step 1, find the number of moles of HCl added. Our next step is to calculate the amount of ethanoate ions remaining after the addition of HCl. To make it easier for you to understand, I've just written a quick equation demonstrating the buffer. So when the HCl is added, what happens is it reacts with the ethanoate ions, meaning therefore that the amount of the ethanoate ion decreases, forming more ethanoic acid, so that in effect increases. So to pin maths to this, we look back at the wording of the question. We started with 0.1 mole per dm cube concentration. Just look at those units. That means we can infer that we started with 0.1 moles of ethanoate ions. And then we know that the number of ethanoate ions will have decreased by 0.01 moles, because after all, that's the quantity of HCl available to react with the ethanoate ions. So our number of moles of ethanoate ions remaining is 0.09 moles. Our next step is to calculate the amount of ethanoic acid in solution. So through the HCl H plus ions reacting with the ethanoate ions, we know we'll have more ethanoic acid, but how much more? So we have in effect 0.15 moles of ethanoic acid, and then we add the 0.01, which formed when we added the HCl. So we now have more ethanoic acid. We now have 0.16 moles. So I think that's probably the most difficult part of the question done, because we can now find our concentration of H plus ions. One thing to think about here is the fact that obviously the Ka expression involves concentrations, but if you look at the wording of the question, it says that the volume of buffer solution is 1,000 centimeters cubed. So when we say this out loud, we're saying that we have 1 mole per decimeters cubed of hydrochloric acid. So that is in effect 1 mole present in this volume, because 1 decimeters cubed is the same as 1,000 centimeters cubed. So in this particular case, we would say we can cancel out the volumes and not worry about them. So our Ka value was 1.74 times 10 to the minus 5. We know we've got 0.09 moles of ethanoate ions, 0.16 moles of ethanoic acid. So we can solve to find our H plus ion concentration, which is 3.09 times 10 to the minus 5 moles present per decimeters cubed. So that's why we can bring those concentration units back in. And then final step is to find the pH. This was extremely nasty, so let's go through quickly what we did again. So in a buffer solution, we know we have a weak acid reacting with a salt. Of that acid, we have our Ka value. We're being asked to find the pH of the initial buffer solution, which was fairly straightforward as we wrote our expression for Ka, solved to find the concentration of H plus ions, plugged it in to find the original buffer solution's pH. Things got more complicated when we added 10 centimeters cubed of 1 mole per decimeters cubed HCl to 1,000 centimeters cubed of this buffer solution. We were asked to find the pH of the new solution. So what we did first of all was find the number of moles of HCl added. And then we had to recall that the way that this particular acidic buffer works is the HCl reacts with the ethanoate ions and therefore decreases the number of ethanoate ions but increases the number of ethanoic acid. So when we calculated the amount of ethanoate remaining, we took the original amount and minus the amount of HCl present in our reaction mixture to find 0.09 moles. We then wanted to find the amount of ethanoic acid, which we knew would be an increase. After all, more ethanoic acid was produced for the reasons I just specified. So we took the original amount of ethanoic acid in the question and we added this value here to get a final total of 0.16. We then subbed in all these numbers to our Ka expression. Remember I said it's okay to not include volumes, and the reason for that is because the volume given was 1,000 centimeters cubed, which is in effect 1 decimeter cubed. And then we could solve to find the concentration of H plus ions and finally the pH. At 298 Kelvin, the value of the acid dissociation constant for weak acid is this value. Calculate the value of pKa for the weak acid at this temperature. So pKa is the same as minus log to the base 10 Ka. So to 2 dp as the question specifies, it's 4.52. Write an expression for the acid dissociation constant. So our expression for Ka is the following. Calculate the pH of a 0.17 mole per dm cubed solution of HX at this temperature. Give your answer to 2 dp. So start by getting your acid dissociation constant copied down. Now one thing you must remember here is that when you calculate the pH of a weak acid, you can assume that the concentration of H plus ions equals the concentration of A minus ions, so these are in effect the same. If you write this statement here, it's fair to say it's the same as the concentration of H plus squared. So that's what we're going to do here, because it makes everything so much easier for us. Remember, this doesn't apply with a buffer. It's only when you're finding the pH of a weak acid by itself. Finally, find the pH. An acidic buffer is formed when 10 centimeters cubed of 0.125 mole per dm cubed aqueous sodium hydroxide are added to 15 centimeters cubed of 0.17 mole per dm cubed aqueous weak acid. The value of Ka is this. Calculate the pH of this buffer solution. So we know this is going to be way more involved because it's worth 6 marks. I'm writing this again just so that you can see how we're going to arrive at this answer. Remember how the acidic buffer works is that when you add that strong base, the sodium hydroxide, it reacts with your weak acid to produce these ions here, releasing H+ ions. By doing so, it uses up the acid, it increases the number of negative ions, and that will enable you to find the new concentrations of the acid and the A- ion, and then by using your expression for Ka, you'll be able to calculate your H+ again. So I promise it's not as awful as it sounds. Let's start by writing our expression for Ka. Same old, same old. Let's start by finding the initial moles of our weak acid that's present at the start. So we know we're going to do concentration times volume. The concentration we were told was 0.174. The volume is 15 centimeters cubed. So that's our initial number of moles of our acid. What about our moles of weak acid remaining once the sodium hydroxide has been added? Well, we take our number of moles that we had to begin with. We need to find out the number of moles of sodium hydroxide that were added. So I've done a quick calculation up there. What about the number of moles of the A- ions now present in solution as a result of the reaction between the sodium hydroxide and the weak acid? So the moles of X-, by definition, must be the number of moles of hydroxide ions which were added. So we know that that is 1.25 times 10 to the minus 3. We're so close now. Let's sub in our value for Ka. We're finding our concentration of H+ ions. That equals 3.27 times 10 to the minus 5. So our final answer is 4.49. Buffer solutions are important in biological systems and in industry to maintain almost constant pH values. In the human body, one important buffer system in blood involves the hydrogen carbonate ion and carbonic acid, which is formed when CO2 dissolves in water. Use the following equation to explain how this buffer maintains a constant pH of 7.41 even if a small amount of acid enters the bloodstream. So when that acid enters the bloodstream, it's in effect donating more H+ ions, meaning that the position of equilibrium shifts to the left, and therefore the ratio of the concentration of carbonic acid to hydrogen carbonate ions remains constant, so therefore the concentration of H+ ions and pH remains constant. In a sample of blood with a pH of 7.41, the concentration of hydrogen carbonate ions is 2.5 times 10 to the minus 2. The concentration of carbonic acid is this. Calculate a value for Ka, the acid dissociation constant. Write your expression. Now to find the concentration of H+ ions, remember we do 10 to the minus pH. We were told that was 7.41. And then sub in our values into our expression. In industry, the pH of a solution used to dye cloth must be controlled or else the colour varies. A solution of dye in a beaker is buffered by the presence of ethanoic acid and sodium ethanoate. In this solution, the concentration of ethanoic acid is this, the concentration of sodium ethanoate is this. The value of Ka at 298 Kelvin is this. A 10 centimeter cubed portion of 1 mole per dm cubed HCl is added to 1000 centimeters cubed of the buffered solution. Calculate the number of moles of hydrochloric acid added. So number of moles is concentration times volume. Calculate the number of moles of ethanoic acid and the number of moles of sodium methanoate in the solution after the addition of HCl. Let's start here with the mole of sodium methanoate after the addition. So you add hydrochloric acid, and what it does is it reacts with the ethanoate ions, in effect using them up. Just look up here, we're told that the concentration of ethanoate ions is 0.1. Because this volume is 1000 centimeters cubed, which is in effect per decimeters cubed, we're allowed to use that as our number of moles to begin with. We're going to minus the 0.01 we just calculated, because after all that's the hydrochloric acid that reacted, which gives us 0.09 moles of sodium methanoate left over. And then what about the number of moles of ethanoic acid? Well, when the H plus ions from the HCl react with the sodium methanoate, you're going to make more ethanoic acid. So we'll get our starting number of moles and add 0.01 this time to get 0.16 mole. Hence calculate the pH of the new solution. Final pH is 4.51. Properties of period 3 elements and their oxides. I brought up a periodic table so we can be sure that we're looking at the same thing. That's period 1, that's period 2, that's period 3. So this part of the video just deals with these elements here, ranging from sodium to argon. The first thing to be aware of is that the reactions of period 3 elements are all redox reactions. That means both oxidation and reduction reactions occur. So in the case of sodium reacting with water, we're going to produce sodium hydroxide and hydrogen gas. I've added the oxidation states here in my revision guide. You can see that sodium goes from 0 to +1, so it's been oxidized. Hydrogen goes from +1 to 0, so it's been reduced. If you've done this at school, you'll know that the group 1 elements, so such as sodium, react very vigorously with cold water. They skid along the surface of the water, it floats, it eventually melts. The temperature increases, indicating that the reaction is exothermic, heat energy is released. And the sodium hydroxide produced, remember, is a strong base. So when we add universal indicator to that remaining solution, it will turn purple-blue, and that's because it's strongly alkaline and has a pH of around 13 to 14. If we take the next period 3 element, in group 2 this time, magnesium, it reacts much more slowly with cold water. Again, it produces magnesium hydroxide, hydrogen gas. Check out the oxidation states. You can see here that magnesium is oxidized, hydrogen is reduced. You'll find that the solution formed is far less alkaline compared with the sodium hydroxide. This time the pH is around 9, and that's because the magnesium hydroxide produced is only sparingly soluble, slightly soluble. So if we take it up a notch and we react the magnesium this time with steam as opposed to cold water, you're going to have a vigorous reaction. This time it produces magnesium oxide plus hydrogen, and check out those oxidation states. Now we're taking the reactions of period 3 elements with oxygen. So when we burn sodium and oxygen, we form a white solid of sodium oxide and we'll see a yellow flame. Taking magnesium, you might be familiar with this at school. It burns with a bright white light. That's why you need to wear special glasses, because it's quite blinding. It forms a white solid of magnesium oxide, and white fumes are also observed. Aluminium now burns with a bright flame, again forms a white solid. Now, despite the fact that aluminium is a fairly reactive metal, because it has an oxide layer, it means that aluminium is fairly resistant to corrosion in water, makes it a very useful metal, especially owing to its low density. Moving on to the non-metals of period 3, silicon. Silicon reacts with oxygen to form silicon dioxide, a giant covalent structure you might be more familiar with. It's sand, has a high melting and boiling point. Now phosphorus. Phosphorus reacts with oxygen to form P4O10. White smoke is produced. And then sulfur burns with a blue flame, producing a choking gas of sulfur dioxide. And here is an alternative reaction that may also take place. Now let's consider the melting points of our period 3 oxides that we've just formed. So starting with sodium oxide and magnesium oxide, which sit on the left-hand side of period 3, they're both metals. Because you've got a metal and a non-metal, you're going to have a giant ionic lattice. They'll have high melting points, and that's due to those strong electrostatic forces of attraction between oppositely charged ions. The reason why the magnesium oxide has a higher melting point compared with sodium oxide is simply because the magnesium ion, remember, is Mg2+. The sodium one is just Na+, so you end up with a stronger attraction between Mg2+ and O2-. Moving on to aluminium oxide, although it's an ionic lattice, it has some covalent character. The Al3+ ions from the aluminium have a strong attraction to the O2-, so that's why you have a higher melting point compared with sodium oxide. Now we move on to our non-metals. Silicon dioxide, I already mentioned, is a giant covalent structure, has many strong covalent bonds, so it has a high melting point. And then the last three, P4O10, SO3 and SO2, they have much lower melting points, and that's because they're simple molecular structures, meaning that their molecules are held together by weak van der Waals forces, which require very little energy to break. Now, the strength of the van der Waals forces very much depends on the size of the molecule. P4O10 being the largest molecule, therefore has a higher melting point compared with SO3 and SO2. Now a tiny detail here to do with determining the melting point and purity of a sample. First of all, you place your sample in a suitable melting point apparatus. You heat slowly to establish a melting point range. A broad range of melting points indicates the presence of impurities. A sharp melting point indicates a pure sample, in the way that a pure liquid like water, for example, has a sharp boiling point at 100 degrees Celsius. And then how do we determine whether a substance is ionic? Remember, you'll have learnt this at GCSE and IGCSE. When solid, something like sodium oxide will not conduct electricity because the ions aren't free to move. Melted or in aqueous solution, due to those ions being free to move, the substance will conduct, so you know that it's an ionic structure. Time to look at reactions of period 3 oxides now with water. So here's our sodium oxide reacting with water. The O2- ions present react with water to form hydroxide ions. A strongly alkaline solution is formed. With magnesium oxide, we've already mentioned that it's only sparingly soluble. That means it only partially dissociates in water, and therefore we know that this solution will be weakly alkaline, especially compared with the solution formed when sodium oxide is added to water. Aluminium oxide we know is ionic, but it has covalent character. It's insoluble in water for the reason here. Silicon dioxide is insoluble in water. And then we move on to P4O10. When that is added to water, we form a very strong acid of phosphoric acid with a very high pH. SO3, when added to water, forms sulfuric acid. As we know, it's a strong acid. It fully dissociates in water. It's got a very low pH. And then finally, SO2. This produces sulfurous acid, which is a weak acid with a slightly higher pH when compared with the other two examples. And that's why, to summarize, we know that metals form basic oxides, as demonstrated here, and non-metals form acidic oxides, as demonstrated here. More detail now on the acidic or basic nature of period 3 oxides. Remember, this comes from my revision guide available at SwH Learning.co.uk. So the detail we're going to add here is that those basic oxides produced by the metals will react with acids. The acidic oxides produced by the non-metal period 3 elements will react with bases. So starting with our basic oxide, sodium oxide, it does react with acid to give a salt plus water. Here's your example here with sodium oxide. Here's your example here with magnesium oxide. Aluminium oxide here is what we call amphoteric, which means it reacts with both acids and bases due to that covalent character despite it being an ionic substance. As a result, aluminium oxide reacts with sulfuric acid to produce a salt plus water. It also reacts with a strong base in order to give sodium aluminate. You'll be familiar with this reaction. This one will probably be less familiar to you. Moving on to our acidic oxides, silicon dioxide. Despite it being insoluble in water, it still reacts with strong bases, as seen in this reaction here. P4O10 will again react with a strong base. Sulfur trioxide now reacts with bases to form a salt plus water. In the intermediate stage, it forms sulfuric acid. And now sulfur dioxide, here's an example of a reaction of sulfur dioxide reacting with strong bases. I'm sure you'll have seen these before, particularly if you studied organic chemistry, but it is important that you can draw the various structures of these acids. So here we have sulfurous acid, there's its lone pair of electrons, sulfuric acid and phosphoric acid. So do note where the double bonds occur. Transition metals now, quite a large A-level, A2 topic. The first thing to be aware of is that the transition metals are found in what's known as the D block of the periodic table. Here's your S block, your P block, your D block. Now, in order for a metal to be classified as a transition metal, they must form at least one stable ion with a part-full D shell of electrons. So you can see that's literally what the definition is here, an element that forms at least one stable ion with a partially filled D orbital. And therefore, scandium here and zinc over here are not classified as transition metals. The reason for that is because scandium only forms 3+ ions, which have an empty 3d orbital, so they're not fulfilling this need for a partially filled d orbital. And zinc only forms Zn2+ ions, which have a full 3d orbital, so again, that's not partially filled. The properties of transition metals you've probably come across before. They have variable oxidation states. You might have seen, for example, Fe2+, Fe3+ exists as ions with more than one oxidation state. This actually enables them to take place in many redox reactions. The ions of transition metal elements form coloured compounds. Copper 2+ is blue, Fe2+ is green. Transition metals can be super useful because often they can act as catalysts, and the reason for that is the range of oxidation states that they exhibit allow the transition metals to catalyze other reactions, such as ion, which is the catalyst in the Haber process used to make ammonium, vanadium 5 oxide, which is the catalyst used in the contact process used to make sulfuric acid. Another property of transition metals is they form complex ions. They form when a ligand forms coordinate bonds with a transition metal ion. So we've introduced some new terms here. First of all, a complex ion is a central metal atom or ion which is surrounded by ligands. Key is our definition of a ligand. It is an ion or molecule with a lone pair of electrons that forms a coordinate bond with a transition metal. Remember, a coordinate bond is when both electrons are donated by the same atom. So these two super crucial definitions, again, the complex ion, a central metal atom or ion surrounded by ligands. The ligands are an ion or molecule with a lone pair of electrons that forms a coordinate bond with a transition metal. Let's now look at the different types of ligand. So the first one we're going to look at is the monodentate ligand. So we've taken our definition of a ligand. The key thing about a monodentate ligand is that a single coordinate bond is formed with a transition metal ion. So let's look at some examples. So you'll be familiar with water and ammonia. Water's oxygen has 2 lone pairs of electrons. The nitrogen and ammonia has 1 lone pair. Now water and ammonia are both neutral monodentate ligands and they're a similar size to each other. Now we have a chloride ion and a cyanide ion. These are both negatively charged monodentate ligands and they're both larger than water and ammonia. So our complex ions, which we know consist of a central metal atom or ion surrounded by ligands. Now there's a very specific convention when it comes to writing them. So we'll take our first example here. So the first thing to be aware of is that you have square brackets around the entire complex. Then you have round brackets around your ligand. That's only if the ligand is a molecule. In our second example here, again, we can see our square brackets. This 2 minus here and the 2 plus here represents the overall charge of the complex. And then the 4 here represents the number of each type of ligand surrounding the central metal ion. In the case of water, it was 6. Now the coordination number is the number of coordinate bonds formed to a central metal ion. And we're going to tie in the coordination number together with the oxidation states. So to find the oxidation state of the transition metal ion, we're going to do the overall charge of the complex minus the combined charge of the ligands. Let's look at an example. So the overall charge of the complex is 2+. Then we need to minus the combined charge of the ligands. This water ligand is neutral, so it's 6 times 0, which is 0, to get a final answer of +2. And so we can infer that the oxidation state of the transition metal ion, in this case the cobalt, must be CO2+. And remember, we use Roman numerals to represent that. Let's take another example now. So the overall charge on the complex is -1. Then we need to subtract the combined charge of the ligands. We have a chloride ion here, which remember is -1. There's 4 of them, so it's -4. So that gives us Fe3+, ion 3. Now, as we've already seen, ammonia and water are similar size and they're both uncharged, and this means that ligand exchange can occur between the ammonia and the water without a change in coordination number, such as the case here, where you have in the original complex ion water reacting with ammonia, and as you can see here, in effect they've swapped places. You'll find that incomplete substitution can also occur with copper 2. So rather than a straight swap between the ammonia and the water here, we've got 4 of the water ligands swapping out for ammonia, as we see here. And in both of these examples, the coordination number, as we can see, remains 6. But if a larger charged ligand, such as the chloride ion, substitutes a smaller uncharged ligand, such as ammonia or water, it can cause a change in coordination number. So if we go from our small neutral water ligand, we replace with the chloride, we see a change in coordination number to 4. Whereas before with the monodentate ligands, we saw that they were molecules or ions with a lone pair of electrons that form a single coordinate bond with the transition metal ion. What about if you have bidentate or multidentate ligands? This time, these are molecules or ions with lone pairs of electrons that form 2 coordinate bonds with a transition metal ion. So good examples of bidentate ligands include ethane 1,2-diamine and ethane diorate. The multidentate ligands, exactly the same definition, but this time we have more than 2 coordinate bonds formed with a transition metal. This is an incredibly complex molecule, the EDTA4-. Be aware, in your exam you don't need to be able to draw it, thank goodness, but you do need to know that it can form 6 dative bonds and that it has a charge of -4. Now you'll be familiar with hemoglobin. It's a pigment found in our red blood cells. It actually contains heme, which refers to the fact that it contains an iron 2 complex with a multidentate ligand. Here, oxygen forms a coordinate bond to the iron 2 in heme, enabling the oxygen to be transported in our blood, which is used in respiration. The Fe2+ to O2 bond is weak, as oxygen is not a very good ligand, and this means that the oxygen molecule can be taken up easily by cells where it's needed in respiration. Ligands that form stronger bonds than oxygen bond irreversibly to iron 2, and this is actually the chemistry which explains why carbon monoxide here is so toxic. Because carbon monoxide is a ligand which forms a stronger bond to the iron, it binds preferentially to the iron 2 displacing the oxygen, meaning that a person effectively suffocates if they're exposed to too much carbon monoxide. Complex ions containing bidentate or multidentate ligands are called chelates. The substitution of monodentate ligands with a bidentate or multidentate ligand leads to a more stable complex, and this is known as the chelate effect. Now, the chelate effect occurs because the entropy, so the amount of disorder in the reaction, increases. As you can see, there are 2 moles on the left, 7 moles on the right. You can add that up. 2 moles versus 7. Now, our enthalpy change is usually small, as the number and type of bonds are similar in both complexes, so a positive entropy change is likely to lead to a negative Gibbs free energy, meaning that the reaction is spontaneous, it's feasible, and therefore the products are stable. Chelates can be used to effectively remove D-block metal ions from solution, so we can use EDTA to remove poisonous heavy metal ions from rivers. This occurs because the EDTA substitutes out the water due to the chelate effect. EDTA complexes are not toxic. So this is a very useful way in order to remove any poisons from river water. The concentration of copper-2 ions in a sample of water was determined to be this. This result was checked by titrating a sample of the water with a solution containing EDTA4- ions with a concentration of this. Calculate the volume of EDTA4- solution needed to react with 30 centimeters cubed sample of the water. The first thing we're going to do is find the amount of copper-2 ions present in the sample. We'll use the balanced symbol equation to calculate the number of moles of EDTA4- required to react fully with the copper-2 ions, and that will enable us to calculate the volume of EDTA needed. So we'll start by finding the number of moles of Cu2+ ions in the sample. So just pulling these numbers from the question. Just make sure that 30 centimeters cubed is converted to decimeters cubed to get a number of moles of 1.94 times 10 to the minus 6. We're now going to use stoichiometry to determine the moles of EDTA4- needed to react fully with the copper-2 ions. So we can see they react in a 1-to-1 ratio, so we can therefore infer that the number remains the same. And then lastly, let's find the volume of EDTA4- needed. And then the last step to convert that into centimeters cubed is multiplying by 1,000. Now we need to move on to the shapes of complex ions. It will remind you a lot of the V-separ theory we did earlier on in the course, so do bear everything you learned there in mind here. The first thing you need to be aware of is that transition metal ions commonly form octahedral complexes with small ligands such as water and ammonia. So you can see the coordination number here is 6. We have the octahedral shape. Do make sure you draw square brackets and include the charge if a charge is present. With larger ligands, you commonly get a tetrahedral complex with the transition metal ion present in the middle. You have your 4 ligands around the edge. This time you've got your chloride ion, which is a larger ligand when compared with water and ammonia. You'd expect your typical tetrahedral bond angle of 109.5. Very occasionally you get a square planar complex with larger ligands as opposed to the tetrahedral, such is the case with this cyanide ion. And here the bond angle is 90 degrees. The simplest shape is obviously linear with a bond angle of 180 degrees. This forms when you have silver as your transition metal ion surrounded by 2 ammonia ligands. Now, this particular complex ion here is actually Tollin's reagent, which remember is used to distinguish between aldehydes and ketones. Aldehydes reduce this complex ion to silver, a silver mirror. It's possible to get geometric isomerism with octahedral complexes. So in essence, the complex ion is the same. You have a cobalt transition metal ion located in the middle of our complex ion. You're going to have 2 different ligands. One of them is ammonia, one of them is water. Now, the way in which these ligands can arrange themselves varies, hence the presence of geometrical isomerism. In this case, the water molecules are located opposite each other. Remember, we learned when we looked at isomerism, this indicates that these are trans isomers, or E. They are enemies, they are on opposite sides. In this case, the water molecules are next to each other. They are on the same side, so they are Z or cis isomers, whichever you prefer. One of the most interesting cases of geometrical isomerism is if we consider the drug cisplatin, which is a cancer drug. Now, cisplatin is made up of platinum surrounded by 2 ammonia ligands, 2 chloride ligands. Now, if those chloride ligands are on the same side, as is the case of the Z isomer or the cis isomer, this is an anti-cancer drug known as cisplatin. However, if the chloride ions are on opposite sides, they are E isomers or trans, you'll actually find that this will have no therapeutic effect on someone suffering from cancer. And just to reiterate, geometric isomerism in complex ions requires 2 different ligands to be present, as we've seen in the last 2 examples here. Then it gets even more complicated. We're now looking at optical isomerism in octahedral complexes. Just to remind you, optical isomers are non-superimposable mirror images and are said to be chiral. Now, in order for optical isomerism to occur in complex ions, you require 2 or more bidentate ligands in an octahedral complex. Remember that bidentate ligands are molecules or ions with lone pairs of electrons that form two coordinate bonds with the transition metal ion. So here and here, here and here, here and here. This is obviously a super complex bidentate ligand. So actually we can use the two letters En to represent this entire bidentate ligand. And in the exam, it's perfectly okay to substitute this for En, as we can see here. Now the dotted line is supposed to represent, in effect, our mirror. So you can see that these are both mirror images of each other. They are non-superimposable mirror images. Now we've already pointed out that transition metals have formed coloured compounds, but now we really need to understand why. And it's all due to the splitting of the d orbitals into different energy levels. Because if you remember, what I taught you is that transition metals by definition have incomplete d orbitals, which means there'll always be at least one unpaired electron in their d orbitals. So just to remind you of an earlier part of the specification, we have selenium here. It's not a transition metal. This is the electron configuration of selenium, showing the electrons present in the various orbitals. So obviously we're talking a lot with transition metal elements about d orbitals. So I want you to see here, look, one of the reasons why selenium isn't a transition metal is because every single orbital is fully paired. Now the first thing to be aware of is that 3D sublevel. We know it consists of 5 orbitals, but the truth of the matter is that in the case of transition metal ions, when ligands form coordinate bonds with them, the metal d orbitals split into 2 energy levels, as we see here, as opposed to the more typical representation there. And because transition metals by definition have incomplete d orbitals, this means that there'll always be at least one unpaired electron in their d orbitals. So as a coordinate bond forms between the ligand and the transition metal ion, an electron is excited from the lower energy level, which we call the ground state, to a higher energy level, and that occurs due to certain frequencies of visible light being absorbed. But at the same time, remember, visible light is a spectrum. It contains lots of different colours. Any frequencies of visible light which aren't absorbed, they're transmitted. That's a chemistry term. In physics, you might have used the word reflected. These are the frequencies that correspond to a particular colour we see. So if a particular solution absorbs red but transmits green, the solution will appear green. Scandium and zinc we've met before, they're not transition metals, in part because they do not have a partially filled d orbital, so electrons therefore can't be promoted from a lower energy level to a higher energy level, and they can't transmit any colours. Now, there are certain equations that link the colour, wavelength and frequency of the light absorbed with the energy difference between the split d orbitals, and they are this first equation, which states the energy difference between split orbitals given in joules equals Planck's constant, which has a particular value, multiplied by the frequency of light, and that delta E again equals Planck's constant multiplied by the speed of light divided by the wavelength of light absorbed. And now going into greater detail about the colour of light you'd expect to see. The EM spectrum, remember, shows that the visible light consists of the following colours. Now red has the longest wavelength and therefore the lowest frequency, and it is lowest in energy. Violet at this end has the shortest wavelength, it's highest in frequency and highest in energy. And so the colour of a transition metal ion depends on the energy gap between the split d orbitals, delta E. The colour of the transition metal complex can be altered by changing the ligand, so swapping out ammonia for water, changing the coordination number and changing the oxidation state. Let's practice using the Planck constant now. I'm just writing down the equation there. Remember, this is the energy difference between split orbitals. This is Planck's constant. This is the frequency of light absorbed. When a d electron moves from the ground state to the excited state in a copper complex, the energy change is this. Here's Planck's constant. Calculate the frequency of the light absorbed. There's the final answer. A solution containing complex Fe3+ ions is placed in a colorimeter and found to absorb light of wavelength 490 nanometers. Here's your speed of light. Here's Planck's constant. calculate the energy in joules gained by each excited electron in the absorption at 490 nanometers. Here's our equation. This is your wavelength of light absorbed. This is Planck's constant. This is the speed of light. Just make sure that gets converted into the equivalent in meters. So that's 4.90 times 10 to the minus 7. Our final answer is 4.06 times 10 to the minus 19 joules. Variable oxidation states. As we've already mentioned, transition metals show variable oxidation states. For example, iron 2, iron 3, copper 1, copper 2, copper 3. The thing to be aware of here is that the transition metal compounds with high oxidation states usually act as oxidizing agents, and that makes sense really, because remember, oxidizing agents are by definition reduced, so that high oxidation state that they start with easily allows them to become reduced. A good example here is manganese 7 in MnO4-. We can work out the oxidation state. Oxygen is -2, which means that the manganese must be +7 to give the overall oxidation number of -1. Compounds with a low oxidation state are usually reducing agents. These are by definition oxidized. So again, that makes sense that they start at a low oxidation state. Here, iron 2 is starting at +2. The redox potential for a transition metal ion changing from a higher to a lower oxidation state is influenced by both pH and the ligand present. So we've got the oxidation states of D block ions moving from titanium to vanadium, chromium, manganese, iron, cobalt, nickel and copper. So as we can see, a huge variety in their oxidation states. The blue boxes indicate the most common oxidation states for each element. So titanium most often exists as titanium 4, vanadium exists as vanadium 4 and 5. Unfortunately, there's an awful lot of learning off by heart in this part of the specification, so I've listed the various transition elements as well as their species and the colour each of these species is. Remember, this is taken from my SwH Learning revision guide. So if we look at vanadium 5, this species is VO2+. You can check. Look, that will be -2. There's 2 of them, it's -4. The overall oxidation state is +1, so that's why that is +5. So you could do that for each of these species, practicing your oxidation states. Now the vanadium 4 exists as the VO2+ species. This is blue. V3+ is green. Vanadium 1, V2+ is violet. One thing to be aware of is that zinc in acidic conditions is a strong reducing agent, and that when zinc is added to vanadium 5, in acidic conditions, the colour change will go from yellow to blue to green to violet. So tracking down these various colours here, and that's because the vanadium is being reduced from vanadium 5 all the way down to vanadium 1. Iron 2 is more straightforward. Here's your complex ion. Iron 2 is green. You'll have met this when you were learning your various anion and cation tests. Remember, when you add sodium hydroxide to iron 2, you get a green precipitate. The same reaction this time with iron 3, you get a brown precipitate. What about chromium? Well, Cr2 is blue, Cr3 is red-yellow. Manganese now, manganese 7, MnO4- is purple, Mn2+ is pale pink, and then lastly cobalt 2 is brown, cobalt 3 is yellow. Like I said, you will need to learn these colours off by heart. I've already mentioned that Tollen's reagent is a complex ion which is used to distinguish between aldehydes and ketones. Remember that aldehydes reduce the silver in Tollen's reagent to solid silver. And here's an equation representing that reduction reaction, the addition of electrons in order to produce that solid silver. Because it's a redox reaction, you'll also get the oxidation reaction occurring with your aldehyde here. This is ethanol being oxidized to ethanoic acid. You could be asked to answer a redox titration calculations involving transition metals. This is a good example here. A 50 centimeters cubed sample of solution containing this complex ion was added 50 centimeters cubed of dilute sulfuric acid. It was made up to 250 centimeters cubed of solution in a volumetric flask. 25 centimeter cubed sample of this solution was titrated with this concentration of KMnO4. At the end point of the reaction, when the solution changes colour from pale green to pink, the volume of KMnO4 added was 16.50 centimetres cubed. We're being asked to calculate the concentration of iron 2 ions in the original solution, and here's our equation. So it does seem quite complicated. What we are going to start by doing is calculating the number of moles of KMnO4 that react. That will be quite straightforward, remember, because we're going to use this equation which states that concentration times volume equals the number of moles. Then we can use the stoichiometry in the equation to work out the number of moles of Fe2 plus ions present in the 25 centimeter cubed sample. And then we'll multiply that number by 10 in order to gain an idea of the number of moles of Fe2 plus in the original solution. And then we can finally sub our numbers back into here in order to find the original iron 2 concentration. But beginning at the beginning with the number of moles of KMnO4, just underlining the key numbers here, just dividing by 1,000 to get that into decimeters cubed. So we have 4.95 times 10 to the minus 4 moles of KMnO4. Now we're using the stoichiometry to work out the number of moles of Fe2 plus in the 25 centimeter cubed sample. So it's 1 to 5, so we need to multiply that number that we just calculated by 5. And then multiply it by 10 so that we know the number of moles present in 250 centimeters cubed of solution. And then our final step to find the concentration is to take that number of moles we just calculated and then divide by the volume given in the question as being the volume of the original sample, 50 centimeters cubed. So our final answer here is 0.496 as our concentration. Let's take another calculation now. So a 1.265 gram sample of this impure compound, which was dissolved in an excess of dilute sulfuric acid and made up to 250 centimeters cubed of solution, 50 centimeters cubed of this solution decolorized, 39.35 centimeters cubed of this concentration of potassium manganate 7. Calculate the percentage by mass in the original sample. Now this is the equation for the overall reaction. So our first step will be to find the number of moles of MnO4 minus that react. We'll then use the stoichiometry here to work out the number of moles of FeC2O4 present in the 50 centimeter cubed sample of the solution. We'll then multiply it up to find out the number of moles in 250 centimeters cubed of the original solution. And then we can just do some simple maths to find the mass of FeC2O4, and then we can use that to find the percentage by mass. So the number of moles of MnO4 minus, first of all. Now let's use the stoichiometry to find the number of moles of FeC2O4. So there's a 3 here, a 5 here, so we need to do 5/3 multiplied by the number of moles of the MnO4 minus. And then in a similar way to the question before, we need to multiply that up to find the number of moles present in the original solution, so we need to multiply it by 5. So close. So now let's find the mass. So we're doing MR times number of moles. You need to use your periodic table to find the MR of this. It will come out as being 179.8. And then finally, to find the percentage of the hydrated FeC2O4, we're going to do the mass we just calculated over the original mass, 1.265, times by 100 to get a final answer of 85.8%. An awful lot of learning things off by heart in this part of the specification. So the use now of transition metals as catalysts, that'll have come up frequently the whole time you've studied chemistry, right from when you were young. So remember that a catalyst, by definition, increases the rate of a chemical reaction usefully without being used up. How do they do this? By providing an alternative reaction pathway with lower activation energy. Remember, activation energy is the minimum amount of energy required for a reaction to take place. Now, there are two types of catalysts. The first one is heterogeneous. The second one is homogeneous. So a heterogeneous catalyst is one that is in a different phase from the reactant. So really that means a different state. They are usually solid, with your reactants being in either aqueous or gaseous state. The reaction occurs at active sites on the surface of the catalyst. Whereas a homogeneous catalyst, this is a catalyst that is in the same phase as the reactants, and the reaction proceeds through an intermediate species. The reason why transition metals can be used as catalysts is because, as we keep saying, they have variable oxidation states. The partially filled d orbitals can be used to form weak bonds with the reactants. This weakens the bonds within the reactants and holds the reactants close together in the correct orientation for the reaction. So looking in more detail how solid heterogeneous catalysts work, the reactants adsorb onto the active sites on the surface of the catalyst. This weakens the bonds in the reactants, lowering the activation energy, enabling the reaction to take place. The products desorb. This means that they leave the surface of the catalyst, and as you'd expect, the catalyst is left unchanged. What factors affect heterogeneous catalysts? Well, first of all, the strength of that adsorption. If the absorption to the metal is too strong, the products cannot be released. If the adsorption to the metal is too weak, the reactants are not brought together and the bonds are not weakened. Surface area is the second factor affecting heterogeneous catalysts. Increasing the surface area increases the effectiveness of a solid catalyst, and a support medium is often used in order to maximize the surface area and to minimize the cost. Now, poisoning may occur. This is when impurities in the mixture can poison the catalyst, blocking the active sites, reducing its efficiency, meaning that catalysts must be replaced, which can be very expensive. Let's look at a couple of examples of heterogeneous catalysts. The one you'll be more familiar with probably is the iron used in the Haber process, a reversible reaction used to make ammonia. Now remember that iron catalyst increases the rate of both the forward and reverse reactions equally. The catalyst is made more efficient by using powdered iron or a support medium to increase the surface area. In terms of these poisons, it's actually going to be sulfur compounds here which can poison the iron catalyst. The sulfur compounds strongly adsorb onto the active sites, blocking them, preventing the reactants from absorbing. And we can reduce this by removing impurities from the reactants before they pass over the catalyst. A second example of a heterogeneous catalyst is the contact process used to make sulfuric acid. Vanadium 5 oxide this time is used as the catalyst due to its variable oxidation states, and it works in two states. We can see the vanadium moving through from being +5 here to +4 here. It's been reduced, and then in the second stage it goes from +4 to +5. It's been oxidized. So overall, it's unchanged, and each of these two steps has a lower activation energy than the uncatalyzed single step, so the reaction is sped up. What about the use of Fe2+, this time as a homogeneous catalyst, one which is in the same phase as the reactants? So Fe2+ can be used as a catalyst in the reaction between I- and S2O8- ions. I'll show you the overall equation here. Now, the iron ions act as a catalyst because they have variable oxidation states and they are positive ions, so they attract the negative ions, and the catalyzed reaction occurs in the following step. So here's step 1. as you can see, the Fe2 plus remains unchanged, and what happens is the ions are providing an alternative reaction route with lower activation energy. Now the Fe3 plus ions we've also mentioned are as effective as the Fe2 plus ions in catalyzing the reaction, and that's because both steps 1 and 2 can occur in any order. The uncatalyzed reaction is very slow because the negative ions repel each other, so the activation energy is high. Autocatalytic reactions. Now, autocatalysis is when one of the products of the reaction then acts as a catalyst for the reaction. So that really is a very ideal situation. If we see this graph here on the y-axis, we have the concentration of reactants. Then we have time on the x-axis. As you would expect, the reaction starts slowly because we haven't produced any product yet that can act as a catalyst. But then as more of that product forms, as more of that catalyst forms, the rate of reaction increases. We see a steeper gradient, and then eventually that rate decreases as the reactants are used up. Now, a good example of this is the reaction between oxalic acid and acidified potassium manganate 7. This is the overall equation here. Now, the Mn2 plus product is what's going to be acting as the catalyst. Because it's obviously not present in the reactants at the beginning, the rate is slow, and a large part of that is due to these two ions being negatively charged and therefore repelling, leading to the reaction having a high activation energy. However, as the Mn2 plus forms, it can now act as a catalyst in the following two steps. The Mn2 plus obviously needs to be regenerated because after all a catalyst isn't used up, and it is the Mn3 plus being reduced to the Mn2 plus by C2O42 minus that does that. And then the Mn2 plus is then oxidized back to Mn3 plus by MnO4 minus. We can track this reaction using a colorimeter, and that's because we learnt the various colors, didn't we? MnO4 minus is purple, whilst all the other reactants and products are colorless. When a transition metal salt is dissolved in water, what happens is the water molecules surround the transition metal. The transition metal ions are surrounded by water ligands, and we call these aqua ions. How does the coordinate bond or dative bond form? It's the oxygen atom of the water donating a pair of electrons to form a coordinate bond with, in this case, copper. We see several other examples here. Don't forget that you need square brackets with your charge to represent that it's a 2 plus ion. Count the number of water molecules around the outside. There's 6. This means that the aqua ions are octahedral shaped here. And we even say that aluminium can form aqua ions despite the fact that aluminium isn't a transition metal. One thing to be aware of is that aqua ions with an M3 plus metal ion at the centre are more acidic than those with an M2 plus ion. Obviously, M stands for the transition metal or aluminium, so therefore the pH of Fe3 plus is approximately 1.5, whereas Fe2 plus is almost neutral. So what is the reason for that? In this case, Fe3 plus ions are smaller, more highly charged than the Fe2 plus ions, and therefore the Fe3 plus ions are more strongly polarizing. They weaken the oxygen-hydrogen bonds in the water ligands more, and then the water ligands can then more easily release a H plus ion into the solution, and it's that H plus ion which makes it more acidic. So the reason here explains why our M3 plus ions produce solutions with lower pHs compared with M2 plus ions, and fundamentally that's due to more H plus ions being donated. Now if a base which remember is a proton acceptor, is added to an aqua ion solution, it will remove H plus ions, protons from the complex ion, and the maximum number of protons removed is the same as the charge on the metal ion. We've given two examples here of bases which are capable of removing protons: the strong base sodium hydroxide, the weak base ammonia. Just have a close look at the state symbol. This particular substance will always be insoluble and produce a precipitate. The M3 plus ion can lose up to 3 protons until it forms a neutral compound. Just one thing on drawing convention, don't use square brackets here because we no longer have an ion. Now we have a summary of various transition elements plus aluminium. We've got their various aqueous ions. Remember, that's when you have the central metal ion surrounded by your water ligand. We've got the various colours they turn. If we start with ion 2, the complex ion of iron 2 forms a green solution. When reacted with sodium hydroxide, we've met this reaction before, it forms a green precipitate. If you add excess sodium hydroxide, you see no further change. How about when we add a weak base to our aqueous ion? This time you'll get a green precipitate. If you add excess ammonia, you get no further change. And if you add sodium carbonate to your aqueous ion, again you get a green precipitate. What about copper 2 now? So here's your aqueous ion, it's a blue solution. We react the aqueous ion with sodium hydroxide, we produce a blue precipitate. The addition of excess sodium hydroxide causes no further change. If you add ammonia, again you get a blue precipitate. This time when you add excess ammonia, you lose your precipitate and you end up with a deep blue solution. And if you add sodium carbonate, this time you get a blue-green precipitate. What about iron 3 now? So the iron 3 aqueous ion is a purple solution. If you add sodium hydroxide to iron 3, remember that's a test for that cation, you'll see a brown precipitate. Excess sodium hydroxide causes no change. If you add ammonia to that aqueous ion, you get a brown precipitate. The addition of excess ammonia causes no further change. And then lastly, if you react sodium carbonate with iron 3, you produce brown precipitate and that carbon dioxide gas is released. And now aluminium 3, this time you have a colourless solution as the aqueous ion. Reacting sodium hydroxide with the aqueous ion produces a white precipitate. Remember, when you add excess sodium hydroxide, that precipitate dissolves to form a colourless solution. Ammonia and the aqueous ion produces a white precipitate. And then lastly, the action of sodium carbonate with that aqueous ion produces a white precipitate and carbon dioxide. I know this looks stinky, but you probably already knew from GCSE and IGCSE, the green precipitate here for iron 2, the brown precipitate here for iron 3. If you did AQA GCSE, you'll have learned that aluminium produces a white precipitate with sodium hydroxide. And then at A level, we just need to add what happens with ammonia and sodium carbonate. So that was the summary table we looked at. Now let's look at the various equations, starting with iron 2. So we have our aqueous ion. We're adding that weak base of ammonia. Here's our product, and we're producing the NH4+. As we would expect according to our table, when we add ammonia, we get a green precipitate. So what about copper 2 now? Here's your complex ion. We've changed it up and we're reacting it with our strong base. Here's our product, and we produce water as a byproduct. We already knew that it would turn a blue precipitate here. What about iron 3? Reacting it with our weak base again, producing the ammonium ion. You'll see a brown precipitate here. And then finally our non-transition element, but we're still interested in how it behaves here when reacted with sodium hydroxide. It's going to produce a white precipitate. In these reactions, we can say that the ammonia and the hydroxide ions are acting as Bronsted-Lowry bases, which means that they're acting as hydrogen ion proton acceptors. If we look a little bit more now in depth, particularly here and here, where these are the actual only two reactions that occur with excess sodium hydroxide and excess ammonia. When excess sodium hydroxide is added to aluminium, you find that that white precipitate dissolves, hence why we have an aqueous state symbol here. When excess ammonia is added to copper 2, again, we see that precipitate dissolve, a deep blue solution is formed. And what's actually taken place is that in excess ammonia, ligand substitution occurs after ammonia has stopped acting as a base. That last column then, which dealt with the sodium carbonate solution reactions with aqueous transition metal ions. So we'll take our metal 2+ ions, such as iron 2 and copper 2. Here are example equations of them reacting with the carbonate ion. The iron 2, as anticipated, produces a green precipitate. Copper 2 produces a blue-green precipitate. And now the reactions of metal 3+ ions with carbonate solutions. Iron 3 produces the brown precipitate and that carbon dioxide gas. Aluminium 3 produces a white precipitate and again carbon dioxide gas. And remember that gas will be seen as effervescence, which is in effect fizzing. And just one thing else to point out is that the metal 3+ ions are acidic enough for the carbonate to act as a base and remove protons, but the metal 2 plus ions are not acidic enough and a metal carbonate is formed in a precipitation reaction instead. And so here, because of the 2 plus ions, that's why your product here is a carbonate, whereas up here with the 3 plus ions, your carbonate here is acting as a base, so you end up with a different product as we see here. Now, the amphoteric nature of aluminium hydroxide, now we've previously mentioned that it's amphoteric. This means that it can react with both acids and bases. Here's an example of it reacting with acids, hydrochloric acid, a strong acid, to produce this complex ion and chloride ions. This time we have the example of it reacting with a strong base, the hydroxide ion, to produce this complex ion and water. And then last up, before we look at past paper questions, ligand substitution reactions when an aqua ion, so that remembers when you have your complex ion surrounded by water, reacts with ammonia, there's no change in coordination number, and that's in large due to the fact that water and ammonia are both uncharged and similarly sized ligands, and therefore the shape remains octahedral. However, if you have your aqueous metal ion reacting with concentrated hydrochloric acid, there's a change in both charge and coordination number. And you go from, in the case of this complex copper surrounded by water ligands, you go from a pale blue solution to a yellow-green solution. Notice a change in coordination number. We go from 6 to 4, and that's because that chloride ion is much larger than the water, and therefore we see a change in shape from octahedral to tetrahedral with a bond angle of 109.5. And then if I haven't given you reason enough to get hold of my guide, this is a great summary. And you know what, you do need to learn every single stage, what's happening, the color changes, the various complex ions, and you'll see why when we look at some past paper questions now. This question is about iron and its ions. Discuss the role of iron as a heterogeneous catalyst in the Haber process. Your answer should include the meaning of the term heterogeneous catalyst, how iron acts as a heterogeneous catalyst, the factors that affect the efficiency and lifetime of the catalyst. It's worth 6 marks. These bullet points are super helpful, don't ignore them. Remember that a heterogeneous catalyst is in a different phase or state from the reactants. Let's define both words. So what is a catalyst? A catalyst speeds up the rate of reaction without being used up. By offering an alternative reaction pathway with lower activation energy. So how does iron act as a heterogeneous catalyst? Well, remember that the hydrogen and nitrogen involved in the Haber process adsorb onto the active sites of the iron. The products, which is the ammonia, deadsorb. And then what factors affect the efficiency and lifetime of the catalyst? Just going to summarize that. Surface area. You want to use powdered iron ideally. The lifetime can be reduced through poisoning. We mentioned that it was the sulfur doing the poisoning in the Haber process. Fe2 plus ions catalyze the reaction between peroxodisulfate 6 ions and iodide ions in aqueous solution according to this reaction. Explain why this reaction is slow before the catalyst is added, and give 2 equations to show how Fe2 plus ions catalyze this reaction. So the first thing to point out here is that the 2 reactants are negatively charged and therefore repel, meaning that the activation energy is high. Let's now write the 2 equations. So equation 1, remember you do have to do an awful lot of learning off by heart in the transition element part of the specification. Give a reason why Zn2 plus ions do not catalyze the reaction in part B. Remember I said that zinc and scandium aren't transition elements. The reason for zinc is because it exists only as the Zn2+. It doesn't have variable oxidation states. The figure below shows some reactions of iron ions in aqueous solution. Identify A and state its colour. So because this is a 2+ ion and we know that the ligands are neutral here for water, that means that's Fe2+. So remember, we just did this. If you react Fe2+ with that sodium carbonate, it's going to produce iron carbonate, and that is a green precipitate. Over here, we have Fe3+ reacting with sodium carbonate. That produces a brown precipitate. The formula is this, and they want the ionic equation for this. Explain why an aqueous solution containing the Fe3+ ion has a lower pH than that containing the Fe2+ ion. That's all to do with the size of the ion. So remember, Fe3+ is smaller than Fe2+. I then said that Fe3+ as a result is more polarizing. So more H+ ions are released, which lowers the pH further. Question 5, which shows the electron configuration of an atom of a transition metal. Remember, we define a transition metal as having a partially filled d orbital. Look down here, that has no electrons in the d orbital. These two are both full, which means that the answer here must be B. Which will not act as a ligand in the formation of a complex ion. So remember, ligands need to be able to donate a lone pair in order to form a dative bond. So it's important you know the structure of these various substances. So obviously the answer here is methane, because it doesn't have a lone pair. The other thing to be aware of, remember, is we've met water and ammonia loads as I was going through the content. They're both monodentate ligands. They're small and uncharged. We met carbon monoxide when we were discussing how it binds preferentially to red blood cells, preventing the transport of oxygen, and therefore is highly toxic. Which shows the correct oxidation state and coordination number of cobalt here. So just count how many ligands are attached. It's 5 + 1, so 6. And then the oxidation state, we know that this is neutral. So in effect, we're doing 0, which is the charge on the complex ion, minus the ammonia is neutral. That chloride ion is -1. Then we've got 2 chloride ions there. So it's in effect this, which gives us an oxidation state, therefore, of +3. The diagram shows some reactions of aqueous iron ions. Give the formula precipitate J and state its colour. We have Fe3+ reacting with sodium carbonate. We've already done this. We know that it's going to be a brown precipitate. Here's the formula. And then the equation is the same as before. Give the formula of L and an equation for reaction 2. This is FeCl4 minus another complicated equation. And then we want to suggest a reagent that will take our Fe3+ to Fe2+. From my table, we can see that it's zinc. Give the formula precipitate M and state its colour. So we're reacting this complex ion with ammonia. That's going to produce a green precipitate. Like I said, you simply have to learn these. I'm really sorry. It's super confusing. And then part E, transition metal complexes have different shapes and many show isomerism. Describe the different shapes of complexes and show how they lead to different types of isomerism. Use examples of complexes of cobalt-2 and platinum. You should draw the structures of the examples chosen 6 marks. So in essence, your answer here to get those 6 marks needs to be very similar to this part of my revision guide. Look, we've got the cobalt and the platinum examples here showing the geometric isomerism where the water molecules may be on opposite sides or the same side of that cobalt central metal ion versus our cisplatin and transplatin examples involving platinum, where, if you remember, it's only the cisplatin which has the therapeutic quality of being able to be used in the treatment of cancer. Do make sure to identify the various shapes of these complexes. So remember here, these are both octahedral, these are both square planar. And then if you really wanted to max out your answer, you could include optical isomerism shown here, where we subbed in an EN to represent this disgusting NH2, CH2, CH2, NH2 ligand. Do make sure you explain what optical isomerism is. Remember, these are non-superimposable mirror images, in this case in octahedral shaped transition metal ion complexes. Optical isomerism now. Now, optical isomerism is a form of stereoisomerism. Remember that stereoisomers have the same structural formulae, but a different arrangement of atoms in space. Optical isomerism is a very specific form of stereoisomerism. For optical isomerism to occur, you need 4 different substituents attached to one carbon atom. And remember, we call this central carbon atom a chiral center, or a chiral carbon. The result of this is that you have 2 isomers that are non-superimposable mirror images of one another. And these optical isomers are actually known as enantiomers. So how do we distinguish enantiomers from each other? A very key difference is that they rotate plane polarized light in opposite directions, which means it makes them optically active. An equal mixture of enantiomers is known as a racemic mixture, a racemate. Racemic mixtures have no effect on plane polarized light. We call them optically inactive, and that's because the rotation in opposite directions caused by each enantiomer is cancelled out due to the equal mixture of enantiomers. So how do we recognize chiral carbons and how do we draw optical isomers? We'll go through a variety of examples here. So we can see we have a chiral carbon here. The reason for that is we have 4 different groups attached. The hydroxyl group here, the carboxyl group here, we have C2H5 and CH3. Do notice that when we use the word group, we're not just referring to a single atom next to that central carbon, it's all the preceding atoms until we reach the end of the chain. Here we have a skeletal formula. This actually represents a structure with 2 chiral carbons. I'll highlight them here, 1, 2, because if you double check, you can see that each of these carbons has 4 different groups attached. Remember that we only show hydrogens in a skeletal formula that form part of a functional group, hence why that hydrogen is present here. So we've looked at 2 chiral carbon examples. Now to show you one which isn't a chiral carbon. Now, simply owing to the fact that this molecule is symmetrical, it means it can't have a chiral carbon. I'm going to use my highlighter again here to represent a chiral carbon here. Now, the 4 groups attached are a hydrogen, which again we can't see because of the fact that this is a skeletal formula. We have NH2, and then we have some really large groups of CH2, 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 CHOH, as well as CH2, CHOH. So we've mentioned that optical isomers are non-superimposable mirror images of one another, but how do we draw them? So I'll write a list of instructions here. Step 1 is draw the molecule in 3D, making sure that your chiral carbon is in the center. Your second step is to draw a mirror line. And then to draw the second enantiomer, you want to draw the mirror image of the molecule on the right-hand side. So I'm going to start by drawing my molecule in 3D with my chiral carbon in the center. So there's step 1. Now I'm going to do step 2, which is draw my mirror line as a dotted line. And now I'm going to draw the mirror image of that molecule nice and carefully. So how might you be asked about this in the exam? Well, you could be asked to deduce structures using optical activity. So here we have compounds A and B with this molecular formula. We know that A shows optical activity, B does not. Draw one possible structure for each of the species. So we'll start with A, which we know is optically active, which means it has by definition a chiral carbon with 4 different groups attached. So I'm going to start with my central carbon atom. I know I need to obey this molecular formula. So to explain why this structure here is optically active, we have our central carbon and then we have 4 different groups attached to that chiral carbon. We can see that we have CH3, hydrogen atom by itself, chlorine by itself, and then lastly CH2Cl. So here is our chiral carbon. It is optically active. And then what about the structure of B, which we know is optically inactive? So we need to arrange these atoms so that we don't have 4 different groups attached to that central carbon. So B is optically inactive. The easiest way to draw that is by drawing that central carbon and then immediately adding 2 identical groups, in this case 2 hydrogen atoms. This renders this structure immediately optically inactive because they are the same group, and then all I've done is make sure I fill up with the rest of the atoms to ensure that the overall molecular formula is correct. It's now time to turn our attention to 2 very closely related homologous series, the aldehydes and ketones. So the functional group of the aldehydes is CHO, CHO, and the functional group of the ketones looks like this. So as it's clear to see here, both contain the carbonyl C double bond O group. How do we go about naming them? We'll start with aldehydes. Aldehydes in most cases end in -al. For example, ethanal, propanal. Now, because the aldehyde has to be at the end of a carbon chain, as we see here, there's no need to put a number in when you go about naming them, because the carbon of the aldehyde is assumed to be carbon number 1. How about naming ketones? Well, ketones end in -one. If we take propanone and butanone, so this is propanone due to the fact that you have 3 carbons and the carboxyl group in the middle with 2 R groups attached. What about butanone? Now, because the carbonyl group for both propanone and butanone can only be on 1 possible carbon, a number is not needed here, but as you increase the length of the carbon chain, that's when you start introducing numbers into the naming convention. So for this larger structure, we need numbers to locate the carbonyl group in the chain. So we can see here that we have 5 carbons. The carboxyl group is on the 2nd carbon, so this is pentan 2-one. One thing to be aware of with the aldehydes, a slight change in their naming, is if you have an aldehyde attached to a benzene ring, which I'm drawing right now, this is known as benzene carbaldehyde, and we are using the suffix carbaldehyde as soon as a benzene ring is involved. let's look at the functional groups again of the aldehydes and ketones to try and understand how these various homologous series are going to react. Now we can see straight away that that carbonyl group is going to be strongly polar. We're going to have a delta positive carbon, a delta negative oxygen. And that means that there are permanent dipole-dipole forces between molecules. So these are stronger, remember, than van der Waals forces, London forces, but weaker than hydrogen bonds. And therefore, we can infer that aldehydes and ketones have a higher boiling point than similarly sized alkanes, but a lower boiling point than alcohols because they don't have hydrogen bonds. Alcohols, remember, are famous for having hydrogen bonds. We've looked previously at the fact that we can easily distinguish between aldehydes and ketones using Failing solution or Tollens reagent. This relies on the fact that aldehydes may be oxidized to carboxylic acids and therefore, if you have an aldehyde added to Tollens reagent, you get what's known as a silver mirror. No such reaction occurs with a ketone, and if you prefer, you can mention the Failings test, where you'll get a brick red precipitate in the presence of an aldehyde. Watch another video in order to actually see the chemistry behind this, because it is important, particularly with AS chemistry, that you know this. I just wanted to mention it here. So going back to this electron-rich oxygen and the electron-deficient carbon, what this means is that the electron-deficient carbon is readily attacked by reagents which have electron-rich areas, such as negative ions or compounds with lone pair of electrons, which remember we refer to as nucleophiles. So we're going to expect plenty of mechanisms here with aldehydes and ketones which involve nucleophilic addition. So I'm going to run you through the nucleophilic addition reaction using aqueous NaBH4 on, first of all, an aldehyde. So to remind you, here's our aldehyde functional group, meaning that this oxygen is electron rich, this carbon here is electron deficient. Do practice naming this aldehyde when you get the opportunity. 1, 2, 3, 4. We have 4 carbons. We have a methyl group on what is in effect the second carbon. So we have 2-methyl butanol. I'm going to rub that out so we can see what's going to happen in terms of the transfer of electrons. Now, you do need to be aware that the NaBH4 is super unusual, that it produces a hydride ion, H- ion, which has a lone pair of electrons in solution, which is acting as your nucleophile. So this electron-rich nucleophile is going to attack our slightly positive carbon, which causes one of the bonds in the C double bond O to break. So we're using curly arrows to represent that. We now have a lone pair of electrons on our oxygen, which is going to be attracted to an H+ ion. The H+ ion comes from either the solvent used or an acid added. Remember, our curly arrows always go from a lone pair of electrons or a bond. That hydrogen now adds itself as an alcohol functional group, a hydroxyl. And therefore, if we look at what we have here, again, we have 4 carbons in a row. We've got a methyl group, alcohol functional group. So the name of this is 2-methyl butanol. Remember to always look back at what's actually going on overall. So through the nucleophilic addition reaction using our aqueous NaBH4, the one that contains the hydride ion, we have reduced our aldehyde to a primary alcohol. Remember, this is a primary alcohol because the carbon that the alcohol functional group is attached only has 1 carbon adjacent. So overall, our aldehyde has been reduced to a primary alcohol. And if you want to write a summary equation, you can write this instead of the mechanism. There's CHO for our aldehyde. This represents our reducing agent. Let's do a similar mechanism now involving ketones and NaBH4. Again, it's going to be a nucleophilic addition reaction. We're going to be adding our nucleophile. There's our slightly negative oxygen, slightly positive carbon. Don't forget to use the opportunity here to attempt to name this ketone. We have 1, 2, 3, 4 carbons, so it's simply butanone. Now, let's get into our mechanism. So we're starting with our hydride ion with a lone pair of electrons acting as our nucleophile that's going to attack our slightly positive electron deficient carbon. And then very similar to what we did before, that lone pair on the oxygen is going to attack our hydrogen ion that's come from a solvent or the acid which has been added. What do we have here then? We have a alcohol again, but look, this carbon is now attached to 2 carbons, which means it's a secondary alcohol. What is its name? It's butantuol. Do be aware, I know we've already said it's a nucleophilic addition reaction, but it's because the carbon here starts with 3 groups attached, 1, 2, 3, and ends up with 4 groups attached, hence why it's an addition reaction. So to summarize, ketones are reduced to secondary alcohols. If we write the summary equation here, here's our reducing agent. Here's our secondary alcohol. And it's important to be aware that we can't reduce either aldehydes or ketones to tertiary alcohols. If you try and draw it out, it will never work. Formation of racemic mixtures from aldehydes and ketones. We're combining everything we've just learnt to do with nucleophilic addition reactions and how optical isomers involve the production of enantiomers, which are non-superimposable mirror images of one another. We're going to show how the products of these nucleophilic addition reactions produce a racemic mixture. So here I have a generic structure of a ketone. As always, we've got our slightly negative oxygen, our slightly positive carbon. I'm going to just use this to represent a nucleophile. I don't really mind which one it is because after all I'm using this to demonstrate how we can form racemic mixtures from aldehydes and ketones. Now what you need to be aware of here is that this carbonyl group is planar, and that means it can be attacked by a nucleophile either above or below. And it's this that creates the racemic mixture. I'm going to use my mirrored line. I'm going to draw my first isomer on the left, my first enantiomer. I'm showing that my nucleophile has added itself. Then I draw my mirror image over here to show my second enantiomer. And because our racemic mixture, remember, contains a 50-50 mixture of these 2 enantiomers, despite the fact that they rotate plane polarized light in opposite directions, their effects cancel each other out, so we say that the racemic mixture is optically inactive. Okay, so here's our aldehyde to begin with. This is propanol. It's got 3 carbons. Our nucleophile in this case is the cyanide ion. There's the all-important lone pair. Just be aware that we use KCN to produce our cyanide ion instead of another option, which is HCN. And the reason for that is because HCN produces a toxic gas. And the other issue is that HCN is a weak acid, meaning that the concentration of cyanide ions is too low, so the rate of reaction is too slow. So let's get underway then. The lone pair exists on the carbon. It's going to attack the slightly positive carbon here, causing the breakage of that bond. Due to this step here, we're obviously going to add our cyanide ion onto our original substance. The oxygen has gained a lone pair of electrons. So our next step is realizing that the fact that there's a dilute acid here means that we have H+ ions present, which that lone pair is going to attack from the oxygen. So to complete this structure, so in terms of naming this product, due to the presence of the CN here, we have a nitrile. Count your number of carbons, it's 4. Just be a little bit careful here, you need to write butane nitrile here. That E is essential, they will knock off a mark if you don't include it. And then obviously we have the OH here, so that goes at the front according to our IU-PAC naming convention. So that's 2-hydroxybutane nitrile. Now, one thing to be aware of here is this is a chiral carbon, and as is the case when aldehydes react in a nucleophilic addition reaction in this way, you actually produce a racemic mixture of enantiomers. I haven't shown all the wedges and dotted lines because it would get way too complicated. But remember, because of that carbonyl group being planar, the nucleophile can attack to either above or below, so it will actually provide a racemic mixture containing 2 enantiomers. Let's now take propanone and KCN and dilute acid. Again, that mechanism is going to be nucleophilic addition. Here's our cyanide ion, which attacks that slightly positive carbon, breaking that double bond. Exactly the same as before. The oxygen gains a lone pair and attacks the dilute acid's H+ ion. So we'll end up with a hydroxyl functional group up here. Let's name it. This bit represents nitrile. This is a methyl group on the second carbon. This is a hydroxyl group on the second carbon. So to name, it is 2-hydroxy, 2-methyl, propane, nitrile. And there's that all-important E again. Now, ketones will produce racemates, but propanone won't, and that's because it's a symmetrical ketone. So look, you can see that there. Now, these reactions on the whole are pretty useful, and part of the reason for that is because the carbon chain length is extended due to that carbon in the cyanide ion. Butanone is reduced in a 2-step reaction using NaBH4 followed by dilute hydrochloric acid. Write an overall equation for the reduction of butanone using this to represent the reductant. So we're going to start with a ketone. We know we're going to reduce it to a secondary alcohol as per the contents of my video. Let's write the formula of butanone. It's got 4 carbons. There's that ketone functional group. Here's our reductant. And now we need to write the formula of a secondary alcohol. Feel free to write out the displayed formula if you want to see how that secondary alcohol comes about. By considering the mechanism of the reaction, explain why the product has no effect on plain polarized light. So what I'm going to do here is I'm going to draw the mechanism just to show you really what's going on so we can understand, first of all, that enantiomers are formed, and then we'll go on to explain that despite the fact that those enantiomers are formed, that it has no effect on plain polarized light. So here's butanone. Here's our hydride ion with the lone pair that attacks the electron deficient carbon, breaking that double bond. Here's our oxygen with its lone pair. The lone pair attacks the hydrogen ion from the dilute acid. So here's our product, our secondary alcohol. And sure enough, we have our chiral carbon, we have our central carbon atom, which is surrounded by 4 different groups. So yes, we have 2 enantiomers which can form. And remember, that's due to that carbonyl functional group being planar, meaning that our nucleophile, the hydride ion, can attack either above or below. However, the 2 enantiomers that exist are formed in equal amounts. Remember, we call that a racemic mixture. And therefore, even though they rotate the plane polarized light in opposite direction, the rotation is cancelled out due to the presence of these enantiomers in equal quantities. Here's our full answer then, that will get us our 6 marks. The carbonyl compound, it's an aldehyde, I can see that straight away, reacts very slowly with HCN. Name and outline a mechanism for the reaction of the aldehyde with HCN. This is nucleophilic addition. With propanol. We have our cyanide ion with the lone pair that attacks that electron deficient carbon, breaking the double bond. Our oxygen gains a lone pair, which attacks the hydrogen ions also present. Here's our product. The reaction in part A produces a pair of enantiomers. Draw the structure of each enantiomer to show how they're related to each other. So I am going to start by drawing this in 3D. We add our dotted line to represent the mirror, and then we draw our mirror image super carefully. And as you'd expect to see, of course, because we have enantiomers, we have that chiral carbon with 4 separate groups attached. State and explain how you could distinguish between the 2 enantiomers. Plane polarized light is rotated in opposite directions. Give the IUPAC name of the product of the reaction in part A. So we're naming this. So notice we have the nitrile here that goes at the end. Count the number of carbons. Remember, we've gained an extra carbon, so we now have butane. Because it's a nitrile, we need to include that E. And then finally acknowledge the OH. It's on the second carbon, so we have 2-hydroxy butane nitrile. In practice, KCN rather than HCN is added to the carbonyl compound. Given that the acid dissociation constant for HCN is this, suggests why the reaction with HCN is very slow. So we're going to write that HCN is a weak acid. Remember, weak acids only partially dissociate, so the concentration of HCN in solution is very low. Meaning that therefore, the reaction proceeds at a very slow rate. Carboxylic acids and their derivatives. So starting with some background on carboxylic acids, remember they are what we call weak acids. Why is that? Because they only partially dissociate. Being acids, however, they show the typical reactions of acids. If you were to take a carboxylic acid such as methanoic acid and react it with a base such as sodium hydroxide, guess what? You get a salt. This is sodium methanoate. Plus water. If you were to react ethanoic acid this time with a carbonate, sodium carbonate, you're going to make your salt again, sodium ethanoate, plus water, and then due to that carbonate we're going to have a third product, carbon dioxide. Let's practice naming carboxylic acids and drawing their structures. Here's your functional group. That's your carboxyl functional group. This is the first carboxylic acid, I've already mentioned it, methanoic acid. The second carboxylic acid contains 2 carbons. It's obviously ethanoic acid, otherwise known as vinegar. So we can see straight away that carboxylic acids end in oic acid. Now, because the carboxylic acid has to be at the end of the chain, it does not require a number, so the carbon of the carboxylic acid is always assumed to be carbon number 1. Properties of carboxylic acids, they have characteristic smells. Not necessarily nice smells, but this one here, which is ethanoic acid, vinegar, obviously has a very distinctive smell. Now, carboxylic acids exhibit hydrogen bonding as their intermolecular force, which means they have a comparatively higher melting point compared with other molecules of a similar MR. And those hydrogen bonds which form with water means that the shorter chain carboxylic acids are soluble in water. Despite the fact that carboxylic acids are weak acids, they're still strong enough acids to react with sodium hydrogen carbonate. To show you an example, here we have ethanoic acid reacting with sodium hydrogen carbonate to form a salt, sodium ethanoate, plus water, plus carbon dioxide. And we can use this reaction to distinguish a carboxylic acid from other organic compounds which contain that OH, because you'll expect to see effervescence due to the production of carbon dioxide. Moving on to a derivative of carboxylic acids, the esters. Here's their functional group. Now, esters are made by reacting a carboxylic acid with an alcohol in a reversible reaction to produce an ester plus water. The fact that water is released means that it's a condensation reaction. You need a sulfuric acid or strong acid catalyst. Just to practice naming your esters and drawing them, I'm going to start with methanoic acid over here. I'm going to add ethanol. Now, to name the ester formed, the start of the ester's name comes from the alcohol, so it will be ethyl methanoate. In terms of drawing the ester, let's just highlight the fact that the OH of water comes from the carboxylic acid, the second H comes from the alcohol, and then stick everything else together. Now the short chain esters are fairly volatile, which means they readily turn into a gas. They have fruity smells, so they're often used in perfumes and flavourings. They can also be used as solvents and plasticizers. Acid hydrolysis of esters, so we're going to start with an ester in this case. This portion comes from the alcohol, this portion comes from the carboxylic acid. So if we were to hydrolyze it, which means adding water, we're going to produce, due to that C2, the alcohol ethanol. And the carboxylic acid, methanoic acid. So this is ethyl methanoate. The ethyl comes, remember, from the alcohol. The methanoate comes from the carboxylic acid. This is ethanol. This is methanoic acid. So there's our overall equation for the hydrolysis of an ester, ethyl methanoate, plus water produces ethanol and methanoic acid. The conditions you need to be able to list is that you're going to heat under reflux. And you need, again, a strong acid catalyst. What about base hydrolysis of esters? Practice working out where your carboxylic acid and your alcohol comes in. Here's your alcohol. Here's your carboxylic acid. We name it according to the alcohol first of all. That's only got one carbon, so this is methyl. This portion, the carboxylic acid portion, has two carbons, so it's methyl ethanoate. We're doing base hydrolysis, so I'm going to add a strong base, sodium hydroxide. And we're going to produce a salt, sodium ethanoate, plus methanol and alcohol. So overall, we have methyl ethanoate reacting with sodium hydroxide to produce a salt, sodium ethanoate, plus an alcohol, methanol. Now, if we're carrying out this hydrolysis with a warm solution of sodium hydroxide using distillation as our reaction condition, the reaction goes to completion. So we don't have a reversible reaction here. But that sodium hydroxide needs to be warm and aqueous. And if you add a strong acid such as HCl to our carboxylic acid salt, we will convert our salt to the carboxylic acid form. So in this case, it would be ethanoic acid. Formation and structure of triglycerides, which you need to think about as being a very special type of triester. Because if you think of the word triester, when you hear the word triglyceride, that will tell you straight away that yes, you're going to have an alcohol. It's going to be a triol reacting with a carboxylic acid. In this case, there's going to be 3 carboxylic acids, hence tri. You're going to produce your triester, which we call a triglyceride. And as always, you're going to produce water. There's going to be 3 waters produced. And it's going to take place in a condensation reaction, just as you would expect. So now let's give it context with the actual structures. First of all, our triol. Look, there are 3 OHs forming our alcohol functional group. fill up with hydrogens. Let's go about naming this from a UPAC point of view. 3 carbons means it's propane. 3 alcohol functional groups means that we write propane 1,2,3-triol, otherwise known as glycerol. What about these carboxylic acids now? Here are 3 carboxylic acids. Yes, the hydrogen numbers vary in each of the carboxylic acids, and that's due to a varying number of C double bond Cs present. Now let's draw our triglyceride. I'm just going to highlight where we're losing our water from. The hydrogen comes from the alcohol, the OH comes from the carboxylic acids, so then you stick together both ends of the molecules. Here are our ester linkages. This is triglyceride, plus 3 water molecules due to the 3 ester linkages that have been produced. Now, triglycerides are fats and oils which include glycerol molecules in their structure. So to zoom out, formation and structure of triglycerides, fats and oils, we're going to take a triol, propane 1,2,3-triol, known as glycerol. We're reacting it with 3 carboxylic acids. They're going to undergo a condensation reaction whereby 3 water molecules are lost and the 2 molecules join together as you'd expect with your ester linkage, losing the OH from the carboxylic acids and the H from the alcohols to form the water. Making soaps now, we're looking at the opposite reaction. So we're going to start with triglycerides. What's going to happen is we're going to use a strong base, sodium hydroxide, to hydrolyze those triglycerides. According to the following reaction, this will produce glycerol, so propane 1,2,3-triol, plus our all-important soap. Just be careful when you draw this. You need to show that you've got an ionic bond with your salt and not a covalent bond. So we have taken our triglyceride. We've used a strong base of sodium hydroxide to hydrolyze to produce glycerol and soap. The way in which soaps work is that the long hydrocarbon chains mix with the grease whilst the COO- mixes with the water. Last up, making biodiesel. Now, biodiesels are fuels made from organic compounds such as alcohols. So here we have methanol. Here's your triglyceride reacting with methanol in the presence of a strong catalyst. This is going to hydrolyze your oils again, and it will form glycerol, which you're more than familiar with by now, as well as your biodiesel, which you can see the biodiesel is made up of a mixture of methyl esters. Which compound is formed when phenyl benzene carboxylate is hydrolyzed under acidic conditions? Now, don't get confused by this nasty name. It's very similar to your other esters. Remember when you had something like methyl ethanoate? It's just that benzene in there that might confuse you, but everything else remains the same. So we're hydrolyzing an ester under acidic conditions. So we know we're going to make a carboxylic acid from the latter portion of the name and an alcohol from the former. So we're obviously picking between these two. So to help you work out whether the answer is A or D, I've drawn out the displayed formula of phenyl benzene carboxylate. So we can see straight away that here's our carboxylic acid end, here's our alcohol end. And if you look here, look, although we've got that benzene ring, you've got an extra carbon, which doesn't exist here. So that's why the answer here is D. Which compound is caused by acid hydrolysis of phenyl methyl ethanoate? So very similar to before, we've got our ester undergoing hydrolysis in the presence of an acid. This indicates that we have ethanoic acid as one of our products. I'm just going to look down and see if I can see that anywhere. No, so it's going to be my alcohol. So I've drawn the alcohol here that would be formed through the hydrolysis of phenyl methyl ethanoate using the phenyl methyl as a clue. So have a look, which option is that? It's option A. Coconut oil contains a triester with 3 identical R groups. This triester reacts with potassium hydroxide. Complete the equation by drawing the structure of the other product of this reaction in the box. Notice here you obviously have your triester reacting with your strong base. Here it's potassium hydroxide. You're expecting to make a salt as well as glycerol, which remember is propane 1,2,3 triol. Then it says name the type of compound shown by the formula RCOOK. That is a carboxylate salt. The use of this in industries to make soap. In a reaction to form biodiesel, 1 mole of vegetable oil reacts with an excess of methanol to form 2 moles of an ester with a molecular formula this and 1 mole of an ester with a molecular formula this. Draw the structure of the vegetable oil, clearly showing the ester links. You should represent the hydrocarbon chains in the form CXHY, where X and Y are the actual numbers of carbon and hydrogen atoms. Right, to show you how to answer this question, I've taken it upon myself to first of all show my methanol. There's one of my reactants. I know that it's going to react with 1 mole of a vegetable oil, which I'm being asked to draw the structure of. So I've actually put an X in there. And then we've been told what our products will be. Remember, when you form biodiesel, you are going to make glycerol, propane 1,2,3 triol, so I've drawn that out here. And then the rest of the product is made up of these 2 esters, 1 mole of an ester with this molecular formula, 2 moles of an ester with this molecular formula. To draw an ester, remember you will need that ester linkage. And then in terms of finishing your ester structure, just remember this side attached to the O will come from your alcohol, so that's why I know it's CH3. And then I just work it out based on the molecular formula, what I have left over here to complete my molecule. So that now means I'm ready to find the structure of my vegetable oil. So obviously X will be a triglyceride it's a triester containing 3 ester linkages. So here is the structure of the vegetable oil. Bear in mind, remember that hydrolysis has occurred, so that means adding water, breaking ester linkages here, here and here. And so you can therefore see where our glycerol structure comes from, as well as these ester structures, which are a combination of here and here. We're going to continue with our organic chemistry, specifically looking at that C double bond O. Specifically, what happens when you add an acyl group to another molecule, and that other molecule is a nucleophile. So acylation is the addition of an acyl group to another molecule, a nucleophile. Acylation is carried out using an acyl chloride or an acid anhydride. Let's draw the structure of an acyl chloride now. Here's your acid anhydride structure. I'm sure you can see straight away that we're going to have lots of areas which are electron rich and lots of areas which are electron deficient. So the chlorine and the oxygen of the acyl chlorides are obviously strongly electronegative. So the oxygen and the chlorine will both withdraw electrons from the carbon, rendering it slightly positive. And this slightly positive carbon is therefore easily attacked by nucleophiles. Again, here these oxygens of the acid anhydrides are electronegative, so they withdraw electrons from the carbon, meaning that again, the slightly positive carbon is easily attacked by nucleophiles. Remember that a nucleophile is an electron pair donor. The first mechanism we're going to look at is the nucleophilic addition-elimination reactions using acyl chlorides. Remember, we'll need a nucleophile as well as our acyl chloride. The acyl chloride I'm going to show you is ethanol chloride. So there's our ethanol chloride. Slightly positive carbon, slightly negative oxygen, slightly negative chlorine. Our nucleophile here is water. Has that lone pair that I just told you needs to be present on our nucleophile. That lone pair will attack that slightly positive carbon, causing the breakage of this double bond here. Now, as our nucleophile here is added, that's where the addition comes from, this chlorine is going to be eliminated, hence nucleophilic addition elimination is the name of this mechanism. So here's the addition of that nucleophile. So due to the breakage of this double bond here, this oxygen ends up with a lone pair of electrons and a negative charge. Our nucleophile here, the water, has added itself here, hence nucleophilic addition. This lone pair of electrons on the oxygen is going to move here in order to reform the double bond. And in doing so, this chlorine here will be eliminated, forming a chloride ion, which I'll draw shortly. So finally, we don't want our oxygen left with this positive charge here. So in order to do that, we deprotonate. So the electrons in that bond have gone to that oxygen, effectively neutralizing the positive charge. So to show you our product, by the time all these bonds have been broken and reformed, we'll have a double bond up here from the formation of the bond shown by this curly arrow, and then down here we'll have OH. After all, that chlorine has been eliminated as a chloride ion, which we see here. And then the H plus that's come off here will actually bond to our chloride ion, forming HCl gas. So let's name this. It's simply ethanoic acid. So I'm just going to show that forming as HCl gas, which is kind of problematic because remember that's toxic, which is why, as I'll show you very shortly, we prefer to do this reaction using acid anhydrides because it avoids the production of HCl gas. So in this example, we used water as our nucleophile. What about if we choose ethanol? We're starting with ethanol chloride again. Here's our nucleophile, ethanol. The lone pair is present on the oxygen. That's going to attack at our slightly positive carbon, causing the breakage of this double bond. The oxygen up here will end up with the lone pair. The ethanol will have added itself here. We don't want a negative charge on this oxygen, which means this lone pair will be donated here to form a double bond. Remember, carbon always needs to have 4 bonds. So if we're forming a double bond here, we're going to have to lose something. We're going to use the chlorine. We call this a good leaving group because chloride is a stable ion. So that breaks that bond there. And then we can't keep a positive charge on the oxygen, so we need to deprotonate. So this hydrogen here will leave. Our final product looks like this. We're going to have our carbon double bond oxygen. The chlorine's already left. So let's name everything. This was ethanol chloride. Here's ethanol. And here we have an ester, which is ethyl ethanoate. There's the ester linkage. Remember that the alcohol forms the first bit of the ester's name, and in this case the ethanol chloride forms the second part of the ester's name. So to summarise this second equation, we have our acyl chloride reacting with an alcohol to form an ester and hydrogen chloride gas. Let's write the summary equation. There's ethanol chloride. Here's ethanol. Our ester is ethyl ethanoate, and we're making hydrogen chloride gas. We're going to work our way through this nucleophilic addition elimination reactions using more examples of nucleophiles. So back in again with ethanol chloride. And just keep practicing these until you get used to drawing the mechanisms. I'm going to be using a nucleophile which is a weak base, ammonia. The lone pair exists on the nitrogen, It's going to attack our slightly positive carbon, causing the breakage of that double bond there. Our oxygen gains a lone pair. The chloride ion is our leaving group, so we need to see the breakage of this bond here in order for the chlorine to leave. The ammonia has added itself. Currently it has too many hydrogens, hence why that nitrogen has a positive charge. So we're going to deprotonate by breaking this bond here to draw a product now. Double bond O here, NH2 because we've deprotonated, and then we have left over that chloride ion again. So to name everything, ethanoyl chloride, here's ammonia, and the name of this substance over here is ethanamide. Now, in these solutions which do contain ammonia, what I find in this situation is that it's another ammonia molecule which removes this hydrogen here, forming an NH4 plus ion, and that's going to react with that chloride ion that left to form NH4Cl. Time for another summary equation. So this time we have acyl chlorides react with ammonia to produce amides. And as I was just saying, ammonium chloride will be our second product. So that's example 3. So the nucleophiles we've considered thus far are water, alcohols, ammonia, and now we're going to consider amines. So in our fourth example, we have our ethanoyl chloride again here. We are going to react with an amine. It has a lone pair on that nitrogen. We are going to attack our slightly positive carbon, causing the breakage of that bond here. Redraw everything carefully, showing that lone pair on the oxygen and the negative charge. We know that we're going to have a positive charge on this nitrogen, 2 hydrogens attached, plus our CH3. There's our leaving group, the chlorine. Let's add some curly arrows, showing the formation of that double bond there, the fact that the chlorine's leaving and that we are deprotonating. Final step to draw the product. We have formed what's known as an amide. Now, the amide functional group consists of C double bond O and an NH. So our summary equation now, we've got our acyl chloride reacting with an amine. It's going to form an N-substituted amide. And then because you've got excess of your amine, that's going to cause the deprotonation here. So you'll end up with an extra hydrogen, and that will combine with your chloride ion to form this salt here. Usually you're not asked to draw this comparative mechanism with an acid anhydride, just because obviously the acid anhydride structure is much more complicated. Just to show you this from my revision guide, we're using water here as a nucleophile. The lone pair on the oxygen attacks the slightly positive carbon, causing the breakage of this double bond here. We end up with our negative oxygen, as you would expect, with a lone pair. The electrons move from that lone pair to reform a double bond here. This becomes our leaving group. So that bond there will break, and then obviously we can't keep that oxygen as a positive charge, so we deprotonate, we lose that H+, the electrons are donated here. So our product is quite straightforward here to see. It's going to be ethanoic acid, obviously, but because this is our leaving group, every single time we'll be producing an ethanoate salt. And actually what happens is it reacts with H+ in solution to form another ethanoic acid in this particular example when water is your nucleophile. So here we are with a summary table. We can see our various nucleophiles, ammonia, amines, alcohols, and water. Here they are reacting with acyl chloride. These were the examples I drew out from a mechanism point of view. And here are the products that we make. We did the water one first of all, which remember made carboxylic acid and HCl gas. Then we moved on to the reaction with an alcohol, which produced an ester and HCl gas. Then we moved on to ammonia, and I said that we produced an amide, and then because of the excess ammonia causing the deprotonation to form an NH4 plus ion, that reacts with the chloride ion that was lost to form ammonium chloride. And then the last most complicated example, we formed an N-substituted amide as well as our NH3Cl, very similar to here. With acid anhydrides, although I didn't draw it out, you can see, look, you're going to produce the same products. So as I just showed you, if we now look at what happens with the acid anhydrides with water, we produce carboxylic acid and Your second product, due to the leaving group, will be another carboxylic acid. When an alcohol is your nucleophile, you'll produce an ester and a carboxylic acid. For ammonia, you'll produce an amide. And then lastly, your unsubstituted amide will be your product when you have an amine nucleophile. So although we drew all those mechanisms involving acyl chlorides, we looked at ethanol chloride time and time again, actually from a laboratory setting, we prefer to use the acid anhydrides such as ethanoic anhydride. The reason for that is because it avoids the production of those HCl gas fumes. So remember I said you get ethanoic acid as a byproduct, which is obviously much safer. In terms of the reactant, ethanoic anhydride is much cheaper, much less corrosive than the comparative acyl chloride. But one advantage of acyl chlorides is they react faster and they produce a purer product, so sometimes they'll still be used in industry. And then a very particular example of this mechanism is used in the manufacture of aspirin, which is a common drug used as a painkiller and blood thinner. It's again made using the nucleophilic addition-elimination reaction. So here you're using an acid anhydride, it's ethanoic anhydride. It's reacting with salicylic acid, which is acting as your nucleophile due to the lone pair of electrons on this oxygen here. So as you can see, this salicylic acid has added itself. We haven't drawn the mechanism, but you can see how this would be your leaving group. Obviously, being symmetrical, it doesn't matter which side we pick as our leaving group. So that produces our ethanoic acid, which we said was a safer byproduct, and the rest of the molecule has attached itself here. The reactions of molecules containing the chlorine atom are often affected by other functional groups in the molecule. Consider the reaction of this compound and this compound with ammonia. For the reaction of the first compound with ammonia, name and outline the mechanism and name the organic product. Okay, so this is obviously an acyl chloride. Ammonia is our nucleophile with our lone pair of electrons. Let's start by naming the mechanism. Remember, it's nucleophilic addition, elimination. Okay, so here's our acyl chloride drawn out. Let's label our slightly positive carbon, slightly negative oxygen and chlorine. We'll add ammonia now with its lone pair. It's acting as our nucleophile, which will attack the slightly positive carbon, causing the breakage of that double bond there. To draw the intermediate step, we're going to have a lone pair on that oxygen. Chlorine will become our leaving group. We're going to have a positive charge on that nitrogen plus 3 hydrogens. Time to add more curly arrows. Here's the formation of that double bond. Chlorine becomes our leaving group, and then we deprotonate right here in order to neutralize that positive charge. So we're ready to draw a product. Don't forget to name the organic product. We have 3 carbons, it's an amide, it's propanamide. Name and outline a mechanism for the reaction of this with another acyl chloride, name the amide formed. Nucleophilic addition, elimination. Here's our nucleophile, breaking that double bond. Double bond forms there. Chlorine is our leaving group. Deprotonation occurs. What is the name of this? Well, it's an N-substituted amide, N-ethyl propanamide. So the propanamide bit comes from the 3 carbons here. The N-ethyl comes from here. Butyl ethanoate is used as a solvent in the pharmaceutical industry. Write an equation for the preparation of butyl ethanoate from an acid anhydride and an alcohol. I'm just going to draw this out so you can see it more clearly. Remember, this bit comes from the alcohol, so that will therefore be butanol, butan-1-ol. And then this portion here comes from your acid anhydride, which is going to be the ethanoic anhydride. Don't forget you make ethanoic acid as your byproduct. So I'm just going to write that in terms of how you would put it in your exam. There's butan-1-ol. Here's your acid anhydride. Name and outline a mechanism for the reaction of this acyl chloride, ethanoyl chloride with methanol to form an ester. Nucleophilic addition, elimination. Draw ethanoyl chloride. That lone pair will attack here. Aromatic chemistry, and what this really means is that we're dealing with benzene rings. What is the molecular formula of benzene? Well, it's C6H6. And this benzene ring consists of a flat regular hexagon of carbon atoms, each of which is bonded to a single hydrogen atom. So how was the structure and shape of the benzene ring determined? Now, the structure and shape of the benzene ring went through many iterations, and as we can see here, at first it was proposed that benzene had alternating double and single bonds, which we called the Kekulé structure. As you can see, the position of the double and single bonds varied. However, by comparing thermodynamic data, it was discovered that in actuality, each carbon had 3 covalent bonds. As you can see here in the displayed formula, look, each carbon has 3 covalent bonds. And then remembering the fact that usually carbon forms 4 bonds, by only forming 3 covalent bonds, the spare electrons in a p orbital overlap to form a delocalized system, and we show this delocalized system as a circle in the middle. Benzene has a planar structure where the carbons are arranged in a hexagon, and all the carbon bonds are of an equal length. So although we usually draw it as a skeletal formula, such as the case here, where we don't show the hydrogens, in my guide here we can see a displayed formula showing each of the carbons bonded to one hydrogen, which allows the molecular formula C6H6. The bond angle we see here is 120 degrees. But what about the length of these carbon-carbon bonds? Although we know that they're an equal length, how do they compare to carbon-carbon single bonds and carbon-carbon double bonds? Well, you can see here that they have an intermediate length compared with the single and double bonds. But how did they actually realize the structure of benzene? Well, obviously we wanted experimental data. So evidence was found using hydrogenation enthalpies. And actually what was found was that the delocalization of those electrons in the benzene ring leads to a more stable structure with lower hydrogenation enthalpies. So here we have cyclohexene with a single double bond. It's been hydrogenated in the presence of a nickel catalyst. And here our hydrogenation enthalpy is minus 120 kJ per mole. With cyclohexane 1,3-diene, we've got 2 double bonds. We're hydrogenating again, and this time we've got a lower hydrogenation enthalpy of minus 163 kJ per mole. And one thing that's interesting about this data is obviously we only have 1 double bond here. Well, usually we'd expect as soon as we introduce 2 double bonds to have a value which was effectively double that, so minus 240. But in fact, it's only minus 163, so less than double that of cyclohexene, and that's because the alternating double bonds allow some delocalization of electrons. And then lastly, if we look at the benzene ring here, where we have delocalized electrons around the whole ring, look at our enthalpy value here of minus 208 kJ per mole. If that original Kekulé structure I showed you of cyclohexo 135-triene was correct, so if this structure here was correct, you would expect that enthalpy value to be 3 lots of minus 120 to give us minus 360. But actually the value is only minus 208, showing that the benzene ring is more stable than our Kekulé structure of cyclohexane 135-triene. Which means there must be delocalization of electrons. And in this diagram here, we're comparing them fully. Here's the Kekulé structure, and if that were the correct structure of benzene, we would have expected that enthalpy value to be minus 360. We can see that it's actually only minus 208, so it tells us that it's more stable, and that is due to the delocalization of electrons in the overlapping p orbitals. So how do we go about naming aromatic compounds, ones which contain benzene rings? So obviously we'll start here with our classic benzene ring, showing our delocalized electrons. What about if I were to add a halogen such as chlorine? Then this would be chlorobenzene. I'm going to swap out the chlorine now for a methyl group. You've guessed it, this is methyl benzene. Let's add some spice now with 2 groups, so 2 chlorines. As always, we want to number the carbons to keep the values as low as possible. So I'm just going to call this carbon number 1, 2, 3, 4, 5, 6. So here we have 1, 4 because it's on the first and fourth carbon, di, meaning 2 chlorobenzene. I've switched out those chlorines now for methyl groups. What do we have here? Well, we have 1, 2 dimethyl benzene. What about this example? Okay, so the NO2 is nitro. It's present on the first and third, so it's 1, 3 dinitrobenzene. Okay, well, what about our reactions with benzene? Let's understand what this delocalized ring of electrons is going to confer in terms of the way in which benzene reacts. So obviously this delocalized ring in benzene produces an area of high electron density, which will therefore attract electrophiles. Remember that an electrophile is an electron pair acceptor. The other thing to be aware of is that these aromatic rings are very stable, and as a result they require lots of energy to break, and this does actually mean that the ring almost always remains intact in the reaction of aromatic compounds. So that means you'll see that ring remaining throughout. Due to all of these things, we can say that reactions with benzene involve electrophilic substitution reactions. I'm going to show you 2 electrophilic substitution reactions now. First of all, the nitration of benzene rings. As I've already said, that mechanism is electrophilic substitution. So what is acting as our electrophile here, our electron pair acceptor? It's going to be NO2+. And how do we produce that NO2+? By reacting concentrated nitric acid and concentrated sulfuric acid. So here's the equation for that reaction between sulfuric acid and nitric acid. Now actually what's happening here is the nitric acid is acting as a base, the sulfuric acid is acting as an acid. We can see that because the sulfuric acid has donated an H+ ion. So I'm going to highlight our electrophile here that has been generated. We're ready to draw our mechanism. So obviously starting with our benzene ring, here's our electrophile. So the first step is an electron pair from the delocalized system of our benzene ring attacks the NO2+ ion. So we draw a curly arrow to show that. So here you've broken the delocalized ring of electrons. Remember that each of the carbons in the benzene ring is attached to a hydrogen, so I'm just going to show you that hydrogen there because it is important. We need to transfer electrons back into our delocalized system from our CH bond, hence the relevance of this hydrogen here. And therefore our product looks like this, with a H+ left over. Now that H+ can react with our HSO4 to regenerate our sulfuric acid, so therefore sulfuric acid is acting as a catalyst because it remains unchanged by the end of the reaction. One thing to be aware of is that this NO2 group can be reduced to an NH2 group by using the reagents tin and HCl, and we'll look at this in much more detail later on in the spec. And then the second type of electrophilic substitution reaction I want to show you, involving benzene rings, is known as Friedel-Crafts acylation. Obviously we need another electrophile. This time it's going to be RCO+. And how do we produce the RCO+? By reacting an acyl chloride with an aluminium chloride catalyst. So here's ethanoyl chloride. Here's aluminium chloride. And that's generating CH3O+, our electrophile, plus AlCl4-. Let's show a mechanism now involving the CH3O+. Here's our benzene ring. The way in which this mechanism works is that obviously with this delocalized ring here, we have a high electron density, so it's able to attack this positive carbon. So we use this to represent the fact that some of those electrons have been lost. I'm going to add in that hydrogen again, which remember is attached to that carbon. Everything else remains the same as the last mechanism I drew. And then obviously we need to recomplete the delocalized rings, so we're donating electrons from this bond. Now the H plus generated can react with AlCl4- to form HCl plus AlCl3, and so we have regenerated our AlCl3. So again we can make the comment that the AlCl3 is acting as a catalyst. Consider the following reaction sequence starting from methyl benzene. So what's happening here is that we are producing an aromatic amine. It's aromatic because it has a benzene ring. It's got NH2, so it's an amine. And we're producing it in 2 steps. Remember, this first step involves this electrophile. Mechanism 1, electrophilic substitution. Now in the reaction 2, we have compound J being formed by reduction. There's our clue. So give a reducing agent for this reaction. Remember I said it was tin and hydrochloric acid. Write an equation for this reaction. So starting with this substance here, here's our reducing agent. And remember we produce water. And it says give a use of J, and we said it was used in the manufacture of dyes. In an experiment starting with 5.05 grams phenylamine, 4.82 grams of purified product were obtained in step 1. Calculate the percentage yield of this reaction. Give your answer to an appropriate number of significant figures. So the first thing we want to do is find the MR of this product. 135. The MR of phenylamine was 93. Let's find the number of moles of phenylamine. So that's mass divided by MR. Looking at the equation, we therefore know the number of moles of the product expected was this. So now we can find its expected mass by doing that number of moles we calculated times by the MR we just calculated. So now we're ready to find the percentage yield, which is the actual yield, which they told us was 4.82, divided by the theoretical yield times by 100. So final answer is 65.8%. A reagent for step 2 is a mixture of concentrated nitric acid and concentrated sulfuric acid, which react together to form a reactive intermediate. So I know that that reactive intermediate is the nitronium ion. So I know that together nitric acid and sulfuric acid, nitric acid acting as a base, sulfuric acid acting as an acid, it's going to produce that nitronium ion, which we can see attached here. So we want the equation taking this as our reactant with the NO2 plus and producing this and an H plus ion. What is the name of this mechanism? Well, this was the generation of our electrophile, so it's electrophilic substitution. Suggest the type of reaction occurring in step 3. This is hydrolysis. Identify the reagents used in step 4. From here, we are carrying out a reduction process, and so in order to do that, we need tin and hydrochloric acid. Benzene reacts with ethanoyl chloride in a substitution reaction to form this. The reaction is catalyzed by aluminium chloride. Write equations to show the role of aluminium chloride as a catalyst in this reaction. Outline a mechanism for the reaction of benzene. Name the product. So this, remember, was Friedel-Crafts acylation. So we know that aluminium chloride is acting as a catalyst, so we do need to reform that. Let's draw the mechanism for the reaction of benzene. So here's our benzene ring. The CH3O+, we now need to reform that delocalized electron system using the electrons from the CH bond. So we're talking about that bond there. And here's that H+ ion, which reacts with the AlCl4- to form HCl, and it regenerates the AlCl3, which is important, seeing as we know that that's acting as a catalyst, so it can't be changed by the end of the reaction. Let's name the product. This product here is phenylethanone. Moving on to amines. Now, amines are compounds based on ammonia, which remember is NH3, but what you find is that the hydrogen atoms have been replaced with an alkyl group, so carbon and hydrogen, or aromatic rings, so we're building on our chemistry relating to benzene. Primary, secondary, tertiary amines. So the primary, secondary and tertiary refer to the number of R groups on the nitrogen atom. So if we start with ammonia, which we know is our core structure, let's draw the structure of a primary amine. And according to my definition, primary amine has one R group on the nitrogen atom, as we see here. What about a secondary amine? We're now going to have two R groups attached to that central nitrogen atom. And here's our tertiary amine. And then very closely related, we have our quaternary ammonium salt, which you're probably already aware has a positive charge. To reiterate, so amines we know are compounds based on ammonia, NH3, but the hydrogens in ammonia are replaced with either alkyl groups or aromatic rings. So our primary amine has a single R group attached, the secondary amines has two R groups attached, tertiary has three, and here's the structure of a quaternary ammonium salt. Now we're going to practice naming our amines. So here we have our core ammonia, one of our hydrogens replaced with CH3, CH2, 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 so we know it's a primary amine. What is the name of this? It's butylamine, due to the fact we've got 4 carbons. So we can see that the suffix amine is used when naming amines. Introducing an aromatic compound now, obviously benzene. So we have our core N. We've got a primary amine again, where one of our hydrogens this time is replaced with benzene ring. An aromatic ring in this case is given the prefix phenyl, so this is phenylamine. Now we've replaced a second hydrogen with an alkyl group. We've got 2 methyl groups, so that's why we need to write dimethyl amine. Dimethylamine. Our most complex structure now. Now remember that table I showed you, it's a list of functional groups in order of their priority. Now here we have higher priority functional groups present, and therefore the amine is given the prefix amino. So we need to look at our longest carbon chain, it's 3. With this carboxylic acid, it's propanoic acid. If I number the carbons, we've got carbon number 1, carbon number 2, carbon number 3. This OH from the alcohol functional group is in effect on the 3rd carbon. So in terms of naming, we're going to write 2 amino, that's this bit, 3 hydroxy, this portion, propanoic acid. And then a few extra points here. Because the amines are based on ammonia, we know that they have a trigonal pyramidal shape with bond angles of 107 degrees. Primary and secondary amines here can form hydrogen bonds due to the presence of that highly electronegative nitrogen. And due to those hydrogen bonds, they have higher boiling points than similarly sized alkanes, but lower than similarly sized alcohols. And that's because nitrogen is less electronegative than oxygen, so therefore the hydrogen bonds formed with primary and secondary amines are weaker. Short chain amines are soluble in water due to the formation of those hydrogen bonds, and unpleasantly, amines have fishy smells. Preparation of aliphatic amines using halogenoalkanes and ammonia. So the first thing you'll want to know is what an aliphatic amine is. These are amines that do not contain an aromatic ring, so no benzene. Now, primary aliphatic amines are produced by reacting halogenoalkanes with ammonia. What type of mechanism is it? It's a nucleophilic substitution reaction. I'm going to draw out the mechanism right now. So we'll take a halogenoalkane chloroethane, 2 carbons, there's the chlorine. We've said that we're reacting ammonia, so I'm going to pop that in here. Remember that ammonia has that lone pair. Due to the chlorine and the carbon, it will leave that carbon electron deficient. The chlorine will be electron rich. Our lone pair will therefore attack at this electron deficient carbon, causing the breakage of this bond. Let's add on that ammonia. Obviously, because that ammonia has the electron pair, it's acting as a nucleophile. But what happens next up is obviously we need to remove that positive charge on the nitrogen. So we need ammonia again, but in this case, the ammonia is going to act as a base because it's going to accept a proton in order to neutralize that charge. So there's our primary aliphatic amine. The name of this is obviously, we've got 2 carbons. I just taught you that we're going to add amine to the end as a suffix, so it's ethylamine. And then don't forget your salt product. Now, the primary amines produced can also act as nucleophiles, and this means that they can react with halogenoalkanes to form secondary amines via nucleophilic substitution. So we in effect take our halogenoalkane, the primary amine produced in the first reaction, and use the lone pair on that nitrogen to act as a nucleophile. So if we look at this nucleophilic substitution reaction, we've produced a secondary amine and a salt, and then the reactions continue with the secondary amine produced reacting with halogenoalkanes to form a tertiary amine. And then finally, those tertiary amines can react with halogenoalkanes to form the solid quaternary ammonium salts. Now, the result is a mixture of primary, secondary, and tertiary and quaternary ammonium salts, and we can separate these products using fractional distillation. And if we want to improve how much primary amine we produce, we should use a large excess of ammonia in order to force the ammonia to keep reacting to produce the primary amine, as opposed to moving through the secondary, tertiary, and quaternary ammonium salts. We can also produce primary amines through the reduction of nitriles. Now, primary alkyl amines can be prepared from halogenoalkanes in a 2-step process where the halogenoalkanes react with KCN in aqueous ethanol by nucleophilic substitution to form a nitrile. And then those nitriles can be reduced to primary amines using a hydrogen nickel catalyst. This gives a purer product than the halogenoalkane and ammonia method because you're not going to go through the primary, secondary, tertiary amine route. You're only going to produce the primary amine. However, a big disadvantage is that toxic cyanide is used. But look, here's our primary amine being made. Obviously, because of the cyanide containing the carbon, we're going to end up with a carbon chain of the amine where there's 1 extra carbon compared with the starting substance. Previously, we met this point in the specification, which was to do the electrophilic substitution reactions of benzene. And what we did was we made an NO2 plus electrophile by reacting concentrated nitric acid and concentrated sulfuric acid. Remember, we said that the sulfuric acid was acting as an acid because it donates a proton. The HNO3 is acting as a base. Now, the result of that is it produces the nitronium ion, which is acting as our electrophile, so our lone pair acceptor, and we said it would react with aromatic rings. We're now going to build on that by stating that we can build aromatic amines, so amines which contain a benzene ring, such as phenylamine, through the following 3-step process. So step 1 is reacting our concentrated sulfuric acid with our nitric acid in order to generate our NO2 plus electrophile. Step 2 is using that NO2 plus electrophile and making it react with benzene according to the following mechanism. Here's our benzene ring, our aromatic hydrocarbon. Here's our electrophile, using arrows to represent the movement of electrons. Remember, we need to reform our delocalized electron system using electrons from the carbon-hydrogen bond. So there's the carbon-hydrogen bond. The NO2 joins here, and then our final product, because we lose that hydrogen, looks like this. And we have a spare H plus ion. So this is nitrobenzene. And then our final step, step 3, is to reduce our nitrobenzene to phenylamine. Again, something I've mentioned before, using tin and hydrochloric acid as the reducing agent. According to the following reaction, here's our nitrobenzene. The tin and hydrochloric acid form hydrogen, which acts as our reducing agent. And here's our phenylamine product. Now these aromatic amines, the aromatic, remember, because they contain a benzene ring, are used to manufacture dyes. Here's our nitrobenzene. Here's our phenylamine. Let's look at our overall equation. Always looking at the overview. This is how we make aromatic amines, so amines involving a benzene ring such as phenylamine. The first step, remember, was taking our sulfuric acid acting as an acid, the HNO3 acting as a base in order to generate our NO2 plus electrophile. Here's the mechanism that I drew out showing the formation of nitrobenzene. Then we need to reduce that nitrobenzene to phenylamine using tin and hydrochloric acid, and here's the overall equation. So more information now. Amines are weak bases. Remember that you'll have that lone pair of electrons on the nitrogen that can attract a proton, and the strength of its ability to act as a base depends on the availability of the lone pair on the nitrogen. So alkyl groups release electrons towards the nitrogen atom, and this makes the lone pair on the nitrogens more available, so actually that makes them a stronger base, and we call this an inductive effect. Now secondary alkyl amines, ones containing two alkyl groups, are stronger bases than primary alkyl amines with one alkyl group, which are stronger bases than ammonia because they have no alkyl groups. And that's because the alkyl groups, as we've just said, release electrons towards the nitrogen. So obviously the more R groups you have attached, the more the electrons will be released towards the nitrogen atom. Ammonia with no alkyl groups will therefore be the weakest base. However, one thing to be aware of is that tertiary alkylamines are not stronger bases than secondary ones, and that's due to them being less soluble in water. So it just goes a little bit against what we just said here. So if we look, diethylamine with its two alkyl groups is a stronger base compared with ethylamine, which is a primary amine, versus ammonia, which is the weakest base. And that's all due to ethylamine having a greater inductive effect, and then again a greater inductive effect here. The aromatic rings, the aryl groups, withdraw electrons from the nitrogen atom. An aromatic ring next to a nitrogen atom will cause the lone pair to delocalize the rings. What this does is it makes the lone pair less available, so makes the substance a weaker base. And if we look at these various structures, we know that we're having a positive inductive effect here with our primary amine due to the presence of that carbon-hydrogen chain, making the lone pair on the nitrogen more available. We've got a different layout here. Now here, the aromatic ring, the aryl groups, will start withdrawing electrons from the nitrogen atom in this direction. The electrons from the alkyl groups over here will be releasing electrons towards the nitrogen atom. So if you think about these two effects, they are acting in opposite directions, so they'll actually cancel each other out. And then finally, phenylamine is a very weak base, and that's because of this, the fact that you don't have alkyl groups and the fact that you have your aryl groups, your aromatic ring, actively withdrawing electrons from the nitrogen atom, making that lone pair of electrons less available. I'm now going to draw all the mechanisms for the various reactions. Remember, we are going to be reacting a nucleophile such as ammonia primary amines, secondary amines, tertiary amines with halogenoalkanes, and we'll be drawing the products that can be produced. These are all examples of nucleophilic substitution reactions. Let's take our first example of chloroethane reacting with ammonia. So you'll have seen this before, but it's the most straightforward example. Our lone pair on our nitrogen attacks the slightly positive carbon, causing the breakage of this bond. Then we have a second ammonia molecule acting as a base because we need to deprotonate here to remove that positive charge, leaving us with this salt. Now remember what I was saying is that this product here, which is ethylamine, can act as a nucleophile too due to the lone pair on this nitrogen. So to make sure that we are making as much primary amine as possible, as opposed to that primary amine getting involved in the further reactions, what you want to do is use excess ammonia. So use excess ammonia to increase the yield of that primary amine. Let's name some things. So that's obviously chloroethane. This is ethylamine. If we didn't have excess ammonia, however, let's actually look at what can happen now. If we take our ethylamine and react it with chloroethane, very similar, just looks slightly more complicated, but our lone pair will attack again at that electron deficient carbon, causing the breakage of this bond. Obviously, our next structure is going to be quite complicated. However, it remains the same that we need to deprotonate that nitrogen. I'm not going to draw this acting as a base here because it makes it really complicated, but remember that deprotonation will look like this. So what's the name of this? It's diethylamine. And then you've guessed it, this diethylamine can now act as a nucleophile. Just keep practicing these until they get so boring that they are so second nature that you know you'll have it sussed for the exam. This is quite a complex structure, but the lone pair on the nitrogen remains the same. It's acting as a nucleophile. So it'll attack here, causing the breakage of this bond. We're deprotonating. I'll need plenty of space for this structure. This is triethylamine. And obviously there's no reason why this tertiary amine can't act as a nucleophile with a lone pair on that nitrogen to attack our chloroethane again. And if that happens, you'll end up with a quaternary ammonium salt. So as you can see here, here's our tertiary amine attacking our chloroethane to produce a quaternary ammonium salt. If we want to increase the yield of quaternary ammonium salt, we want to include an excess of halogenoalkane. Now these quaternary ammonium salts are super useful. They're used as hair and fabric conditioners, and that's because they're cationic surfactants. Remember, a cation is a positive ion. The positive charges of the cations are attracted to the wet surface, forming a coating that prevents the buildup of static electricity. So back in again with ethanoyl chloride. I'm going to be using a nucleophile which is a weak base, ammonia. The lone pair exists on the nitrogen. It's going to attack our slightly positive carbon, causing the breakage of that double bond there. Our oxygen gains a lone pair. The chloride ion is our leaving group, so we need to see the breakage of this bond here in order for the chlorine to leave. The ammonia has added itself. Currently it has too many hydrogens, hence why that nitrogen has a positive charge. So we're going to deprotonate by breaking this bond here to draw a product now. Double bond O here, NH2 because we've deprotonated, and then we have left over that chloride ion again. So to name everything, ethanoyl chloride, here's ammonia, and the name of this substance over here is ethanamide. Now, in these solutions which do contain ammonia, what we find in this situation is that it's another ammonia molecule which removes this hydrogen here, forming an NH4+ ion, and that's going to react with that chloride ion that left to form NH4Cl. Time for another summary equation. So this time we have acyl chlorides react with ammonia to produce amides, and as I was just saying, ammonium chloride will be our second product. We have our ethanoyl chloride again here. We are going to react with an amine. It has a lone pair on that nitrogen. We are going to attack our slightly positive carbon, causing the breakage of that bond here. Redraw everything carefully, showing that lone pair on the oxygen and the negative charge. We know that we're going to have a positive charge on this nitrogen, 2 hydrogens attached, plus our CH3. There's our leaving group, the chlorine. Let's add some curly arrows, showing the formation of that double bond there, the fact that the chlorine's leaving and that we are deprotonating. Final step to draw the product. We have formed what's known as an amide. Now, the amide functional group consists of C double bond O and an NH. So our summary equation now, we've got our acyl chloride reacting with an amine. It's going to form an N-substituted amide. And then because you've got excess of your amine, that's going to cause the deprotonation here. So you'll end up with an extra hydrogen, and that will combine with your chloride ion to form this salt here. Outline a mechanism for the reaction of bromomethane with an excess of compound J. You should represent J as this. So here's our halogenoalkane. J we know is a primary amine, so we know it's going to be nucleophilic substitution. I don't think this one's too complicated, particularly as we're allowed to represent J as RNH2. That carbon there is slightly positive, that bromine is slightly negative. We have a lone pair on that nitrogen that will attack this carbon, breaking this bond. We need to deprotonate. Compound K is a structural isomer of J. Explain why J is a weaker base than K. So just to bring down that formula of J here. Now, because in K we can see that alkyl group, remember that's going to form a positive inductive effect, meaning that more electrons are released so that that nitrogen's lone pair is more available to act as a base, i.e. to deprotonate. We met polymers in first year chemistry when we considered addition polymers. Now is not the time to completely summarize what happened here, but just to remind you, you take a monomer such as ethene, and then you join lots of these ethene monomers together to form an addition polymer, polyethene. Which is an example of a plastic used to make plastic bags and cling film. Remember that a monomer is a small subunit which joins together to form a polymer, a large molecule. At A2 we need to consider condensation polymers. Now these may be formed in the following ways: through reactions with dicarboxylic acids and diols. Remember that di means two, so dicarboxylic acid means that it's a molecule with 2 carboxylic acid groups. What is a diol? It's a molecule with 2 alcohol groups. Condensation polymers may also be formed from dicarboxylic acids reacting with diamines. So that means 2 NH2 groups. They may also be formed from amino acids joining together. Let's remind ourselves, what does the term condensation mean? it means it involves the loss of a small molecule such as water. So you'll expect to see that take place in a condensation polymerization reaction. And I'm sure you're already aware, but condensation polymers are usually made from two different monomers containing two different functional groups. So the first condensation polymer I want to consider is the polyesters, such as terylene. Now, polyesters are made from dicarboxylic acids and diols. They contain many repeating ester linkages, and a common example of a polyester is terylene, which is used to make clothes, plastic bottles and ropes. Let's draw some equations then. So I'm going to start with my diol. I'm going to use ethane diol. So ethane, 2 carbons, diol, 2 alcohol functional groups. Then I'm going to fill up with hydrogens. Our dicarboxylic acid that we're going to combine with ethane diol to produce terylene is going to be benzene dicarboxylic acid. There's our benzene ring. Here's our 2 carboxyl groups. We know that a condensation reaction will occur, which means the loss of a water molecule. As always with esters, it means the OH comes from our carboxylic acid, the H comes from our alcohol. So what's our product? What's our polymer? Just join together the ends of the molecules. So here's our ester linkage. Now this is what's known as a repeating unit of the polyester terylene. We don't complete with hydrogens here because we need to draw open bonds at either end to show that this unit is repeated many times. So that's our first condensation polymerization example, the manufacture of polyesters involving dicarboxylic acids and diols. Now we're going to manufacture polyamides using dicarboxylic acids and diamines. So when you make polyamides such as nylon and Kevlar, you're using dicarboxylic acids and diamines as your monomers, and your polyamide will by definition contain a CONH amide linkage. Remember that nylon is used to make clothes and fishing nets. Kevlar is extremely strong. It's used to make bulletproof vests and crash helmets. So I'm going to show you how to make nylon. So our dicarboxylic acid for nylon is hexane 1,6-dicarboxylic acid. Our diamine is going to be 1,6-diaminohexane. It's a condensation reaction again, we're losing water. So to work out our polymer structure, so here's nylon. Remember, if they ask you to deduce the monomers, if you're given the polymer, all you need to do is break the amide bond between the C and the end and add your H and OH atoms back in to form your water. I'm going to show you how we make Kevlar now. So our monomer is going to be, from the diamine point of view, it's going to be benzene 1,4-diamine. Our dicarboxylic acid is going to be benzene 1,4-dicarboxylic acid. Let's lose our water molecule. Stick together our ends. Here's Kevlar. Now Kevlar is so strong and can be used as bulletproof vests because hydrogen bonds form between the chains and the flat aromatic rings allow these chains to pack close together, so stopping things like bullets getting through. As I previously mentioned, when you join amino acids together, condensation polymerization occurs. If you have two amino acids joined together, you have what's known as a dipeptide, 3 amino acids, tripeptide, many amino acids, polypeptide. If you study biology, you'll be very familiar with the term polypeptide. A polypeptide is simply a polymer of amino acids. So here's your general structure of an amino acid with your central carbon atom. This R group does vary, and that enables there to be 20 different amino acids, but what remains the same is you have your central carbon atom surrounded by hydrogen, your carboxylic acid group and your amino group. As we know, it's a condensation reaction, we're going to lose water. Then we join those ends together. I'm just going to draw a dipeptide here, so one made up of 2 amino acids. And then if they want you to draw the polypeptide repeating unit, obviously we need to have open bonds. So it just needs slightly rearranging. So here's your repeat unit. Here is your amide bond, which in biology is known as a peptide bond. Now we move on to biodegradability and the disposal of polymers. So how are we going to throw away, recycle our plastics? And obviously that depends entirely on their composition. So ideally you want your plastic to be biodegradable. That means that it can be decomposed by microorganisms. Unfortunately, however, addition polymers, polyalkenes, for example, polyethene, polypropene, these are chemically unreactive, which means they are non-biodegradable. They have strong non-polar carbon-carbon bonds and carbon-hydrogen bonds, which really limit their biodegradability. Polyesters and polyamides, these are both examples of condensation polymers that I just showed you. Luckily, these are biodegradable, and that's because they contain polar carbon-oxygen bonds, either single or double, and that means that they can be hydrolyzed by nucleophilic attack using water in an enzyme-controlled reaction. In the laboratory, polyesters and polyamides can be hydrolyzed by heating with concentrated hydrochloric acid. What about other methods of disposal? So our addition polymers, our polyalkenes, can be disposed of by burning. Obviously, this isn't ideal because it releases carbon dioxide, which is a greenhouse gas that contributes to global warming. You also release toxic gases like carbon monoxide, which causes suffocation. It stops the transport of oxygen by the hemoglobin in our red blood cells. And also you release carbon particulates such as soot, which cause global dimming. You can also dispose of addition polymers, plastics such as polyesters, polypropenes in landfill, but they persist for many years. They occupy lots of land. Again, polyesters and polyamides are so much better, not just because they're biodegradable, but they can be recycled. Obvious advantages here include the reduction of landfill, saves raw materials. It's a lower cost of recycling compared with making these things from scratch, and it reduces carbon dioxide emissions as you're not burning them any longer. Major disadvantages of recycling is the difficulty cost of collecting, sorting and processing the plastic. Now, condensation polymers may be disposed of in landfill, but they take much longer to biodegrade once they're in landfill due to the lack of air. And remember, air contains oxygen needed for the respiration of the microorganisms responsible for the decay of these polymers. Sections of two polymers L and M are shown. Give the IUPAC name of the monomer that forms from polymer L. Here we have an addition polymer. So we'll expect our monomer to be unsaturated, so it needs to contain a carbon-carbon double bond. Just look for where the repeat occurs in this structure. It's going to be here. So I'm just going to draw that for you. And now we need to name it. The longest carbon chain, 1, 2, 3, 4, 5. And we have a double bond on the second carbon, a methyl group on the third carbon. So it is 3-methyl pent-2-ene. Give the IU-PAC name of the monomer that forms polymer M. I'll just get rid of all of this so you can see it more clearly. We've got our amide linkage. So if I do a dotted line separating, let's just look here. I'm going to number the carbons, 1, 2, 3, 4. We've got an amino group on the fourth, a methyl group on the third, 4 carbons. With that carboxyl functional group means that we have 4-amino, 3-methyl butanoic acid. The repeating unit shown represents a polyester. Name this type of polymer. We know that we've lost water, it's a condensation polymer. Give the IU-PAC name for the alcohol used to prepare this polyester. So here's our ester linkage. We know that if I draw that dotted line here, this represents the carboxylic acid end, this represents the alcohol end. So I just really want to form my alcohol from this. It's a diol. The alcohol functional groups are on the first and third carbon, so it's propane 1,3-diol. The repeating unit shown represents a polyalkene copolymer. This copolymer is made from 2 different alkene monomers. Name the type of polymerization. Remember, when you add alkenes together, it's addition polymerization. Draw the structure of each of the alkene monomers. Another dotted line here. Because it's an alkene, we need to add that double bond in. One of the 3 compounds shown in parts A, B, and C cannot be broken down by hydrolysis. Write the letter to identify the compound and explain why hydrolysis doesn't occur. It's going to be our addition polymer. We've said, remember, that they are non-biodegradable, they're inert, and that's because the carbon-carbon and carbon-fluorine bonds are too strong. It renders it inert. The amide or peptide link is found in synthetic polyamides and also naturally occurring proteins. Draw the repeat unit of the polyamide formed by the reaction of propane dioic acid with hexene 1,6-diamine. So propane dioic acid, 3 carbons, it's a carboxylic acid. Hexane 1,6-diamine, so 6 carbons. Diamine means 2 NH2 groups. So condensation polymer, so we're going to get rid of this OH here, this H here. So what I'm going to do is just remove that and then stick together these 2 parts, and then because it's a repeat unit, I'm just tidying up a little bit. So by drawing my 2 monomers, my propane dioic acid and my 1,6-diamine, I removed my water in the condensation reaction to form an amide linkage, and then I left my bonds trailing. In terms of the intermolecular forces between the polymer chains, explain why polyamides can be made into fibers suitable for use in sewing and weaving, whereas polyalkenes usually produce fibers that are too weak for this purpose. With our polyamides, you're easily going to form hydrogen bonds, and that's because a hydrogen of one chain will form hydrogen bonds with the oxygen of another chain. Hydrogen bonds are quite strong, whereas polyalkenes, there's no hydrogen bonds. You're only going to have van der Waals forces, so that makes them too weak in order to produce fibers suitable for that purpose. We've already looked at amino acids. Remember, we said they're examples of condensation polymers. We said that there are 20 different naturally occurring amino acids, and the differences arise from that R group. You can have a variety of different elements, you can have a variety of different combinations. And as I've already said, all amino acids contain a carboxylic acid group and an amine group. So here's your standard structure of an amino acid: your carbon bonded to your hydrogen, your carboxyl end, your amine end. Now here's your R group here, and this produces the amino acid threonine. And if we go about naming this from a chemical perspective, remember, you do need to learn that list of functional group priority, but this is carbon 1, 2, 3, and 4. So the name of this is 2-amino 3-hydroxybutanoic acid. And as I've said here in my guide, you don't need to know things like the biological name threonine, but you may be asked to deduce that IUPAC name. What about this one, which we call lysine? Let me number the carbons again. This will be carbon number 3 to 6. So we have 2,6-diamino, because there's 2 amine groups. There's 6 carbons, and there's the carboxyl group, 2,6-diaminohexanoic acid. And then aspartic acid down here is pretty complicated. We have a chiral carbon here due to the 4 different groups attached. The name of this is 2-amino-butane-dioic acid. Now, amino acids can act as both acids and bases. That's due to the carboxylic acid acting as an acid and donating a proton. The amine group can act as a base and accept a proton. We say that amino acids exist as Zwitter ions in neutral solutions. This means that they have both a permanent positive and permanent negative charge. The overall charge of a Zwitter ion, by definition, is 0. It's neutral. So here's our general structure of our amino acid, displaying its Zwitter ion properties due to that amine, which can accept a proton and act as a base, due to the carboxylic end that can donate a proton and act as an acid. Now we're going to run through examples of amino acids in neutral solutions, in acidic solutions, and in basic solutions. So in neutral solutions at room temperatures, most amino acids exist as solid Zwitter ions. Remember, this means that they have a permanent positive charge and a permanent negative charge. And when drawing Zwitter ions, we must ignore the R group, and that's because the overall charge of the Zwitter ion must be 0, neutral. What about in acidic solutions? Now, in acidic conditions, the lone pair of electrons on the nitrogen accept a proton in order to form a positive ion. And then in basic solutions, remember that our carboxylic acid end can donate a proton in order to act as an acid, and when it does that, it forms a negative ion. Proteins, now remember that proteins are sequences of amino acids joined together by those peptide amide links, which we mentioned before. Here we can see that amide link. Now, a protein can be described in terms of its primary, secondary, or tertiary structure. You'll know lots more about this if you study biology. So the primary structure simply refers to the sequence of amino acids. The secondary structure is how those amino acid sequences fold together to form alpha helices and beta pleated sheets. And then the 3D structure is how that polypeptide chain is folded in 3D space. Here we have 3 different amino acids, alanine, glycine, and cysteine. In order to form a polypeptide or a tripeptide, what's happened is a condensation reaction has occurred where we lose a water molecule and an amide linkage is formed. Remember that water molecule is lost in a condensation reaction. And then as many more of these amino acids join together, what's formed is a polypeptide with amide linkages formed between each amino acid. Now, how can we hydrolyze the polypeptide chain? By boiling in concentrated hydrochloric acid or aqueous sodium hydroxide. Because this is a long chain, remember we've kept those bonds at the end open. Running you through the secondary structure of a protein, so that was when I said that the amino acid chain folds into an alpha helix or beta pleated sheet. Now, the secondary structure is held in position through hydrogen bonds between amine and carboxylic acids on different amino groups. Remember, for hydrogen bonds to form, we need hydrogen bonded to a highly electronegative element such as oxygen. The tertiary structure is the folding of the polypeptide chain into 3D shapes, and we hold this tertiary structure in position through ionic interactions between oppositely charged R groups, covalent sulfur-sulfur bonds known as disulfide bridges between sulfur-containing cysteine R groups, and lastly hydrogen bonds between R groups containing oxygen-hydrogen or nitrogen-hydrogen bonds. Right, feel free to pause the video here so you can read through this practical where we're using thin layer chromatography in order to determine which amino acids are present once a protein has been hydrolyzed using concentrated hydrochloric acid. Now, it's possible to use your chromatogram to identify which amino acids are present. They'll all have a known RF value. You can calculate the RF value for each amino acid by taking the distance they've moved divided by the distance moved by the solvent. So as we can see here for the blue spot, it's moved 5.12 centimeters. The solvent front is 8 centimeters. The RF value is 0.64, so we can identify that this particular amino acid is valine. More biology. Enzymes are biological catalysts. Remember, this means that they speed up the rate of reaction without being used up. Enzymes are actually made from proteins, which is why this links nicely with everything we've learnt to do with condensation polymerisation and amino acids. Remember that enzymes have a specific active site. So this is an extremely simple diagram. But if this is your enzyme, this is your active site, and here's your substrate, which fits in, locks into your enzyme's active site. It has a complementary shape. Now, the active site may be stereospecific, and that means it can be specific for only one pair of enantiomers. Remember that we get enantiomers when you have a chiral carbon and you have two isomers that are non-superimposable mirror images of each other. So the substrate must fit the shape of the enzyme's active site and bond temporarily by intermolecular forces. What this does is it lowers the activation energy for the reactions. So we can see here how the enzyme is helping to catalyze the reaction because it lowers the activation energy. Now, some drugs are designed to block an enzyme's active site. It stops the substrate binding, and we call these enzyme inhibitors. The structures and common names of two amino acids are shown. So we have proline and alanine. Draw the structure of the Zwitter ion of proline. So remember, Zwitter ions have both a permanent positive charge and a permanent negative charge. So that's what we really need to show here on proline. Draw the structure of the tripeptide formed when proline bonds to two alanine molecules, one on each side. I don't have an awful lot of space here, so I'm just going to pop the answer up here. So we need 2 lots of alanine, 1 lot of proline. So proline is going to go in the middle. Because it's a condensation reaction, we need to lose a water molecule. And then to add another alanine to the left-hand side of the proline, we need another amide linkage. The tripeptide shown is formed from the amino acids alanine, threonine, and lysine. Draw a separate circle around each of the asymmetric carbon atoms in this tripeptide. So this is just another name for chiral carbon. So we need a central carbon atom with 4 different groups attached. There's our first one. We can clearly see 4 different groups attached. Here's our second one, our third one, and our fourth one. Draw the Zwitter ion of alanine. So we're focusing in on this amino acid here. Remember, a Zwitter ion has a permanent positive and negative charge. Give the IUPAC name of threonine. Just going to draw this amino acid out for you. The carboxylic acids, remember, take priority. So here's carbon number 1, 2, 3, and 4. Then you name your functional groups in alphabetical order. So we're going to start here with the amine. So it's on the second carbon. So we have 2 amino. Check it out, we've got a hydroxyl functional group on the third carbon, 2 amino, 3 hydroxy. We've got 4 carbons, the carboxyl functional groups, that's the carboxylic acid, butanoic acid. Draw the species formed by lysine at a low pH. So that's in acidic solutions. So remember, the nitrogens contain lone pairs. That means they can act as a base to accept a proton to form positive ions. Obviously, don't ignore the R group here. DNA from a chemistry perspective. So DNA stands for deoxyribose nucleic acid. It's a polymer, so it's a large molecule. It's double-stranded. It contains complementary base pairing, where A binds to T, C binds to G. Remember, the A stands for adenine, C stands for cytosine, G is guanine, T is thymine. Now, if we check out this page of my biology guide actually, but it does show the structure of DNA really nicely. So we said that DNA is double-stranded. Now the backbone of the DNA is made up of phosphate sugar alternating. So there's the phosphate, here's your deoxyribose sugar, and then the two backbones are linked by the rungs of the ladder, which are the complementary bases I've mentioned, where A binds to T, C always binds to G. Now these bases are held by hydrogen bonds, 2 hydrogen bonds between A and T, 3 hydrogen bonds between C and G. One thing to be aware of is the term nucleotide. All a nucleotide really is the combination of a phosphate, a sugar and a base. So there's one nucleotide, here's a second nucleotide. So now let's look at all of these various structures from a chemical point of view. So we're going to start with the structure of phosphate. Now handily this is included on the data sheet, so don't worry about learning these, but I just want to show you the structure here. What about the structure of your deoxyribose? And technically speaking, it's actually 2 deoxyribose. So the ribose refers to the fact that you have a sugar made up of 5 carbons. It's a pentose sugar. Here's its structure. As I've already said, nucleotide consists of a phosphate joined to a sugar and then a base. So in simplistic terms, something like this. There's our deoxyribose sugar. So let's combine this simplistic diagram with the actual structures. So we're going to start with our phosphate. And then up here you'll find your base attached. I'm just going to number these carbons. This is carbon number 1, 2, 3, 4, 5. You'll find that your next nucleotide is attached up here. And your next nucleotide is attached down here. What about the structure of these bases? As I've already said, we know that DNA is made up of 2 strands that form a double helix shape. I've said that there are hydrogen bonds between the complementary bases. And as we see here, we know that adenine binds to thymine. I said that there's 2 hydrogen bonds, and we can see how that forms between the oxygen here and the hydrogen here, the nitrogen here and the hydrogen here. And then what about in guanines and cytosines case? Well, we have 3 hydrogen bonds. Happily, you're given the structure of these bases in the exam, but it is important that you rotate them in the correct orientation to show how the hydrogen bonds form. The anti-cancer drug cisplatin operates by reacting with the guanine in DNA. Figure 1 shows a small part of a single strand of DNA. Some lone pairs are shown. Remember, this is the phosphate that I was just telling you about. Here's our deoxyribose forming the backbone, phosphate sugar, phosphate, and here's our guanine base. The DNA chain continues with bonds at X and Y. State the name of the sugar molecule that is attached to the bond at X. Yeah, we just need to name that. That's 2-deoxyribose. Messenger RNA is synthesized in cells in order to transfer information from DNA. The bases in one strand of DNA pair up with the bases used to synthesize RNA. Figure 2 shows 2 bases used in RNA. Suggest which of the bases A and B forms a pair with guanine in Figure 1 when the messenger RNA is synthesized. Explain how the base you've chosen forms a base pair with guanine. So I'm just going to start by writing that it's going to be 3 hydrogen bonds. Let's identify where that will be, and therefore whether it's base A or base B. So I'm just going to bring them up so you can see them more clearly up here. So we need to work out where our hydrogen bonds will form. So I've moved up base A here to actually show you nice and clearly, but obviously this represents the lone pair of electrons. Now you can see here that a hydrogen bond will form between hydrogen and this highly electronegative oxygen. Hydrogen bond here between this hydrogen and nitrogen, and then this oxygen and this hydrogen here, which is why it's base A. And as we'd expect with guanine, it will be 3 hydrogen bonds, so this is likely to be cytosine. So 3 hydrogen bonds form between base A and guanine. And actually, the way I've done it here, rather than writing a big description, you could just redraw the structure and show the hydrogen bonds, and that would be a clearer way for the examiner to see your answer. So by drawing my 2 monomers, my propane-dioic acid and my 1,6-diamine, I removed my water in the condensation reaction to form an amide linkage, and then I left my bonds trailing. In terms of the intermolecular forces between the polymer chains, explain why polyamides can be made into fibers suitable for use in sewing and weaving, whereas polyalkenes usually produce fibers that are too weak for this purpose. With our polyamides, you're easily going to form hydrogen bonds, and that's because a hydrogen of one chain will form hydrogen bonds with the oxygen of another chain. Hydrogen bonds are quite strong, whereas polyalkenes, there's no hydrogen bonds. You're only going to have van der Waals forces, so that makes them too weak in order to produce fibers suitable for that purpose. Anti-cancer drugs. So cancer is when there's uncontrolled cell division, which leads to growths known as tumours. And if those tumours spread, you have what's called a malignant cancer. And then if the tumours stay in one place, you have what's known as a benign cancer. Now, we want to obviously destroy our cancer cells, and one of the drugs used in chemotherapy is known as cisplatin. So I'm just going to summarise that it's an anti-cancer drug. Now, the simplest way to look at how cisplatin works as an anti-cancer drug is that it disrupts the DNA structure of cancer cells. So therefore it stops DNA replication. And then further down the chain of events, it stops cell division. And obviously uncontrolled cell division is the hallmark of cancer. So how does it disrupt the DNA structure? By binding to the nitrogen in the guanine base. Remember that DNA contains the bases adenine, thymine, cytosine, and guanine, and it's the guanine that's super important here because that's what gets majorly disrupted through the binding of cisplatin, and we'll look at how that actually takes place now. Here's your structure of cisplatin, and what actually happens is the chloride ion is displaced by water, as we see here, and then the next step is for this water ligand to be displaced by the nitrogen in guanine. And the reason that occurs is because nitrogen is a better ligand than water, so we call this ligand substitution. And overall what's happening is that we know that our cisplatin is bonding to the nitrogen molecules in guanine, and that's because the lone pair of electrons on the nitrogen can form dative coordinate bonds with the platinum. Remember, a coordinate bond is when both electrons are donated by the same atom. As a result, that's clearly going to distort the shape of your DNA strand and therefore prevent the DNA replication from occurring. DNA replication is obviously required in order to produce new cancer cells, so that's how the tumour is prevented from dividing uncontrollably. Obviously, this cisplatin isn't limited to just binding to guanine of cancer cells. It can also bind to the guanine of normal cells, killing and damaging them, and that's responsible for making people feel very unwell indeed on chemotherapy. We can reduce this risk by using the cisplatin in very small amounts and targeting it at the cancer cells. Cisplatin works because one of the atoms on guanine can form a coordinate bond with platinum, replacing one of the ammonium chloride ligands. Another atom of another guanine can also form a coordinate bond with the same platinum by replacing another ligand. On figure 1, draw a ring around an atom in guanine that is likely to bond to platinum. Here's figure 1. In a previous part of the specification, I talked about how hydrogen bonds form between guanine and cytosine. In order for cisplatin to bind, it needs to bind to a nitrogen with a lone pair that wouldn't be involved in bonding to cytosine, so you can pick either this one or this one. An adverse effect of cisplatin is that it also prevents normal healthy cells from replicating, suggests one way in which cisplatin can be administered so that this side effect is minimized. Administer cisplatin in very small amounts. The complex cisplatin acts as an anti-cancer drug by changing the properties of DNA when it reacts with guanine, a component of DNA. Here's cisplatin structure, here's guanine. When cisplatin is absorbed into the human body, it undergoes a ligand substitution reaction. One chloride ligand is replaced by a water molecule, forming a complex ion Q. Write an equation for this substitution reaction to form the complex ion Q. So from my guide, I'm just going to steal the exact equation I showed you, and here's the answer. The complex ion Q can bond to guanine in two different ways. The first way involves a hydrogen atom from one of the ammonia ligands on Q bonding to an atom in the guanine molecule. State the type of bond formed to guanine and identify an atom in guanine that could form a bond to this hydrogen atom. So the type of bond is obviously hydrogen bond. What is your atom in guanine? I'm just going to write down nitrogen, which I showed you in that earlier question. The second way involves a ligand substitution reaction in which an atom in a guanine molecule bonds to platinum by displacing the water molecule from Q. State the type of bond formed between guanine and platinum when a water molecule is displaced, and identify an atom in guanine that could bond to platinum in this way. So this answer is this bit of the specification where we stated that there's a lone pair of electrons on nitrogen in the guanine that can form a coordinate bond with the platinum. State and explain one risk associated with the use of cisplatin as an anti-cancer drug. Risk: it causes damage to normal cells. Why is that? Because the cisplatin may attach to guanine of healthy cells' DNA. Now, these organic synthesis questions are basically combining everything you've learned in terms of reagents and mechanisms throughout the course. So they are supposed to be difficult and complex, but you will have met them throughout the course. This question is about making a diester from cyclohexanol. State the type of reaction in step 1 and give the name of the reagent needed for step 1. For each step, work out your starting reactant and your product, and use your knowledge of organic chemistry to work out the mechanisms and various reagents. So step 1, you're starting with an alcohol, you're producing an alkene. So in my mechanism summary, we can see that this is an elimination of alcohol's reaction, a dehydration, taking us from an alcohol to an alkene. And the reagent we need, we can see, is hot concentrated sulfuric acid. So the type of reaction is dehydration. We need concentrated sulfuric acid. State the reagents needed and give the equations for step 2 and step 3 and show the structure of compound G in your equations. So we're going from an alkene to a diol. Now this one's obviously going to be quite complicated because we can see it's going to involve 2 steps. So actually I'm going to need to react my alkene with a halogen. I'm going to need to substitute my bromines for my OHs using a strong base. And I'll show you in my guide those summaries. So it's this electrophilic addition reaction here where we're going to take an alkene. The electrons in the double bond will attack this slightly positive bromine, causing the breakage of this bond. So that bromine gets added, hence electrophilic addition. And then in the second step, we're going to have nucleophilic substitution, where our hydroxide ion attacks our slightly positive carbon, replacing this bromine with a hydroxyl group, forming our alcohol. So what was our step 2 reagent to get it from our alkene to our halogenoalkane? It was bromine. And then remember, we need to replace the bromine with OH to end up at cyclohexane 1,2-diol. So instead we needed a strong base, sodium hydroxide. Here's the summary equation. Cyclohexane 1,2-diol reacts with ethane diol dichloride. Give the name of the mechanism for this reaction. Complete the mechanism to show the formation of one ester link in the first step of this reaction. What is the mechanism's name? So remember, as soon as you see an acyl chloride, then you know it's going to be an addition-elimination reaction. So to name it fully, nucleophilic addition-elimination. Let's sort out our mechanism. So remember, we have a slightly positive carbon here, slightly negative oxygen and chlorine. So your lone pair of one of your alcohols is going to attack this carbon here, causing the breakage of this bond. So let's draw a second step. So let's have a look at what's taken place here. We've formed a bond between our oxygen and carbon, as you see here. This double bond has been broken, leaving a lone pair on the oxygen. So our next stage is to show that chlorine is the leaving group. We need to reform that bond here. And lastly, we need to deprotonate. And then I'm just going to show you the product. Here's our final product. Suggests why chemists usually aim to design production methods with fewer steps with higher percentage atom economy. Finally, a break in how difficult this question is. Fewer steps means that less energy is used. High percentage atom economy, that means an increased conversion into the useful product, means that we have less waste. Consider the following reaction sequence, which starts from phenylamine. State and explain the difference in base strength between phenylamine and ammonia. Now remember, ammonia NH3 is usually a weak base because it has no alkyl groups which release electrons towards the nitrogen atom, rendering the lone pair of electrons on that nitrogen more available. So due to that lack of alkyl groups, ammonia tends to be the weakest base unless you have aromatic rings, aryl groups, such as the case here with phenylamine. And actually what they do is they withdraw electrons from the nitrogen atom, meaning that the lone pair of electrons is less available, so you have a weaker base with phenylamine. So ammonia is a stronger base compared with phenylamine because the lone pair of electrons is less available on the phenylamine's nitrogen because they have been delocalized into that aromatic ring. Name and outline a mechanism for the reaction step 1 and name the organic product in step 1. Let's start by outlining the mechanism. So we'll draw ethanol chloride with its slightly positive carbon, slightly negative oxygen. There's our phenylamine, which remember has a lone pair on the nitrogens. The phenylamine is a nucleophile, which remember means that it can donate electrons, so our lone pair, which means we need to draw a curly arrow showing it attacking this carbon, breaking this bond to produce this intermediate. So our nucleophile has added itself. We now need to sort out everything else. The lone pair here on the oxygen will be donated to form that double bond. We need a leaving group, and it tends to be the chlorine because it's the most stable ion. And then lastly, we can't have a positive charge on this nitrogen, so we need to deprotonate. So what's the name of this? Nucleophilic addition elimination. So in order to draw the organic product, it's easiest if I just finish drawing this mechanism. So remember when we named esters, just to make a quick note over here, you had an alcohol plus a carboxylic acid forms an ester plus water. And in terms of the name, if you had something like methanol reacting with ethanoic acid, the name of the ester initially comes from the alcohol, so it would be methyl. The second part comes from the carboxylic acid, ethanoic acid, so it would be methyl ethanoate. Well, it's a very similar situation here when it comes to naming amides. You've got an amine reacting with a acyl chloride to form your amide. And the name of our amine was phenylamine. We had ethanoyl chloride. When it comes to naming your amide, the first part of its name comes from the amine. Because it's got a nitrogen in it, we need to just point out that it's N-phenyl. And then the second part of the amide's name comes from your acyl chloride, your ethanoyl chloride, so that's why it's ethanamide. Let's look at part 3. The mechanism of step 2 involves attack by an electrophile. Give the reagents used in this step. Write an equation showing the formation of the electrophile. Outline a mechanism for the reaction of this electrophile with benzene. So our electrophile, remember, to get from here to here is NO2+. Remember the way in which we form that NO2+ is by using sulfuric acid acting as an acid, nitric acid acting as a base in order to generate our electrophile. So there is my equation showing the formation of the electrophile. What are my reagents? Concentrated sulfuric acid, concentrated nitric acid. And then we want to show a mechanism for this reaction of this electrophile with benzene. There's our benzene ring. Because the NO2+ is an electrophile, which remember is a lone pair acceptor, it's going to be attacked by the electrons in the delocalized ring. So here's our delocalized ring, which has now been broken. The NO2+ is now attached. We need to lose this hydrogen in order to reform the ring. So we're going to use a curly arrow to show the electrons moving from that bond into that delocalized ring to form our product, which will be nitrobenzene plus a H+ ion. So that's part 3 done. Part 4, name the type of linkage which is broken in step 3 and suggest a suitable reagent for this reaction. So I'm just going to draw this out so we can work out what kind of linkage is broken. So name the type of linkage which is broken in step 3. It's that C double bond O NH bit which is present in an amide bond or a peptide bond, which we saw lots of when we were looking at amino acids. Remember, this is a hydrolysis reaction. And so the reagent we require is either concentrated hydrochloric acid or sodium hydroxide. Nuclear magnetic resonance spectroscopy, also known as NMR. This is a method used to determine the structures of molecules and the exact position of functional groups in certain compounds. Now there are 2 types of NMR that we're going to meet. The first one is the more straightforward one. It's the carbon-13 NMR. And then the second one is what we call Proton NMR. That one's slightly more complex. I'm obviously going to talk in great detail about what various NMRs mean and how we actually use them. But just to give you some context, you'll be provided with something like this, which in this case is a carbon-13 NMR. On the y-axis, it shows the energy absorbed, and on the x-axis, it shows the chemical shift. And then there'll be a variety of peaks. And then based on what I'm about to teach you, you'll be able to work out the structure of a compound. This is incredibly important, this TMS, because it has a shift of 0 by definition, and I'm going to tell you now what TMS is. Just note here that the x-axis goes from right to left. So in effect, here's your origin. So what is TMS? Well, it stands for tetramethylsilane, and this is our NMR reference molecule. So every other compound we look at is basically compared to TMS. What is the structure of TMS? What we're going to do is compare the chemical shift of other compounds with TMS. And so, by definition, the chemical shift of the carbons and hydrogens in TMS is 0. And why do we use TMS as our reference molecule? First of all, it's because all the carbons and hydrogens are in the same environment. Look, it's a totally symmetrical molecule. Other useful properties, it's inert, so unreactive. It's non-toxic. And lastly, it's easy to remove from the sample. So TMS is our reference molecule, and all the other compounds we're going to study are going to show a variety of chemical shift which will compare against TMS, which by definition has 0 chemical shift. And these are the reasons here why we use TMS as our reference molecule. I just want to write this statement and then we'll look more closely at some examples. So NMR spectra give, you'll see me talk about this all the time, the chemical shift measured in parts per million of atoms in different environments compared to that of reference molecule TMS. So you'll be using this table all the time in your data booklet. This shows the type of carbon on the left-hand side, and then over here we have the chemical shift given in parts per million. And we're going to use this table in order to interpret the 13 carbon NMR spectra. One thing to point out is, as I've said here in my revision guide, the table below is given in your data booklet, and it gives the expected chemical shifts for carbons in different environments. A carbon's environment is based on its proximity to other atoms, and only symmetrical carbons will be in the same environment as each other. This is very important. So as soon as you have a symmetrical compound, that will reduce the number of carbon environments more than you might think. The closer a carbon is to an electronegative atom, such as oxygen, nitrogen, fluorine, or a double bond, the greater the chemical shift. So as I already told you, this is in effect our origin. Here's our TMS, our reference molecule. These are the peaks on our NMR. So obviously the further along the x-axis they are in this direction, the greater the chemical shift. So we would expect any peaks that occur down this end to be either close to a double bond or close to a highly electronegative element. So now it's time to apply everything that I've just gone through. So here we have propan 1-ol, and I'm just going to talk you through how this NMR basically informs you of the structure of propan 1-ol. Because often in the exam you'll be given something like the molecular formula C3H8O, and obviously you'll have no idea what homologous series this compound belongs to. However, through the NMR spectra, you'll be able to work out the various carbon environments, which will enable you to determine that it's propan 1-ol. But to begin with, we've got our structure here. So here's TMS, which has a chemical shift of 0. This first peak here has the lowest of the chemical shifts compared with the other peaks. Why? Because it's closest to TMS. And so that green peak here is responsible for the CH3 here. Then as we move along to the central carbon, it's getting closer to a highly electronegative element, so we're going to see slightly more of a shift. And then lastly, this carbon here is obviously very close to the oxygen, so we see a large chemical shift, and we'll actually be able to cross-reference these peaks with this table in the data booklet. So for example, 60 here as you can see, yes, it falls into this range here, and therefore it's telling us that it's either going to be an alcohol, ether, or ester. In this case, it's going to be an alcohol because it fits our molecular formula of C3H8O. So you can cross-reference all of these peaks with the data booklet. Obviously, there are some overlapping ranges, so it will be a little bit of trial and error to work out where the functional groups lie. Now, this molecule, propan-1-ol, has 3 carbon environments, and therefore you can see 3 peaks. Do notice that with 13 carbon NMR, the height of the peaks is irrelevant. When we look at proton NMR, the height of the peaks will become far more significant. Now we're going to take a second example, this time with a symmetrical molecule. So we have cyclohexane 1,2-diol. So let's just work out what we would expect to see. Okay, here is my line of symmetry here. And as soon as you have a line of symmetry, it means that matching carbons, such as these two, are in the same environment, so they'll show up as only one peak. So that's one environment. Here's our second environment, here's our third, and that's due to the symmetry. So we would expect to see 3 peaks, which we do. Then we have the alcohol functional group here. Remember, oxygen's highly electronegative, so the carbons next to the oxygen would have the greatest chemical shift, and as we know, that means they'd be situated furthest to the left. I'm just bringing in that table again. So just to look, this is around 75, this peak. Sure enough, it corresponds to being an alcohol. So as always, you can line up the data table with what's going on here in terms of the peaks. Taking yet another example. So here we have a line of symmetry which exists just here. So if we count the number of carbon environments, it's not 1, 2, 3, 4, 5, 6. Instead, due to this line of symmetry, these 2 carbons exist in 1 carbon environment. So that would produce 1 peak, 2 peaks, 3 peaks, 4 peaks. 1, 2, 3, 4. There's our reference molecule again. Here's our highly electronegative nitrogen, so you'd see more chemical shift at the carbons closest to the nitrogen. Now this compound here has no symmetry whatsoever, so we have a huge number of carbon environments, 1, 2, 3, 4, 5, 6. Here's your double bond producing a huge chemical shift, so these peaks exist very far down this axis. And this carbon here next to the oxygen exhibits a large chemical shift. Now let's have a look at another type of way they could ask you about this. So isomers A and B have the molecular formula C4H11N, and they're both secondary amines. In their 13 carbon NMR spectra, A has 2 peaks, B has 3. Deduce their structures. So crucially, we've been told that these compounds are secondary amines. Remember, amines look like this. If you have a primary amine, one of those hydrogens is replaced with an R group, and if you have a secondary amine, it means that a second of these hydrogens is replaced with an R group. So in terms of their structures, that's a very good starting point, because we now need to work out the layout or arrangement of all these carbons. So the next thing to look at is the fact that we've been told that A has 2 peaks, which means it has 2 carbon environments. So to look at A, we need to obey this molecular formula. We know it needs to be a secondary amine. We know that it has 2 carbon environments, but look, we've got to try and fit 4 carbons in. So those 4 carbons have to fit in 2 carbon environments, which means we must have a symmetrical compound. So actually, if you look at our final answer, yes, we have our secondary amine, and yes, the molecule is symmetrical, and therefore those 2 carbons there are part of one environment. These 2 are part of a second environment, so we would expect 2 peaks on our NMR. Now looking at B, where we know we have 3 carbon environments. Again, there's a bit of trial and error here, but we do have the basic structure of knowing that it's a secondary amine. So the way in which we can fit 4 carbons into 3 environments is making sure there's a little bit of symmetry here, so that these 2 methyl groups are in the same environment, allowing us to have our 3 peaks on the NMR. How many peaks are there in the 13 carbon NMR spectrum of 1,4-dimethylbenzene? So what you want to do first of all is draw the structural formula. I'm going to draw the skeletal formula. There's my benzene ring. There's carbon number 1, carbon number 4. That's how you draw the skeletal formula of 1,4-dimethylbenzene. There's no need to write CH3 here. Now, because we're being asked how many peaks, that's really how many carbon environments. So I'll use my highlighter to demonstrate them. There's one carbon environment, it's symmetrical with this one, so that's the same carbon environment. That's a second carbon environment. And then again, because the compound is symmetrical, those 4 carbons are all part of the same environment. How many different colours have I used here? 3, so the answer here is C. How many peaks does this compound have in its 13 carbon spectrum? Let's colour code again. 1 carbon environment, 2, 3, 4, 5, 6, 7, 8. It's not a trick question, the answer here is 8. NMR and infrared spectroscopy are used in organic chemistry to distinguish between compounds and to identify them. Give the skeletal formula of the compound that is used as the standard when recording a 13 carbon NMR spectrum. We need to draw the skeletal structure of tetramethylsilane. So we just need that central silicon atom, and then we show the 4 methyl groups simply by doing that. 4 isomers of C6H12O2, PQRNS as shown in figure 1, were analysed by our NMR spectrometry. 3 of these isomers as shown in figure 2. Use table C in the data booklet to help you identify which isomer produces each spectrum. So I've just grabbed that table from the data booklet, just popped it in here so we can see it more easily. So in effect, here are 3 spectra, and we have to decide which of these isomers produced each spectra. So in all honesty, I think the easiest way of doing this is first of all going through each of these structures and working out how many carbon environments we have, and therefore how many peaks we'd expect to see on the infrared spectra. So there's 1 carbon environment, 2, 3, 4, 5, 6. So we'd expect to see 6 peaks here. What about this isomer? Just be careful here. These 2 methyl groups are part of the same carbon environment. 2nd, 3rd, 4th, 5th. 5 peaks for Q. Let's look at the number of carbon environments and therefore peaks for R. So these will all be part of the same environment. So that's 4 peaks. And then lastly, 1, 2, 3, 4 peaks. So now we're ready to look at our NMR. Just count the number of peaks. 4 peaks. 4 peaks. 1, 2, 3, 4, 5. 5 peaks. So that 5 peak one will be easy. Where did I write 5? Just here next to Q. So immediately we write Q here. This is obviously trickier because we have 4 peaks for both. 2 options here with 4 peaks R and S. So now we need to try and differentiate between the 2. Now looking at the major differences, it's here you've got a carboxylic acid versus an ester down here. Let's just have a look at this ester. Now here, because that carbon environment here is next to an oxygen, you'd expect to see more of a shift. So let's just have a look down here, and sure enough, there's the largest shift here compared with here. So that means that this particular NMR belongs to our ester, which was S. And therefore, by process of elimination, that means that that must be R. K and L are cyclic compounds with this molecular formula. Both have 4 peaks in the NMR spectra. K is a ketone, L is an aldehyde. So higher up in the question, we're being asked to determine their structures. Loads of information here. So K is a ketone. So obviously we'll expect this functional group on a ketone. L is an aldehyde, CHO. We've been told that they're cyclic compounds made up of 6 carbons. So let's start with our ketone. And I'm just going to explain to you why this is the structure of K, because there's 1 carbon environment. It's symmetrical, so there's the 2nd, 3rd, and 4th. So therefore we'd expect 4 peaks. So just to double check, is K first of all obeying the molecular formula C6H10O? Sure enough, 1, 2, 3, 4, 5, 6 carbons, 2, 4, 6, 8, 10 hydrogens, and there's our O. Is it a cyclic compound? Sure enough. Yes, it is. And then do we have 4 peaks represented by 4 different carbon environments? Yes, we do. What about our aldehyde L? This will take practice, but I'm just going to explain to you why this is correct. So we have our aldehyde functional group. Let's count the carbon environments. 1, 2, 3, and 4. So yeah, another 4 peaks. And we know that it's cyclic again. When the molecular formula of a compound is known, spectroscopic and other analytical techniques can be used to distinguish between possible structural isomers. Draw one possible structure for each of the compounds described in parts A to D. So we're going to go in straight here. Compounds F and G have the molecular formula of this. They're both dinitrobenzenes. F has 2 peaks, G has 3 peaks. So the fact that they're dinitrobenzenes means that we're going to expect to see a benzene ring. The nitro bit means we're going to have an NO2. So let's start with F. We know that it has 2 peaks, so that's 2 carbon environments. But we've got to accommodate 6 carbons. So here's my benzene ring. 2 carbon environments needing to accommodate 6 carbons means we'll need a great deal of symmetry here. So I'm just going to draw a dotted line here and add my NO2s right there. Marking off the carbon environments then. There's obviously 1, and then because of the symmetry, those 4 carbons belong to the same carbon environment, so I'm happy that that's my structure for F. What about my structure for G, which I know has 3 peaks, so 3 carbon environments? There's my benzene ring. Let's add a dotted line just to show you how we're working out these carbon environments. They're both in the same carbon environment, and then a 3rd carbon environment. So yeah, 3 peaks. Now we're moving on to look at proton nuclear magnetic resonance spectroscopy, so Proton NMR. As I previously said, it's used to determine the structures of molecules and the exact position of functional groups in a compound. So previously we've looked at the more straightforward 13 carbon NMR. Now we need to turn our attention to Proton NMR. As usual, we're using the reference molecule tetramethylsilane. You can see its structure here. This is the reference molecule, and when we compare the chemical shift of the carbons and hydrogens present in other functional groups, we'll always be comparing them to the TMS because by definition it has 0 chemical shift. Now previously in carbon 13 NMR we said that the height of the peaks is totally irrelevant to what we're trying to find out. With Proton NMR, by stark contrast, the area under each peak is incredibly important because it gives the relative number of hydrogen atoms in each environment. So here's a proton NMR spectra similar to the carbon 13. You've got your energy absorbed on the y-axis, you've got your chemical shift in parts per million on your x-axis. TMS shows your reference molecule with its 0 chemical shift. Now what happens with Proton NMR is you'll get what's known as splitting patterns. And these are caused by an effect called spin-spin coupling, and they give you information about the neighbouring hydrogen atoms. So these splitting patterns will tell you how many hydrogens there are on neighbouring atoms, and we use the n+1 rule in order to determine this. And I'll write this down for you shortly, but the n+1 rule states that the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So here we can see 4 peaks, which means that the neighbouring atom must contain 3 hydrogens. Here we see 2 peaks, which means that the neighbouring atoms must contain 1 hydrogen. And if we start adding a little bit of detail here, look, sure enough, if you look at my colour coding, yes, this neighbouring atom contains 1 carbon, And if we look at my colour coding for the blue one, I said we'd expect the neighbouring atom to contain 3 hydrogens. Sure enough, the neighbouring atom here does contain 3 hydrogens. Proton NMR displays splitting patterns. These are caused by an effect called spin-spin coupling. The key thing though is that those splitting patterns provide information about the neighbouring hydrogen atoms. So basically they're going to tell us how many hydrogens there are on neighbouring atoms using the n+1 rule, where the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So for example, if we apply this, we said that the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So if the number of hydrogens on adjacent carbons is 0, by definition, the NMR signal will have a single peak. And we call that single peak a singlet. What about if there's 1 hydrogen on adjacent carbons? We can work this out with the n+1 rule. The NMR signal will be split into 2 peaks. With a tiny extra detail here in a 1-to-1 ratio, which we'll look at on NMR. And we call this situation a doublet. What about if there are 2 hydrogens on the adjacent carbon? This time the NMR signal will be split into 3 peaks in a 1-to-2-to-1 ratio, which we'll call a triplet. If there are 3 hydrogens on the adjacent carbon, the NMR signal will be split into 4 peaks in a 1-to-3-to-3-to-1 ratio, which we'll call a quartet. So to look back at what we've just discussed, the n+1 rule states that the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So for example, if there are 0 hydrogens on the adjacent carbon, the NMR signal will have a single peak, which we'll call a singlet. If there's 1 hydrogen on the adjacent carbon, the NMR signal will be split into 2 peaks in a 1-to-1 ratio, and we call this a doublet. If there are 2 hydrogens on the adjacent carbon, the NMR signal will be split into 3 peaks in a 1-to-2-to-1 ratio known as a triplet. And lastly, if there are 3 hydrogens on adjacent carbons, the NMR signal will be split into 4 peaks in a 1-to-3-to-3-to-1 ratio, a quartet. And this goes on. If we had 4 hydrogens, we'd expect 5 peaks. 5 hydrogens, 6 peaks. Again, in your data booklet, you'll get some information regarding the chemical shift. This time, because we're looking at proton NMR, it's going to be a type of proton on the left-hand side of the table as opposed to the type of carbon. Now, the chemical shifts in proton NMR are smaller than the chemical shifts in 13-carbon NMR. The closer hydrogen is to an electronegative atom such as oxygen, nitrogen, fluorine, etc., the greater the chemical shift. So let's have a go at interpreting a proton NMR. As I've said, you'll expect your spectra to look very similar to your 13-carbon one with your chemical shift along here. Remember, it reads from right to left with TMS, your reference molecule, situated here. Just to look at the various peaks. So here you can see a quartet. According to the n+1 rule, you would therefore expect the adjacent carbon atom to have 3 hydrogens. Here we have a single peak, so you'd expect the adjacent carbon to have no hydrogens. Same is true here, no hydrogens. We've got 2 peaks here, so I'd expect the neighbouring carbon atom to have 1 hydrogen. Let's look at our molecule. I'm going to start at this end. Here we have 3 hydrogen atoms. Just to colour code, just to show you what we're looking at. The chemical shift here for these 3 hydrogens is between 0.7 and to 1.2. And the reason that this peak is split into 2, as we see here, is because, as I've written here, we are expecting one hydrogen on the next door carbon atom. And sure enough, the next door carbon atom has one hydrogen. If we move along to this hydrogen here, which is represented by the chemical shift here with 4 peaks, we've got one hydrogen showing a chemical shift between 3.1 and 3.9. The reason why that peak is split into 4 is because, as I wrote here, there are 3 hydrogens on the next door carbon atom. We call this a quartet, and yes, there are 3 hydrogens here. This red ink here represents this peak with a chemical shift of between 0.5 to 5, and we've written here that hydrogens attached to oxygen or nitrogen do not tend to show splitting patterns. They're represented by a singlet. Remember, the whole time you'll want to cross-reference with this table from the data booklet just to make sure you're happy with where these chemical shifts are coming from. And then lastly, the 3 hydrogens here located at between 2 to 2.9. As I've said, we've got no splitting here, and that's because, as I wrote here, there will be 0 hydrogens on the next door carbon atom. This is true, there's no hydrogens on here, so we're seeing a singlet. And then the extra thing, look, I pointed out that that was a singlet, and yes, it is a singlet, there's no splitting. Here, with the blue, I already mentioned why we're expecting to see 4 peaks, and that's due to there being 3 hydrogens on the adjacent carbon. I said that that was known as a quartet. Yes, we can see that here. And then on top of that, we said that the ratio would be 1 to 3 to 3 to 1. And sure enough, the height of these peaks does show that ratio there. What about this orange one, which is a doublet? The ratio, we said, remember, would be 1 to 1, as you can see here, by the height of those peaks. Now, these numbers here, the numbers that have lovely colours, these are incredibly important. They're called integration values, and they show the relative number of hydrogens in each environment. Sometimes they'll be listed in a table, sometimes they'll just be written directly above the peaks. So here, one hydrogen has been split into a quartet by hydrogens on an adjacent carbon. Now, the integration values only show the ratio of hydrogens and not the actual number. This will become far more clear when we look at some past paper questions. Now, in Proton NMR, CdCl3 or CCl4 is usually used as the solvent. The D is deuterium, which is known as heavy hydrogen because it contains an extra neutron. Now, neither CdCl3 or CCl4 contain hydrogen atoms, and therefore they give no signals in the spectrum. That's important. We don't want them disturbing the Proton NMR. Now, CCl4 is non-polar, so it's a good solvent for non-polar organic molecules. CdCl3 is a polar covalent molecule, which means it's a good solvent for polar organic compounds. So obviously you'll pick your solvent based on what type of organic compound you have. Let's take another Proton NMR spectra. Now obviously we have an ester here. Let's actually look at the splitting patterns on the NMR. So I've just grabbed the chemical shift data here from the table from the data booklet so we can actually have a look at what's going on. Starting with this CH3 here, we've got 3 hydrogens showing chemical shift from 0.7 to 1.2. Look, RCH3 0.7 to 1.2. So they're in the correct place on this x-axis. Now we have a splitting of 3 peaks, which means that the adjacent carbon to that CH3, according to the n+1 rule, must contain 2 hydrogens. Yep, there it is. That carbon next door has 2 hydrogens. Checking out its peaks now. So we've got 2 hydrogens with chemical shift of 2.1 to 2.6. So expecting it to be located next to that carbon double bond O. Because that carbon next door contains 3 hydrogens, according to the n+1 rule, that makes sense, therefore, that we have this quartet here. And then that has pinned down our C double bond O. What about this CH3 down here? We have a chemical shift of 3.7 to 4.1 due to the ester linkage. Look at the data here. And the next door atom has no hydrogens on it, which is why you see no splitting of this peak. We have simply a singlet. Now, this is an isomer, and the biggest thing I want to point out here is notice how the different isomers produce different proton NMR spectra, and that's due to the different hydrogen environments and splitting patterns. So despite the fact that obviously they have the same molecular formula, they're both esters, you still see different splitting patterns. So you can see how the proton NMR is very helpful in determining the order of these atoms. So diving in here where we have a quartet, yes, you can look at the chemical shift here, but the one thing I want to point out is because that is a quartet, the next door carbon must have 3 hydrogens due to the n+1 rule. Yes, here it is. Here's our triplet as represented here, and that therefore accounts for the differences we see between these two isomers NMR. Now, spin-to-spin coupling is not seen when equivalent hydrogens are on adjacent carbon atoms, nor when a hydrogen is attached to an oxygen or a nitrogen, which is something I previously mentioned, so we can't see any splitting here. And so as a result, the spectrum for this ethane 1,2-diol has simply 2 singlet peaks. And one last thing to point out is that these peaks, these integration values, only show the ratio of hydrogen atoms, not the actual number. This question is about NMR spectroscopy. A compound is usually mixed with SiCH34 and either CCl4 or CdCl3 before recording the compound's proton NMR spectrum. State why these 3 compounds are used and explain how their properties make them suitable. Let's start with tetramethylsilane is used as a reference molecule as it shows 0 parts per million chemical shift. What other properties make it useful for this purpose? TMS is unreactive, it's inert, non-toxic, and easy to remove from the sample. How about CdCl3 and CCl4? Well, these are both used as solvents. The ideal thing about both of them is they give no signals in the spectrum because they have no hydrogen atoms. And let's go in now really precisely saying when you'd use each type of solvent. So CCl4, remember, is non-polar. So is a good solvent for non-polar organic molecules. And then CdCl3 is polar, and therefore it's a good solvent for polar organic compounds. Deduce the splitting pattern for each of the peaks given by the hydrogen atoms labelled X, Y, and Z in the proton NMR spectrum of the compound shown. I've just set myself up for the rest of this question by pulling in the chemical shift data from the data booklet, and then I've drawn out the displayed formula so we can see more clearly what will be going on here. So if we look at X, which is CH3, according to the n+1 rule, just have a look at the next door atom, the carbon. It has 1 hydrogen atom attached, so according to n+1, we'd expect to see a doublet here. Remember, that would tell us, therefore, that the neighbouring carbon has 1 hydrogen, as is the case. So moving on now to Y, right, obviously there are 2 adjacent carbons. There's no hydrogens on this carbon, however, so we would expect no splitting caused by that. However, over here, we have 3 hydrogens, so according to n+1, we'd expect this hydrogen to be split into a quartet. And then last but not least, Z. Because they're in the same environment, it doesn't matter which one you look at, but obviously the neighbouring carbon has 1 hydrogen on it, so therefore the hydrogens would be split into a doublet. Suggests why it's difficult to use table B, so this table here, to predict the chemical shift for the peak given by the hydrogen atom labelled Y. Well, that's because this hydrogen is attached to both a carbon chlorine and a carbon oxygen. So if we look here, look, that would be relevant because it's carbon attached to chlorine. This would be relevant because it's carbon attached to oxygen, but there's no set of atoms which shows both. Two isomers of blah each have 2 singlet peaks only in their proton NMR spectra. In both spectra, the integration ratio for the 2 peaks is 2:9. Deduce the structures of these 2 isomers. Okay, the first thing I want to do is work out the molecular formula. So we have 6 carbons, 11 hydrogens, a chlorine and an oxygen. Now the integration ratio is 2 to 9, which adds up to 11, which is super handy because we know we've got 11 hydrogens altogether. So actually that tells us straight away that we have 2 hydrogen environments, one with 2 and the other one with 9. And that singlet tells us that both of them must be attached to a carbon with no hydrogen, otherwise you'd expect splitting. So based on all of that, we know we must have this layout of atoms. And so to actually apply what I just said in terms of a structure, look, this is the only structure that works. Why? Because here we have 9 hydrogens. They're clearly all in the same environment and they're attached to a carbon with no hydrogens. So thus far we have obeyed all the information here. Next up, we need 2 different ways, because we've got 2 isomers, of including a C double bond O and a Cl. So if we think about the possible homologous series, it's likely to be an acyl chloride and a ketone with a chlorine group elsewhere. And then finally, we need to fit in our remaining leftover atoms of CH2 so that the hydrogen will not be split, and therefore we know that that must be next to a carbon with no hydrogen. So I'll show you the structures and then I'll kind of explain it again from the structural point of view. And remember, with these sorts of questions, there's always an element of trial and error here, so you must take your time to try out different arrangements of atoms. So here's our acyl chloride. So just to show you, 3, 6, 9, 10, 11. Yes, we've got 11 hydrogens. In terms of the environments, they're all one environment. Wonderful. These are in a second environment. There's 2 hydrogens. Yes, great. And then just to show that we've got 2 singlet peaks, if I focus in on here, let's have a look at the neighbouring atoms, both of these carbons. Look, neither of them have hydrogen attached, so that's great. That gives me a singlet peak here. So if we look at our second singlet peak, focusing in on this hydrogen environment, sure enough, the neighbouring adjacent atom, this carbon, has no hydrogens attached to it. So I'm very happy with my acyl chloride structure. And then my second isomer is a ketone. Okay, so looking again, yes, we have 11 hydrogens. Yes, we have 2 environments. One has 9 hydrogens, the second one has 2. Perfect. What about these 2 singlet peaks? Looking at this carbon here, sure enough, the adjacent carbon has no hydrogens on it, so that would produce our singlet peak. And then what about this carbon here? No, neither of these atoms have a hydrogen attached, so perfectly happy with both of my isomers. Figure 3 shows the proton NMR spectrum of Q, which has the molecular formula of C3H7ClO. The table below shows the chemical shifts and integration values for each peak. Deduce the structure of Q and explain your answer. I'm going to start by looking at the integration values. Remember, this tells us the relative number of hydrogens in each environment, so we need a ratio here. So in effect, you want to divide each of these 3 numbers by the smallest number, which is 0.6, to get a ratio of 1 to 1 to 1.5. Let's get a whole number ratio, 2 to 2 to 3. So what that means is that the first environment contains 2 hydrogens, the second environment contains 2 hydrogens, and the third environment contains 3 hydrogens. And we know that that ratio corresponds to the exact number of hydrogens in this compound, because actually here it tells us that there's 7 altogether, so that makes this question slightly more straightforward. And let's look at the chemical shift data now. So we know we've got a peak at 3.95. I've pulled in the data from the data booklet. So 3.95, look down here, could obviously correspond to this type of proton and this one here. Again, bear in mind your molecular formula, it contains a chlorine, so it's highly likely, therefore, that that 3.9 corresponds to our CH2Cl. So I'm just going to write that there. Because that's the highest chemical shift, it means that it is this triplet here. And because that's a triplet, according to the n+1 rule, it tells me, therefore, that there's 2 hydrogens on the neighbouring carbon. Let's have a look at this chemical shift data here, 3.65. Again, look down here. Now it's likely to be the ROCH, again, because we've double checked with our molecular formula. Yes, we do need an oxygen in there. And then because of this integration value here, I know that I've got 2 hydrogens in this particular environment, so I can just add a H here. And then looking here with this chemical shift of 3.35, it does actually fit as being ROCH again, and that makes sense because obviously that oxygen does need to be bonded to atoms either side of it, and because we have an integration value of 3, that tells me that I have 3 hydrogens in this environment. So now we've worked out the individual pieces, we can start to fit them together in the puzzle. I'll start here just because I know the chlorine can only ever have 1 bond. And I know that the chemical shift here relates to this triplet here. So I'll expect, due to the n+1 rule, there to be 2 hydrogens on the neighbouring carbon. So that makes me look at this set of atoms. Obviously, this corresponds to this triplet here, as I would expect, because it's a triplet next door. Due to the n+1 rule, we'd expect 2 hydrogens on this structure, and sure enough, here are 2 hydrogens. And then we get to complete our molecule over here, which corresponds to this peak. And again, that makes sense. It's a singlet, which means that the next door atom shouldn't have any hydrogens on it, and sure enough, it doesn't. So now let's write our full explanation. So just pointing out everything I've already mentioned, our integration ratio was 2 to 2 to 3. Just to remind you, that means that we had 2 hydrogens, and 3 hydrogens in the various environments. What about our peak at 3.95 is a Cl to CH2 next to a CH2. I'm just pulling this out from the structure I've drawn. And how do we know that? Because from the NMR we can see it's a triplet. Let's do the exact same thing here for the 3.65. We know that that's an OCH2 next to a CH2, as it's a triplet, and therefore it must be next to a carbon with 2 hydrogens. And then lastly, our chemical shift here with 3.35 is also an oxygen CH3. We can see that it's a singlet from the proton NMR, which means that the adjacent atom can't contain any hydrogens, as we see here. So we're just going to point that out. So to summarize, what did we do? We used the integration value to determine the number of hydrogens in each environment. Luckily, they added up to 7, so we could actually use that as an exact number. We used the chemical shift data to determine the likely type of proton. We also used the peaks, the fact that that was a triplet, which meant that the adjacent atom must contain 2 hydrogens. Again, that was true for this one. The adjacent atom must contain 2 hydrogens. And then this singlet here told us that the adjacent atom, in this case the oxygen, must contain no hydrogens. Now, chromatography is a separation technique used to separate and identify the components in a mixture. This mixture can be separated as long as it's first of all dissolved in a solvent and then it's passed over a solid. So let's look at these brief steps. So first of all, the mixture is dissolved in a solvent, and we call this solvent. It's known as the mobile phase. It is important that you know what that means. And then the resulting solution that's formed is passed over a solid. And that solid is known as the stationary phase. There are 3 main types of chromatography: thin layer chromatography, column chromatography, and gas chromatography. So starting with the first one, thin layer chromatography. So what happens here is a plate is coated with a solid, which is usually silicon dioxide, and then the solvent moves up the plate. So to give everything its correct label, the mobile phase, remember, is the solvent. The stationary phase is our solid, the silicon dioxide. And then after that plate's been run, it's possible to calculate the RF value, which you'll have met so many times before. To calculate that, we do the distance travelled by the component divided by distance travelled by solvent. Now, thin layer chromatography we met when we looked at the amino acid part of the specification. Remember I said that each of the amino acids has its very own RF value. So once you carry out thin layer chromatography with an unknown substance and you calculate that RF value, the number you'll be able to cross-reference with that table of known amino acid RF values, so you can use that to identify each amino acid. And why do the varying amino acids travel a different distance? Well, that's because each of the amino acids has a different polarity and therefore has a different affinity for the stationary phase and a different solubility in the mobile phase. Now, occasionally 2 different solvents will need to be used during our thin layer chromatography, and that's because some of the components might not dissolve in the first mixture, or if 2 or more components have the same RF value with the first solvent, there'll be no way of telling them apart. So how do we carry this out in the case where you need to use 2 solvents? So what happens here is you have your plate, which remember we said might be made from silicon dioxide. Here's your original spot. And then obviously as that solvent soaks up, and obviously where it stops moving, we call that the solvent front, that original spot is going to separate into 3 separate components. However, we believe that it's not finished. We think that there are still numerous components contained within each of these 3 dots. So our second stage is to rotate our plate by 90 degrees. So these 3 spots here, plus the original spot you can see down here, and then we start soaking in a small volume of a second solvent. That solvent will start moving up the plate, we'll have a new solvent front, and then once that solvent's allowed to dry, we add a developing agent, and look, from our original spot which originally produced 3 components, we can now see a grand total of 7 different components here. One extra thing to point out, they could ask you, how can we identify the positions of the amino acids on the TLC plate? And you just need to say shine under UV light. Now in column chromatography, a column is packed with a solid and a solvent which moves down the column. What is our mobile phase here? Well, we call it the eluent. And this is our mixture in the solvent. The stationary phase, remember we said, is solid. It could be silicon dioxide again or aluminium oxide. This is packed into a column, and as our mobile phase, the eluent, runs down the column, the components of the mixture move at different rates and can be collected separately in flasks at the bottom. Now, separation time depends on a balance between solubility or affinity of compounds in each phase. So to give that greater context, the greater the charge on a compound, the greater the affinity for that solid, that stationary phase, the longer the separation time. Now, gas chromatography, this time we have a column packed with a solid or a solid coated by liquid, and a gas is passed through the column under pressure at high temperature. So our mobile phase here is the unreactive gas, nitrogen or helium. Our stationary phase is the powder coated with oil. Now the components leave the column at different times after injections. This means that they have different retention times, and this is due to different relative affinities of components for mobile and stationary phases. The protein fibroin can be broken down into amino acids using an enzyme. A student uses TLC to identify these amino acids. The student identifies 2 of the amino acids as alanine and serine. Use the figure below to calculate the RF value of the unknown amino acid. Show your working. Use your RF value to identify the unknown amino acid. So what you're going to do is take this measurement here for the solvent front. This is 80 millimeters. Do the same now for the unknown amino acid, 27 millimeters. So the RF value is the distance moved by the amino acid divided by the distance moved by the solvent, 0.34. So we can see that that is glycine using the table here. The amino acids cannot be seen as they move during the experiment. State how the amino acids can be made visible at the end of the experiment using UV light. State why each amino acid has a different RF value. That's because each amino acid has a different affinity in the stationary and mobile phases. question is about TLC. A protein was hydrolyzed to form a mixture of amino acids. A spot of this mixture was added to a TLC plate and the plate placed vertically in a small volume of solvent 1. When the solvent front reached nearly to the top of the plate was removed and allowed to dry. The plate was turned anti-clockwise through 90 degrees and placed vertically in solvent 2. When the solvent front reached nearly the top of the plate was again removed and allowed to dry. And here we can see our final TLC plate. So here's the position of the original spot. So as we know, solvent 1 soaks up, drawing with it our original spot into its various components. And then this whole thing got rotated anti-clockwise through 90 degrees. And then in effect, this became the new reference line. So then the soaking occurred here. So solvent 2 moved all the components in this direction, so you can see how they've separated out. Suggest a suitable reagent for the hydrolysis of a protein. So touching on a different part of the specification, concentrated hydrochloric acid. Suggest how the positions of the amino acids on the TLC plate were located using ultraviolet light. Deduce the minimum number of amino acids present in the original mixture. Just count up these dots. 1, 2, 3, 4, 5, 6, 7. Suggest why it was necessary to use 2 different solvents. So you could write here some amino acids have the same RF value, or some of the amino acids did not separate in the first solvent. A tripeptide was heated with hydrochloric acid and a mixture of amino acids was formed. This mixture was separated by column chromatography. Outline briefly why chromatography is able to separate a mixture of compounds. Practical details are not required. Obviously, it says practical details are not required. I do want to mention, however, the mobile phase and the stationary phase. And what these are, the mobile phase is the solvent, different amino acids have different solubilities. So that will impact how far they move up the solvent. Now, the stationary phase, remember, is a solid, such as silicon dioxide. By comparing calculated RF values with known ones, it's possible to identify various amino acids. The dipeptide in part D is hydrolyzed in acidic conditions and the mixture produced is analyzed by column chromatography. The column is packed with a resin which acts as a polar stationary phase. Suggests why lysine leaves the column after alanine, and I've pulled down the structures of lysine and alanine for us to compare here. You do need to be aware of your amino acid chemistry. It says here that the dipeptide is hydrolyzed in acid conditions, which means that both of these amino acids will have a positive charge. Now, the lysine having more nitrogens means that it will have more positive charge, and therefore it will have a stronger affinity to the stationary phase, meaning that it leaves the column after alanine.